This video introduces the idea of finding the area between two curves. Let's start with some review. In Calculus 1, you approximated the area between a curve and the x-axis by dividing it up into tall, skinny rectangles. You represented the width of one of these rectangles using the symbols delta x. Here, delta x means a small distance along the x-axis, or a small change in x values. You picked out an x value, called a sample point, from each of these little subintervals along the x-axis, one sample point for each rectangle. The sample point on the x-axis for rectangle number I is denoted by xi star. You use these sample points and the function f to figure out the height of each rectangle. The height of rectangle number I is given by the function's value on the sample point, f of xi star. From this, you calculated the area of each rectangle. The area of a rectangle is base times height. So the area of the first rectangle is delta x times f of x1 star. The area of the second rectangle is delta x times f of x2 star. And the area of rectangle number I is going to be its base, delta x, times its height, f of xi star, and so on. If there are n rectangles, then the last rectangle will have base delta x and height f of xn star. So the approximate area under the curve is given by adding up all these areas of all these rectangles. In sigma notation, this can be written as sigma, the sum, from I equals 1 to n, the number of rectangles, of the area of the ith rectangle, delta x times f of xi star. The exact area is then given by the limit of these approximating areas as the number of rectangles goes to infinity. That's the limit as n goes to infinity of this Riemann sum of areas. A limit of a Riemann sum like this is by definition an integral. So we can rewrite this using the integral sign as the integral of f of x dx. And the bounds of integration here, based on our picture, are from x equals a to x equals b. Notice that when we convert the limit of a Riemann sum to integral notation, the sample points x sub I star just become our variable x, and the delta x becomes our dx. Now that we've reviewed these ideas of calculating the area under a curve, we're going to use these same ideas to calculate the area between two curves. To compute the area between two curves, y equals f of x and y equals g of x, in between the x values of a and b, we can again divide up the region into tall, skinny rectangles, as shown in this picture. Once again, let's let delta x be the width of each rectangle, and let's let xi star represent a sample point in the ith interval. So x sub I star is a point on the x-axis that lives in the rectangle number I. Now if we want to compute the area of one of these tall, skinny rectangles, as always, the area of a rectangle is the base times the height. The base of any of these rectangles is given by delta x, but the height is different for each rectangle. If I focus in on rectangle number I, I'll assume this is rectangle number I right here. It stretches all the way up to f of the sample point, f of x sub I star, and it stretches all the way down to g of that x sub I star. So the height of that rectangle is the gap between f of x and g of x at that sample point. In other words, it's the difference f of x sub I star minus g of x sub I star. Now that we have an expression for the area of one of these rectangles, we can add up all those areas as before to get an expression for the approximate area between the curves. It's just the sum of these areas. And as before, we can get the exact area by making these rectangles skinnier and skinnier by taking more of them. We take the limit as the number of rectangles goes to infinity of this Riemann sum, and as always, the limit of a Riemann sum is given by the integral. Where the x sub I stars, the sample points just become our variable x, and the delta x becomes our dx. Let's put in our bounds of integration. We're told that x goes between a and b, and we have an expression for the area between our two curves. Actually, this formula only works if f of x is greater than or equal to g of x on the interval from a to b. That inequality guarantees that this expression, f of xi star minus g of xi star, will be a positive number. We want a positive height for our rectangle so that we'll get a positive area. If instead f of x is less than or equal to g of x, then you'll need to switch around your subtraction and take the integral of g of x minus f of x dx instead in order to get a positive area. One way to remember what to do is just to write the integral as the integral from a to b of the top y value minus the bottom y value dx. Remembering that you'll need to replace the top y value and the bottom y value with functions of x before you can integrate. Let's look at an example. We want to find the area between the curve y equals x squared plus x and y equals 3 minus x squared. X squared plus x is a parabola pointing upwards, so that must be the red curve here, while 3 minus x squared is a parabola pointing downwards, so that must be this blue curve. We know that area is given by the integral from our starting x value to our ending x value of our top y values minus our bottom y values, all integrated with respect to x. Our top y values are given by the equation 3 minus x squared, and our bottom y values are given by the equation x squared plus x. Now we still need to figure out the values of a and b, the bounds of integration. And from the graph, it looks like a should be maybe about negative 1.5, and b should be about 1, since that's where the green area starts and ends in the horizontal direction. But to find exact values of a and b, the easiest thing to do is to set these two equations equal to each other and solve for x. So I'll set 3 minus x squared equal to x squared plus x. I can add x squared to both sides to get 2x squared plus x minus 3 equals 0. This factors into 2x plus 3 and x minus 1, and therefore x has to equal negative 3 halves, or x equals 1, just like we thought from the graph. So we can finish doing our setup. Our bounds of integration are from negative 3 halves to 1, and I can simplify my integrand here. This is 3 minus x squared minus x minus x, or in other words, the integral from negative 3 halves to 1 of minus 2x squared minus x plus 3 dx. This integrates to minus 2x cubed over 3 minus x squared over 2 plus 3x, evaluated between 1 and negative 3 halves. Now I just need to plug in my bounds of integration and then simplify to get 125/24. as the area. In this video, we saw that the area between two curves, in between the x values of a and b, can be given by the integral from a to b of the top y values minus the bottom y values dx, where the top y values and bottom y values are functions of x. More specifically, if the top curve is given by y equals f of x, and the bottom curve is y equals g of x, then this integral is the integral from a to b of f of x minus g of x dx. In this video, we'll calculate the volumes of solids of revolution. A solid of revolution is a three-dimensional object that can be formed by rotating a region of the plane around an axis. Volumes formed by rotating a region of the plane around a line are called solids of revolution. In this figure on the left, this three-dimensional object is formed by rotating a region of the plane shaped like this around the x-axis. The solid on the right can be formed by rotating a crescent-shaped region of the plane like this, again around the x-axis. If we slice these two solids of revolution using planes perpendicular to the x-axis, on the left side, our cross-sections look like discs. A disc here means the inside of a circle. The figure on the right is different because it's hollow inside, and when we slice it by planes perpendicular to the x-axis, we get cross-sections that are shaped like washers. A washer here means the region in between two concentric circles. So for solids of revolution, the cross-sections can have the shape of a disc or the shape of a washer. The area of a disc is given by the familiar formula pi r squared, where r is the radius, and the area of a washer can be written as pi times r outer squared minus pi times r inner squared, where r outer is the radius of the big circle and r inner is the radius of the little circle. This formula works because the area of the washer is just the area of the larger circle minus the area of the inside smaller circle. Now we know that the volume of any solid that can be sliced into cross-sections using planes perpendicular to the x-axis is given by v is the integral from x equals a to x equals b of the area of the cross-section at point x integrated dx. If our cross-sections are discs, this formula becomes the integral of pi r squared dx, where the radius r is a function of x. If instead the cross-sections look like washers, then the volume formula becomes the integral of pi r outer squared minus pi r inner squared dx. Again, r outer and r inner are functions of x here. These formulas work when the solid of revolution is formed by rotating a region around the x-axis, or any horizontal line. When we rotate around a horizontal line, then our cross-sectional discs or washers are perpendicular to the x-axis and are thin in the x direction. So it makes sense to integrate dx. If instead we want to rotate around the y-axis or a vertical line, then our disc or washer cross-sections are going to be perpendicular to the y-axis and are going to be thin in the y direction. So when rotating around the y-axis or a vertical line, we'll need to do our integral with respect to y. Our cross-sectional area will be a function of y, we'll integrate dy, and our bounds of integration will have to be y values. Our formulas will look pretty much the same. We'll just have to calculate our radii and bounds of integration in terms of y instead of x. As our first example, let's consider the region bounded by the curve y equals the cube root of x, the x-axis, and the line x equals 8. We want to find the volume of the solid of revolution found by rotating this region around the x-axis. Our cross-sections here are going to be disks, and these disks are thin in the x direction, so we're going to be integrating dx. Our smallest x value is 0, and our largest is 8, so those are our bounds of integration. And we want to integrate pi times the radius squared dx. Now the radius of our disks is given by the y-coordinate on this curve. So we can write r is equal to y, which is equal to the cube root of x, according to our equation. So we can rewrite the volume as the integral from 0 to 8 of pi times the cube root of x squared dx. I can pull out the pi and rewrite this integral using exponents and integrate, and then evaluate using bounds of integration to get 3/5 pi times 8 to the 5/3 minus 0. Now 8 to the 5/3 means 8 to the 1/3 raised to the 5th power. 8 to the 1/3 is 2, and 2 to the 5th is 32. So this expression simplifies to 3/5 pi times 32, or 96/5 pi. As our next example, let's consider the region in the first quadrant bounded by two curves, the curve y equals the cube root of x and y equals 1/4 times x. We'll start by rotating this region around the x-axis to get this sort of hollow vase shape. Notice that our cross-sections this time are shaped like washers, where the outer circle of the washer is swept out by the curve y equals cube root of x, and the inner circle is swept out by the curve y equals 1/4 x. We know our volume is given by the integral of pi times r outer squared minus pi times r inner squared. And since our washers are thin in the x direction, we know we'll need to integrate dx. Our bounds of integration are just our lowest x value of 0 and our largest x value, which is where these two curves intersect, which is an x value of 8. We can confirm that the two curves intersect when x equals 8 by setting them equal to each other and solving for x. Dividing both sides by x to the 1/3 and multiplying both sides by 4 gives us 4 equals x to the 2/3, and raising both sides to the 3/2 power gives us x equals 4 to the 3/2, or x equals 8. This confirms we have the correct bound of integration here. Now we need to figure out a formula for the outer radius as a function of x, and a formula for the inner radius also. Since the outer circle is swept out by the curve y equals cube root of x, the outer radius is just given by the y-coordinate of this curve, and as a function of x, that's the cube root of x. Now the inner radius is given by the y-coordinate of this line, and the y-coordinate of this line as a function of x is 1/4 x. So we've set up an equation for the volume of our solid, and a routine computation gives us a volume of 128/15 times pi. Now let's switch gears and rotate this region around the y-axis instead. Our cross-sections are still washers, but this time the washers are thin in the y direction, so we're going to be integrating with respect to y. Our bounds of integration are also y values and start at the minimum y value of 0 and the maximum y value of 2 that corresponds to this intersection where x equals 8 and y, which is the cube root of x, or 1/4 times x, is then equal to 2. For this problem, we need our r outer and our r inner to be functions of y. From the picture, we see that r outer is actually the x-coordinate on this line. The line has the equation y equals 1/4 x, and so x is equal to 4y. So that gives us our r outer as a function of y. To find r inner, we can do the same sort of thing, using the x-coordinate of the curve y equals cube root of x, but writing that x-coordinate in terms of y. We have y equals the cube root of x, means that x is equal to y cubed, and so r inner is equal to y cubed as a function of y. Putting this all together, we have an equation for volume. We can simplify this and integrate to get an answer of 512 pi over 21. In this video, we calculated the volumes of solids of revolution using the disk and the washer methods and the following formulas. One way to calculate the volume of a loaf of bread is to slice it into slices and calculate the volume of each slice separately. That's the idea to keep in mind as we cover this topic on volumes using cross-sections. A lot of three-dimensional objects are kind of like loaves of bread and can be naturally sliced into slabs or slices, like this. Let's suppose we've sliced our object into n slabs. We'll call them S1, S2 through Sn. In this picture, n is 7. Here's S1, here's S2, here's S3, and so on. We'll assume we've sliced in such a way that each slice is the same thickness. We'll call that thickness delta x. Well, the volume of the solid is just the sum of the volumes of the slices. In sigma notation, we can write this as the sum from I equals 1 to n, the number of slabs, volume of S sub I, the ith slab. Now the volume of the ith slab is approximately its cross-sectional area times its width. By cross-sectional area of the slab, I mean the area of the front or the back part of the slice where you might spread peanut butter. Well now, as you've noticed from making peanut butter sandwiches, the area of the front of the slice might be slightly different from the area of the back of the slice. So what we'll do is for each interval I, each slab, we'll just pick a sample point, x sub I star, that's in that ith interval. It could be on the left endpoint, or it could be on the right endpoint, or it could be in the middle somewhere. And we'll just look at the cross-sectional area. I'll call it A at x sub I star. That represents the area if I were to go karate chop right at that x sub I star and figure out the cross-sectional area at that point. Now we can go back and write our volume as the cross-sectional area at x sub I star times delta x, the thickness of the slice. Now this is just an approximation of volume, because this expression here gives you the volume as if the slices are very regular and have the same area from one side to the other. But it's a good approximation if the slices are thin, and in fact we can calculate the exact volume by taking the limit as the slices get thinner and thinner, or in other words, as the number of slices goes to infinity. What we have here is the limit of a Riemann sum, and therefore we can rewrite it as an integral, where the xi star becomes our variable x and the delta x becomes our dx. For the bounds of integration, we'll just use the abstract x values of a and b. For a real problem, we would fill these in based on the context of the problem. This gives us an abstract expression for the volume of a three-dimensional object. But in practice, in order to compute volumes like this, we'll first need a formula for A of x, the cross-sectional area as a function of x. As an example, let's try to find the volume of a solid whose base is an ellipse, given by this equation, and whose cross-sections perpendicular to the x-axis are squares. First, let me graph the base. It looks like an ellipse that's thinner in the x direction than in the y direction, so something like this. Now, sitting above this base are a bunch of squares, and the squares are oriented in such a way that they're perpendicular to the x-axis. So they're oriented sort of like this. I'll try to draw a square here. That's supposed to be coming out of the picture here. And here's another square, again coming out of the picture. Here's a slightly better picture that I drew using Mathematica. It's tilted, so we're looking at it from below, where you can see the ellipse here, and you can see the square cross sections. The x-axis is going in this direction. That's x, and the y-axis is in that direction. This picture is actually an approximation of the solid, where there are only about 8 or 10 slices. Each one's kind of thick and has the same area on the front and the back. A better picture of the solid is this one. Here the slices are infinitely thin, but they're still square-shaped, and they're still oriented in such a way that they're perpendicular to the x-axis. Now we know that volume is given by the integral from a to b of area as a function of x dx. On our ellipse, the minimum x value is -2 and the maximum x value is 2. So I can write those in for my bounds of integration. Also, I know that the area of a square is just the side length squared. So I can write my cross-sectional area as s of x squared, where s of x is the side length of the square as a function of x. Notice that for different x values, my side lengths are different, but my side length is always twice the y value, twice the distance from the x-axis to the y value on the ellipse. So I'll rewrite my formula as 2 times y as a function of x squared. And I can simplify this a little bit as the integral of 4 times y of x squared dx. Now all I need to do is find a formula for y as a function of x. And since I've got this equation up here relating y and x, all I have to do is solve for y in terms of x. In fact, I can get by solving for y squared, since I've really got y squared in my formula. Solving for y squared, I have y squared over 9 is equal to 1 minus x squared over 4, which means that y squared is equal to 9 times 1 minus x squared over 4. Now I'll plug this into my volume equation, and I get the integral from -2 to 2 of 4 times 9 1 minus x squared over 4 dx. I'll pull out the 4 times 9, that's 36, and integrate. Plugging in values and simplifying, we get a final answer of 96. Now, how would this problem be different if we used cross-sections that were perpendicular to the y-axis instead of the x-axis? Well, for one thing, our picture would look a little bit different, since our squares would now be running in the other direction. Since our squares are now thin in the y direction instead of the x direction, it makes sense to have the width of a slab be delta y and to compute our volume as an integral with respect to y. Our bounds of integration now also need to be y values, so they run from the minimum y value of -3 to the maximum y value of 3, and our cross-sectional area should also be written in terms of y. area is still side length squared, but now our side length is actually twice our x value instead of twice our y value. And we can write our x value squared in terms of our y value as 4 times 1 minus y squared over 9. Therefore, our area, which is our side length squared, which is 2x quantity squared, or 4x squared, is going to be equal to 16 times 1 minus y squared over 9. And we'll need to calculate our volume by taking the integral from -3 to 3 of 16 times 1 minus y squared over 9 dy. If we integrate this, we get an answer of 64, a different answer from the answer to our first problem. And it makes sense that we get a different answer, because we now have a different three-dimensional object with a different shape and a different volume. In this video, we saw that if we divide a three-dimensional object into slices, then the volume of the three-dimensional object is the integral of the cross-sectional area dx. In this video, I'll derive a formula to calculate the length of a curve given as a function y equals f of x. For a curve like this one, that's made up of a bunch of straight line segments, it's easy to calculate the length just by using the distance formula to find the length of each line segment. The distance formula says the distance between 2 points, x1, y1, and x2, y2, is given by the square root of x2 minus x1 squared plus y2 minus y1 squared. Applying this formula to the first line segment, connecting the points 1, 2, and 2, 3, we get a length of the square root of 2 minus 1 squared plus 3 minus 2 squared, which is the square root of 2. The length of the next line segment can be calculated similarly. And the next piece has length 2. We don't even need the distance formula for that one. And the last line segment has a length of the square root of 5. If we add up all the lengths of these 4 line segments, we get a total length of the curve of 2 times the square root of 5 plus the square root of 2 plus 2. We can use the same process to approximate the length of any curve by dividing it up into n small pieces and approximate the length of one small curved piece with a straight line segment, and using the distance formula to calculate the length of these line segments. In this picture, the curve is divided up into 9 subintervals. I'll label the corresponding points on the x-axis x0 for A, x1, x2, all the way through x8, and x9 is B. And I can label the points on my curve. So here's the 6th point, P6, has x-coordinates x6, and then y-coordinate will be f of x6, since my curve is given by the equation y equals f of x. More generally, I have n subintervals, and I'll label an arbitrary point P sub I. The point before it is then P sub I minus 1. And the length of the I segment is given by the distance between P sub I and P sub I minus 1. So that's the square root of x sub I minus x sub I minus 1 squared plus f of x sub I minus f of x sub I minus 1 squared by the distance formula. The total length of the curve can be approximated by adding the lengths of all these line segments up. So that's the sum from I equals 1 to n for the n line segments of these lengths. This is starting to look a little bit like a Riemann sum because of the sigma sign, but it's missing the delta x that I usually have out here. So I'm going to use a trick. I'm going to multiply each term of this expression by x sub I minus x sub I minus 1 divided by x sub I minus x sub I minus 1. This doesn't change the value of my expression, but it does introduce a delta x over delta x into my equation, because delta x represents the width of a subinterval, and that's equal to x sub I minus x sub I minus 1. Now I'm going to suck the factor in the denominator inside the square root sign. Notice I have to square it when I pull it inside the square root sign. Now I'm going to rewrite my fraction inside the square root sign. Now this first fraction is just 1, and this second fraction can be rewritten with a single squared sign. And this second expression should look familiar to you. It's the expression for the slope of a secant line. And if xi and xi minus 1 are very close to each other, the slope of that secant line is very close to the slope of a tangent line at a point in that interval. In fact, you might recall that the mean value theorem says that the slope of the secant line is actually exactly equal to the slope of a tangent line for some point, I'll call it xi star, in that interval. So I'll rewrite my expression for the approximate length of the curve. And since xi minus 1 can be written as delta x, I have a Riemann sum here. So if I want to find the exact arc length, I just need to take the limit of this Riemann sum. This is the limit as the number of intervals goes to infinity. We know that the limit of a Riemann sum is given by an integral. So the arc length is given by the integral of the square root of 1 plus f prime of x squared dx, starting from the first x value of a to the last x value of b. And so we've derived a formula for arc length. Sometimes this formula is also written with the alternative notation of dy dx instead of f prime of x. Let's use the arc length formula to find the length of the curve y equals x to the 3/2 between x equals 1 and x equals 4. That's this section of the curve drawn. Here's the general formula for arc length. And since dy dx for our curve is 3/2 x to the 1/2, we get that arc length is the integral from 1 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared dx. After simplifying a little bit, we can use u substitution to rewrite this. So we get the integral from 13/4 to 10 of the square root of u times 4/9 du, which integrates to u to the 3/2 divided by 3/2 times 4/9 evaluated between 10 and 13/4, which after some computation works out to 1/27 times 80, the square root of 10, minus 13, the square root of 13, or approximately 7.6 units, which seems about right based on the graph, taking into account the fact that the scale here is by 2's on the y-axis. In this video, we found the formula for the arc length of a curve. If the curve stretches from x equals a to x equals b, then the arc length is given by the integral from a to b of the square root of 1 plus f prime of x squared dx. This video introduces the idea of work from physics and the key role of integration in doing work calculations. If a constant force F is applied to move an object a distance d, then the work done to move the object is defined to be work equals force times distance, or in symbols, W equals F times D. The units of force can be given in metric units or in old-fashioned English units. Since force is mass times acceleration, the units of force are going to be units of mass, which are kilograms, times units of acceleration, meters per second squared. This collection of units is also called a Newton. In English units, force is given typically in terms of pounds. Now, the units of work, since work is force times distance, and distance in metric units is in meters, that gives units for work of kilograms meters squared per second squared, or we can write work as Newton meters. And this collection of units is also given its own name, which is the joule. If we're using English units for work, work again is force times distance, so the units become pounds times feet, or usually this is written instead as a foot-pound. Now if I give you my weight in pounds, I weigh about 140 pounds. Those pounds are already in a unit of force. So that 140 pounds, my weight, is also telling the force of gravity on my body. But if I tell you instead that my mass is 63.5 kilograms, well, that's a unit of mass, not a unit of force. So if I want to know the force due to gravity on my body, I'm going to have to multiply that 63.5 by the acceleration due to gravity, which is 9.8 meters per second squared. That product works out to be 622.3 kilogram meters per second squared. Notice that we now have the right units for force. We could also say that's the force of gravity on my body is 622.3 newtons. Now that we've familiarized ourselves with units a bit, let's do some examples. As our first example, how much work is done to lift a 2-pound book off the floor onto a shelf that's 5 feet high? Well, we know that work is force times distance, and 2 pounds is already a unit of force, and distance is 5 feet. So the work done is 10 foot-pounds. Now let's do the same problem in metric units. The 2-pound book is actually a 0.9 kilogram book, and we're lifting it off the floor onto a shelf that's about 1.5 meters high. Well, work is still force times distance, but now the force is 0.9 kilograms times the acceleration due to gravity, 9.8 meters per second squared, times our distance of 1.5 meters. That gives us a product of 13.23 kilograms meters squared per second squared, or in other words, 13.23 joules. In the previous two examples, force was constant, so we could just multiply force by distance to get work. Now let's consider the case where force is not constant. Let's say a particle moves along the x-axis from a point x equals a to a point x equals b, according to a force f of x that's a function of x and varies with x. How much work is done in moving the particle? Although the force is not constant on the whole interval from a to b, if we divide up that interval into a bunch of little subintervals, each of width delta x, then on any particular subinterval, the force is going to be approximately constant. It's not going to change a whole lot on a tiny little subinterval. As usual, let's pick a sample point x sub I star in the ith subinterval for each little subinterval. X sub I star could be the left endpoint of the subinterval, the right endpoint, or any point in the middle. Now on the ith subinterval, the force is approximately constant. It's approximately equal to F at x sub I star. Therefore, the work on that ith subinterval is approximately equal to this constant f x sub I star times the distance that the particle is going on that subinterval, but that distance is just the length of the subinterval, delta x. Instead of thinking of the big picture of the particle going all the way from A to B, I'm thinking of it going just along the first subinterval with an approximately constant force at a distance of delta x, and then it's going to go the second subinterval. Again, the force is approximately constant times the distance of delta x, and then we'll do some more work getting along the third subinterval, another approximately constant force times delta x, and so on. Each little tiny bit of the way, I'll get another little chunk of work, and then I can get the entire amount of work by adding all those little chunks of work up. So the total work done is going to be the sum from I equals 1 to n, where n is the number of subintervals, of the work done on each subinterval, which is f of x sub I star times distance delta x. I should say this is approximately the total work. In order to get the actual total work, we'll need to take a limit as we use more and more skinnier and skinnier subintervals. So the limit as n goes to infinity of this Riemann sum. The limit of a Riemann sum is an integral, so we've got the integral of the force, f of x, dx, and we'll integrate between the minimum x value of A and the maximum x value of B. And that's our formula for work. Let's look at a physical example. How much work is required to lift a 1,000 kilogram satellite from the Earth's surface to an altitude of 2 times 10 to the 6 meters above the Earth's surface? We're given that the gravitational force is F equals G times capital M times lowercase m divided by r squared, where m is the mass of the Earth, lowercase m is the mass of the satellite, r is the distance between the satellite and the center of the Earth, and g is the gravitational constant. We're also given numbers for the radius of the Earth, the mass of the Earth, and the gravitational constant. This problem is different from the problem of lifting the calculus book. When we lifted a book over just a few meters, the force of gravity was essentially constant over such a small distance. So we could use the equation work equals force times distance. But in this problem, since we're moving the satellite a larger distance, the force of gravity changes with distance. And so we need to use work as the integral of this force with respect to distance. The distance variable in this problem is r, so I'll rewrite this using the equation for force and integrate with respect to dr. I'm starting at the Earth's surface, so that's a distance of 6.4 times 10 to the 6th meters from the center of the Earth, since that's the Earth's radius. And I'm ending at a height of 2 times 10 to the 6 meters above the Earth's surface, so that's a distance r of 6.4 plus 2, or 8.4 times 10 to the 6 meters from the Earth's center. My only variable for this integral is r, so let me pull out the constants, and I'll rewrite the 1 over r squared as r to the minus 2. Now I can integrate, and r to the minus 2 becomes r to the minus 1 over minus 1. I'll rewrite one more time and substitute in for r to get a preliminary answer of negative g capital M, lowercase m, times negative 3.72024 times 10 to the minus 8. Now I still need to plug in for capital G, capital M, and lowercase m. My negatives cancel here. And I have G is 6.67 times 10 to the minus 11. Capital M, the mass of the Earth, is 6 times 10 to the 24. And lowercase m, the mass of the satellite, was 1,000 kilograms. Multiplying all these numbers together gives us a final answer of approximately 1.5 times 10 to the 10th joules. To put this number in perspective, this is about the same amount of work done by a car in a year, or by the human heart beating for about 400 years. In this video, we saw that for a constant force, work is just equal to the force times distance. But for a variable force, work is equal to the integral of force with respect to distance. This video introduces the idea of an average value of a function. To take the average of a finite list of numbers, we just add the numbers up and divide by n, the number of numbers. In summation notation, we write the sum from I equals 1 to n of qi, all divided by n. But defining the average value of a continuous function is a little different, because a function can take on infinitely many values on an interval from a to b. We could estimate the average value of the function by sampling it at finitely many evenly spaced x values. I'll call them x1 through xn, and let's assume that they're spaced a distance of delta x apart. Then the average value of f at these sample points is just the sum of the values of f divided by n, the number of values. Or in summation notation, the sum from I equals 1 to n of f of xi, all divided by n. This is an approximate average value of f, since we're just using n sample points. But the approximation gets better as the number of sample points, n, gets bigger and bigger. So we could define the average as the limit, as n goes to infinity, of this sample average. I'd like to make this look more like a Riemann sum, so I need to get delta x in there. So I'm just going to multiply the top and the bottom by delta x, and notice that n times delta x is just the length of the interval, b minus a. Now as the number of sample points goes to infinity, delta x, the distance between them, goes to 0. So I can rewrite my limit as the limit as delta x goes to 0 of the sum of fxi times delta x divided by b minus a. Now the limit of this Riemann sum in the numerator is just the integral from a to b of f of x dx. And so the average value of the function is given by the integral on the interval from a to b divided by the length of the interval. Notice the similarity between the formula for the average value of a function and the formula for the average value of a list of numbers. The integral for the function corresponds to the summation sign for the list of numbers, and the length of the interval, b minus a, for the function corresponds to n, the number of numbers in the list of numbers. Now let's work an example for the function g of x equals 1 over 1 minus 5x on the interval from 2 to 5. We know that the average value of g is given by the integral from 2 to 5 of 1 over 1 minus 5x dx divided by the length of that interval. I'm going to use u substitution to integrate. So I'm going to set u equal to 1 minus 5x. So du is negative 5 dx. In other words, dx is negative 1/5 times du. Looking at my bounds of integration, when x is equal to 2, u is equal to 1 minus 5 times 2, which is negative 9, and when x is equal to 5, u is equal to negative 24. Substituting into my integral, I get the integral from negative 9 to negative 24 of 1 over u times negative 1/5 du. And that's divided by 3. Now dividing by 3 is the same as multiplying by 1/3, and as I integrate, I'm going to pull the negative 1/5 out, and then take the integral of 1 over u, that's ln of the absolute value of u, evaluated in between negative 24 and negative 9. The absolute value signs are important here because they prevent me from trying to take the natural log of negative numbers. To evaluate, I get negative 1/15 times ln of 24 minus ln of 9. I can use my log rules to simplify and get negative 1/15 ln of 24 over 9. That's negative 1/15 ln of 8/3, and as a decimal, that's approximately negative 0.0654. So I've found the average value of g. Now my next question is, does g ever achieve that average value? In other words, is there a number c in the interval from 2 to 5 for which g of c equals its average value? Well, one way to find out is just to set g of c equal to g's average value. In other words, set 1 over 1 minus 5c equal to negative 1/15 ln of 8/3, and try to solve for c. There are lots of ways to solve this equation, but I'm going to take the reciprocal of both sides, subtract 1 from both sides, and divide by negative 5. This simplifies to 3 over ln of 8/3 plus 1/5, which is approximately 3.25, and that x value does lie inside the interval from 2 to 5. So we've demonstrated that g does achieve its average value over the interval, but in fact we could have predicted this to be true. G's average value has to lie somewhere between g's minimum value and maximum value on this interval, and since g is continuous on the interval from 2 to 5, it has to achieve every value that lies in between its minimum and maximum, including its average value. This same argument shows that for any continuous function, the function must achieve its average value on an interval, and this is known as the mean value theorem for integrals. Namely, for any continuous function f of x on an interval from a to b, there has to be at least one number c between a and b such that f of c equals its average value, or in symbols, f of c equals the integral from a to b of f of x dx divided by b minus a. This video gave the definition of an average value of a function and stated the mean value theorem for integrals. If we rewrite the formula for average value a little, then we can see a geometric interpretation for average value. The area of the box with height the average value is the same as the area under the curve. This video gives two proofs of the mean value theorem for integrals. The mean value theorem for integrals says that for a continuous function f of x defined on an interval from a to b, there's some number c between a and b such that f of c is equal to the average value of f. The first proof that I'm going to give uses the intermediate value theorem. Recall that the intermediate value theorem says that if we have a continuous function f defined on an interval, which I'll call x1, x2, if we have some number L in between f of x1 and f of x2, then f has to achieve the value L somewhere between x1 and x2. Keeping in mind the intermediate value theorem, let's turn our attention back to the mean value theorem for integrals. Now it's possible that our function f of x might be constant on the interval from a to b. But if that's true, then our mean value theorem for integrals holds easily, because f av is just equal to that constant, which is equal to f of c for any c between a and b. So let's assume that f is not constant. Well, a continuous function on a closed interval has to have a minimum value and a maximum value, which I'll call little m and big M. Now we know that f's average value on the interval has to be between its maximum value and its minimum value. If you don't believe this, consider the fact that all of f's values on the interval have to lie between big M and little m. And if we integrate this inequality, we get little m times b minus a is less than or equal to the integral of f is less than or equal to big M times b minus a. Notice that the first and the last integrals were just integrating a constant. Now if I divide all three sides by b minus a, I can see that little m is less than or equal to the average value of f is less than or equal to big M, as I wanted. Now I just need to apply the intermediate value theorem, with f's average as my number L and little m and big M as my values of f of x1 and f of x2. The intermediate value theorem says that f average is achieved by f of c for some c in between my x1 and x2, and therefore for some c in my interval AB. And that proves the mean value theorem for integrals. Now I'm going to give a second proof for the mean value theorem for integrals, and this time it's going to be as a corollary to the regular mean value theorem for functions. Recall that the mean value theorem for functions says that if g of x is continuous on a closed interval and differentiable on the interior of that interval, then there's some number c in the interval such that the derivative of g at c is equal to the average rate of change of g across the whole interval from a to b. Let's keep the mean value theorem for functions in mind and turn our attention back to the mean value theorem for integrals. I'm going to define a function, g of x, to be the integral from a to x of f of t dt, where f is the function given to us in the statement of the mean value theorem for integrals. Notice that g of a is just the integral from a to a, which is 0, while g of b is the integral from a to b of our function. Now, by the fundamental theorem of calculus, our function g of x is continuous and differentiable on the interval ab, and g prime of x is equal to f of x. And by the mean value theorem for functions, we know that g prime of c has to equal g of b minus g of a over b minus a for some number c in the interval ab. If we substitute in the three facts above into our equation below, we get f of c is equal to the integral from a to b of f of t dt minus 0 over b minus a, which is exactly the conclusion that we wanted to reach. This shows that the mean value theorem for integrals really is the mean value theorem for functions, where our function is an integral. And this completes the second proof of the mean value theorem for integrals. So now I've proved the mean value theorem for integrals in two different ways, and I've used a lot of the great theorems of calculus along the way. In this video, we'll learn a technique of integration called integration by parts. Integration by parts is based on the product rule for taking derivatives. Recall that the product rule says that when you take the derivative of a product of two functions, that's equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. If we rearrange this formula by solving for this last term, we get f of x times g prime of x is equal to f of x g of x prime minus f prime of x g of x. Now let's integrate both sides of this equation with respect to x. The integral of a difference is the difference of the integrals, so I can break up this right-hand side into two integrals. Now the integral of the derivative of f times g is just equal to f times g by the fundamental theorem of calculus. And I carry the rest of the formula down. And now I have a formula relating the integral of f times g prime to the integral of f prime times g. This formula allows us to rewrite something that might be tricky to integrate in terms of something that's hopefully easier to integrate. Although I've written this formula using indefinite integrals with no bounds of integration, it would be just as easy to put on bounds of integration. Now the fundamental theorem tells us that the integral of the derivative is the original product of functions evaluated from a to b. There's another version of this formula that might be a little easier to remember. If we let u equal f of x and v equal g of x, then du is equal to f prime of x dx using differential notation, and dv is equal to g prime of x dx. In this notation, we can rewrite the formula as the integral of u times dv is equal to u times v minus the integral of v du, since v is our g of x and du is our f prime of x dx. Again, we can include bounds of integration if we're working with definite integrals. This will be our key formula for this section, and integrating using this formula is called integration by parts. Let's use integration by parts to find the integral of x e to the x dx. Our formula for integration by parts says the integral of u dv is equal to u times v minus the integral of v du. So we need to split up our integrand x e to the x dx into a part that we're going to call u and a part that we're going to call dv. One natural way to split it up is to let u equal x and dv equal e to the x dx. But another option might be to make u equal to e to the x and dv equal to x dx. Or we might decide to make u be the whole product x e to the x and leave dv as just dx. Whatever choice we make, we need u times dv to be our entire integrand here, and we need dx to be part of dv in order to use proper differential notation. Let's try using the first choice first. If u is equal to x, then du is equal to dx, and if dv is e to the x dx, then we can find v by integrating this, and the integral of e to the x dx is e to the x. Plugging into our integration by parts formula, we have the integral of u dv, that's x e to the x dx, is equal to u times v, x e to the x, minus the integral of v du, that's e to the x dx. Well, this is looking very promising because I know how to integrate e to the x dx. It's just e to the x plus a constant of integration. And so integration by parts has allowed us to compute our integral. Let's check our answer by taking the derivative of what we got. The derivative of x e to the x minus e to the x plus c is going to be the derivative of x, that's 1, times e to the x, plus x times the derivative of e to the x, which is e to the x, minus the derivative of e to the x, which is again e to the x, plus the derivative of c, which is just 0. And since this term and this term cancel out, we're left with x e to the x, which is exactly what we started out with as our integrand. So we've checked that our work is correct. Notice that in order to take the derivative of our answer, we ended up having to use the product rule. And that's no coincidence, because the formula for integration by parts is really just the product rule, used in reverse. So we were successful in computing this integral using our first choice of u and dv. But before we leave this problem, let's see what would have happened if we'd used a different choice instead. If we'd used u equal to e to the x and dv equal to x dx. If we'd done that, then we would have gotten du to be e to the x dx, and we would have computed v by integrating x dx to get x squared over 2. Plugging this into our formula for integration by parts, we would get the integral of u dv, that's e to the x, times x dx, is equal to u times v, that's e to the x, times x squared over 2, minus the integral of v du, that's x squared over 2, times e to the x dx. Now, in order to go any further, we need to be able to compute the integral of x squared over 2 times e to the x dx. Dividing by 2 poses no problem, that's just a constant. But the integral of x squared e to the x, that's more complicated than the integral of e to the x times x that we started with. So we're going the wrong direction here. And this turns out to be a poor choice of u and dv. I'll let you check that the third choice of u and dv that I suggested also ends up making things more complicated instead of simpler. So the first choice turned out to be the best choice for u and dv. Integration by parts works by replacing an integral of the form u dv by the equivalent expression u times v minus the integral of v du. That's hopefully easier to compute.
Okay, we're going to do integration by parts using the table method, and we're going to start with the integral of x squared e to the x dx. So first we are going to make a table of u and dv. So in this case, our u would be x squared, and our dv would be e to the x. So down the entire line of u, we derive x squared. And down the entire dv, we integrate e to the x. We want to derive u until it reaches 0. Then we can cross multiply through the table. This will be positive, this will be negative, this will be positive, and this will be negative. So then, when we plug it back into a formula, we get x squared e to the x minus 2x e to the x plus 2 e to the x, and then 0 times e to the x is just 0. And this is our end product. The table method still works for more complicated integrals, it's just a little more complex. So we have the integral of x ln of x we set up our table, u dv, where u will equal ln of x and dv will equal x. When we derive down the table, we get 1 over x, and when we integrate down dv, we get 1/2 x squared. Now we want to stop because we know that if we continue to derive 1 over x, it will just get more and more complicated. For example, if we do the next derivative, the next step would be 1 over x squared negated. This is more complicated than 1 over x. So that means that we want to stop deriving at 1 over x. So next we cross multiply like we did before, where this is positive and this is negative. Then when we go to set up our equation, it'll look like this. 1/2 x squared times ln of x minus integral of 1 over x 1/2 x squared dx. When the final term in the u column does not go to 0, the last multiplication across will be in an integral. And that's the table method.
There are a lot of trig identities that come in handy when you're doing calculus. But the good news is, if you're willing to do a little bit of algebra, there are only a few that you really have to memorize. In this video, I'll tell you my 3 favorite trig identities and show you how to derive a bunch more with very little effort from these 3. So I'm going to tell you the 3 trig identities that I think everybody should know. Fortunately, all 3 of them are very easy to remember. The first one is the Pythagorean identity. That's the identity that says sine squared of theta plus cosine squared of theta is equal to 1. That one's easy to remember because it's really just the Pythagorean theorem for triangles in the context of the unit circle. If I draw a right triangle with angle theta on the unit circle, its hypotenuse has length 1 because a unit circle means a circle of radius 1. The base of this triangle has length cosine of theta because by definition cosine of theta is the x-coordinate of the point on the unit circle at angle theta. Similarly, the height of the triangle is sine of theta because sine of theta means the y-coordinate on the unit circle. So by the Pythagorean theorem for right triangles, we know that sine theta squared plus cosine theta squared equals 1, which is exactly the Pythagorean identity. The second identities that everybody should know are the even and odd identities. I guess technically these are 2 different identities, but they go together, so I'm counting them as 1. The even identity says that cosine of negative theta is equal to cosine of theta. In other words, cosine is an even function. And the odd identity says that sine of negative theta is equal to negative sine of theta. In other words, sine is an odd function. One way to remember these identities is by looking at the graphs of sine and cosine. Y equals cosine x has this bilateral symmetry, so it's an even function. And if I look at the value of cosine at theta and cosine at negative theta, my graph has the same height, so cosine has the same value for both of these angles. The graph of y equals sine x does not have bilateral symmetry. Instead, it's got a 180-degree rotational symmetry, which is characteristic of an odd function. And if I compare the y values at theta and negative theta, I see that the y value at negative theta is exactly the opposite as the y value at theta, and therefore sine of negative theta is equal to negative sine of theta. Another way to understand the even and odd identities is by going back to the unit circle. If I look at an angle of theta compared to an angle of negative theta, the x-coordinate, which is cosine, has the same value for both of these angles. So that means cosine of negative theta is equal to cosine of theta. The y-coordinate, instead, is the opposite for negative theta versus theta. One of them is positive and one of them is negative, but they have the same magnitude. Therefore, sine of negative theta is the negative of sine of theta. My third favorite trig identity is the angle sum formula. Again, there are really two, one for sine and one for cosine, but they go together, so I'll consider them a single identity. These identities are easy to remember because there's a song that goes with them. And the song goes sine, cosine, cosine, sine, cosine, cosine, minus sine, sine. You may recognize the tune. Please sing along with me this time so you'll remember it. 1, 2, 3, go. Sine, cosine, cosine, sine, cosine, cosine, minus sine, sine. The only thing you have to remember when you sing this song is that it gives the sine of a plus b first, and then the cosine of a plus b. So these are the three trig identities that I think everybody should memorize. Next, I'll show you how to derive a bunch more trig identities pretty simply from these three. I've written my three favorite trig identities across the top for easy reference. First of all, we can derive a couple good identities just from the Pythagorean identity. Let's start by dividing both sides of this identity by cosine squared theta. We can break up the fraction on the left into sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. But sine squared theta over cosine squared theta is just tan squared theta. And cosine squared theta over cosine squared theta is 1, and 1 over cosine squared theta is secant squared theta, since secant theta, by definition, is 1 over cosine. So we found a new identity, a variation on the Pythagorean identity that involves tangent and secant. Now, what if we wanted an identity that involved cotangent and cosecant instead? Well, as you might be thinking, we could just start with the Pythagorean identity, and this time divide both sides by sine squared of theta. If we break up the fraction like before, we get 1 plus cotangent squared theta equals cosecant squared theta. Since cotangent is cosine over sine and cosecant is 1 over sine. Next, it's possible to get a bunch of great identities from the angle sum formulas. Let's start by deriving an angle difference formula. If we want a formula for sine of a minus b, all we have to do is plug in negative b for b in our angle sum formula. So we get sine of a cosine of negative b plus cosine of a sine of negative b. But we know that cosine of negative b is cosine of b, since cosine is even, and sine of negative b is negative sine of b, so that turns this positive sign to a negative sign. And we have an angle difference formula for sine. Similarly, we can use the angle sum formula for cosine, plugging in negative b for b, and use the even-odd properties to get an angle difference formula for cosine. Now let's derive a super useful formula the double angle formula. If we want a formula for sine of 2 theta, we can think of that as being the sine of theta plus theta. So let's plug theta in for A and theta in for B in our angle sum formula. That gives us sine, cosine, cosine, sine, which simplifies to 2 sine theta cosine theta. That's the double angle formula for sine. That worked out so well. Let's try the same thing for cosine. Cosine of 2 theta is cosine of theta plus theta, and using the angle sum formula, that's cosine, cosine, minus sine, sine. We can rewrite this as cosine squared theta minus sine squared theta and get our first version of the double angle formula for cosine. But we could also use the Pythagorean identity to replace cosine squared theta by 1 minus sine squared theta. Or if we prefer, we could replace sine squared theta by 1 minus cosine squared theta. If we replace cosine squared, we get cosine of 2 theta is 1 minus sine squared theta minus sine squared theta. In other words, cosine of 2 theta is 1 minus twice sine squared theta. And if we go back to the original and replace sine squared theta by 1 minus cosine squared theta, we get cosine of 2 theta is cosine squared theta minus quantity 1 minus cosine squared theta, which simplifies to cosine of 2 theta is twice cosine squared theta minus 1. So we found one version of a double angle formula for sine and 3 versions for cosine just using the angle sum formula and the Pythagorean identity. These last 2 formulas are particularly useful for integration when they're rewritten slightly. For this formula, let me solve for sine squared of theta. I get 2 sine squared of theta is equal to 1 minus cosine of 2 theta, so sine squared of theta is 1/2 minus 1/2 cosine of 2 theta. I'll do the analogous thing with this formula and solve for cosine squared theta. 2 cosine squared theta is equal to 1 plus cosine of 2 theta, so cosine squared theta is equal to 1/2 plus 1/2 cosine of 2 theta. That's all the trig identities we're going to need. It may seem like a lot, but remember, they all follow very naturally from my 3 favorites at the top. While all these formulas are very useful, the ones that are of particular importance for techniques of integration are the first one, the Pythagorean identity and its various forms, and the last 2. In this video, I told you my 3 favorite trig identities: the Pythagorean identity, the even and odd identities, and the angle sum formulas. From these, I derived a bunch of other identities, including a handful that will be particularly useful as we do techniques of integration. Remember the angle sum formulas? Those are the formulas for computing sine of a plus b and cosine of a plus b. I like to sing them: sine, cosine, cosine, sine, cosine, cosine, minus sine, sine. This video gives a geometric proof of those formulas. There are many great proofs of the angle sum formulas, but I'd like to share with you one of my favorites for those who are interested. I'll write the angle sum formulas up here so we'll know what we're trying to prove. To prove these formulas, let me start by drawing an angle A and an angle B on top of that. Next, I'm going to draw a line perpendicular to this middle line and I'm going to extend the top line until it meets that perpendicular, making a right triangle. Finally, I'll draw a rectangle around that right triangle that just touches its vertices. My rectangle is now divided up into 4 right triangles, and I'm going to choose units of measurement so that the hypotenuse of my middle triangle has length 1. Now let's stop for a minute to think about the angles of these other triangles. Since the top and the bottom edge of the rectangle are parallel lines, and this hypotenuse is a transversal, this angle up here must have the same measure as A plus B down here. Also, this skinny angle here must have the same measure as A down here, because this angle is 180 degrees minus 90 degrees minus this angle here, and this angle A is also 180 degrees, the measure of the angles in a triangle, minus 90 degrees minus that same angle. So I'll label this skinny angle with A. Next, let's figure out as many side lengths as we can. Based on the middle right triangle with hypotenuse 1, we know that this side length down here must be cosine of B, since adjacent over hypotenuse is cosine B. Similarly, this side length here must be sine of B, since opposite over hypotenuse is sine of B. Now we see that sine of B is the hypotenuse of this right triangle, which means that this little side here has measure sine A times sine B. That's because the opposite over the hypotenuse of this angle has to equal sine A. A similar argument shows that this side has to have measure cosine A times sine B. Please pause the video and take a moment to fill in the side lengths of this right triangle and this right triangle. You should be getting sine A cosine B, cosine A cosine B, sine of A plus B, and cosine of A plus B. But remember, we have a rectangle here, so the opposite sides have equal length. This tells us that sine of A plus B has to equal sine of A cosine of B plus cosine of A sine of B, which is exactly the first angle sum formula. Also, cosine of A plus B, which is this side length, is exactly the difference of this side length, cosine A cosine B, minus this side length, sine of A sine B. And that's the second angle sum formula. So I think that's a pretty great geometric proof of the angle sum formulas. This video is about integrating trig functions that involve at least one odd power of sine or cosine. Let's start by evaluating the integral of sine to the 4th x times cosine x dx. This integral is a good candidate for u substitution. If we let u equal sine of x, then du is equal to cosine of x dx, and we can rewrite the integral as the integral of u to the 4th du. This integrates easily to 1/5 times u to the 5th plus c, and I can convert things back to x by plugging in sine of x for u to get 1/5 sine to the 5th of x plus c. The next integral, the integral of sine to the 4th x times cosine cubed x dx, can also be handled with a similar u substitution, with a bit more work. First, I'm going to rewrite the integral as the integral of sine to the 4th x times cosine squared x times cosine of x dx. I'm rewriting the cosine cubed of x as cosine squared of x times cosine x in the hopes that I can use cosine of x dx as my du, like I did in the previous problem. Now if we have du as cosine of x dx, we're going to need u to be sine of x. But unlike the previous problem, I can't just replace sine to the fourth x with u to the fourth and cosine x dx with du and be done, because I've got this cosine squared x hanging around that I need to deal with. I wish I didn't have that cosine squared x. I wish everything else over here was just written in terms of sine. Now, as you might realize, it's not hard for me to get my wish. We know from the Pythagorean identity that cosine squared of x plus sine squared of x is equal to 1, so cosine squared of x can be written as 1 minus sine squared x. Making that substitution, I can now rewrite my integral entirely in terms of u and du. Now if I multiply things out, this becomes easy to integrate. And I get 1/5 u to the 5th minus 1/7 u to the 7th plus c, and I can rewrite this in terms of x. To recap, we separated out one copy of cosine x to be part of our du, and then we converted the rest of the cosines into sines using the Pythagorean identity. This allowed us to do u substitution with u equal to sine x and evaluate the integral. This same technique, with some modifications, works on a lot of other problems. In this next problem, if we tried separating out one copy of cosine of x to be part of our du, we'd run into problems because we just have one copy of cosine x left, and we can't use the Pythagorean identity to convert a single cosine into sines. Well, I guess technically we could do something like this, but then we'd have to introduce a plus or minus sign and a square root sign into our integrand, which would make things difficult to integrate. It's a lot easier if we can just use the cosine squared x is equal to 1 minus sine squared x identity to replace our cosines with sines, but this identity only applies if we have an even power of cosines left over that we want to convert. So instead of trying to save out a copy of cosine x, let's save out a copy of sine x instead. So we'll rewrite our integral as the integral of sine to the fourth of x times a sine of x, and we'll keep the cosine squared x and the dx. Now we want the sine x to be part of our du. So let's set u equal to cosine of x. That way du is equal to negative sine of x dx, and so sine of x dx is equal to negative du. Since u is equal to cosine x this time, we want to replace all of our stray sines with cosines. We know that sine squared of x is equal to 1 minus cosine squared of x by the Pythagorean identity. So let's rewrite this sine to the fourth as sine squared of x squared. That allows us to substitute in 1 minus cosine squared of x for sine squared of x. And now we can replace everything with u's and du's. I'll bring out the negative sign and multiply things out. 1 minus u squared squared is 1 minus 2u squared plus u to the fourth. And this multiplies out to u squared minus 2u to the fourth plus u to the sixth. Now I can integrate, distribute my negative sign, and finally plug in cosine of x for u. That completes this problem. In this video, we used u substitution and the Pythagorean identity to evaluate integrals with at least one odd power of sine or cosine. The idea is to separate off one copy from the odd power that one copy becomes part of our du, and the remaining even power gets converted using the Pythagorean identity. In this case, we convert sine squared into 1 minus cosine squared. This allows us to do the u substitution and evaluate the integral. In this video, we'll evaluate integrals of trig functions involving only even powers of sine and cosine. There are three trig identities that will come in handy here. The first one's our familiar Pythagorean identity. The second one's an identity that allows us to rewrite cosine squared of x in terms of cosine of 2x. And the third one is the identity that lets us write sine squared of x, also in terms of cosine of 2x. The only difference between the second and third is, well, the fact that one's cosine squared and one's sine squared, but the other difference is the plus sign versus the minus sign here. Let's start with the simplest possible even power, the integral of cosine squared x dx. According to my calculator, this integral evaluates to sine x cosine x over 2 plus x over 2. And if I look it up in the back of my book, I get the integral to be 1/2 x plus 1/4 sine of 2x. So what's going on here? Are these two answers really the same? Well, yes, because sine of 2x is equal to 2 times sine x cosine x. So if I replace that here, I get that this second answer is equivalent to 1/2 x plus 1/4 times 2 sine x cosine x, which is equivalent to the first answer. Notice that the calculator and the table in the back of the book omit the plus c, the constant of integration, but you should always include them for indefinite integrals. Now let's see where these answers come from. So let's compute the integral of cosine squared x dx by hand, that is, without the aid of a calculator, computer, or integral table. The hint is that cosine squared x is equal to 1 plus cosine 2x over 2, or sometimes I like to write this as 1/2 plus 1/2 cosine of 2x. So I'll use that identity to rewrite my integral. Now I can split up the integral using rules about integration. The integral of 1/2 is just 1/2 x, and the integral of cosine of 2x is 1/2 times sine of 2x. It's possible to get that answer by u substitution with u equal 2x. Or as a shortcut, we can observe that the derivative of sine of 2x is cosine of 2x times 2. The times 2 comes from the chain rule, taking the derivative of the inside. So to get rid of that or counteract that times 2, we have to multiply by 1/2. In any case, our final answer is then 1/2 x plus 1/4 sine of 2x plus c. This is the same answer that we can find using the integral table in the back of the book. Please pause the video for a minute and try to compute the integral of sine squared x dx using a similar technique. You'll want to use the identity sine squared of x is equal to 1/2 minus 1/2 cosine of 2x. If you rewrite the integral, you can integrate like before and get an answer of 1/2 x minus 1/4 sine of 2x plus c. This same technique can be used to evaluate a lot of other integrals involving even powers of sine and cosine, often with a lot more effort. Let's try evaluating the integral of sine to the 6x dx. We know that sine squared of x is equal to 1/2 minus 1/2 cosine of 2x. And since 6 is an even power, we know we can rewrite sine to the 6th as sine squared to the x raised to a power, in this case the power of 3. Now let's substitute in our identity. I think think I'm going to factor out the 1/2. 1/2 cubed is 1/8, so I'll pull the 1/8 out of the integral sign and multiply out. Now let me divide up my integral into pieces, and I'll try to handle each piece separately. The integral of 1 dx, that's easy, that's x. And the integral of cosine of 2x, that's going to be 1/2 times sine of 2x, like before. Now to integrate cosine squared of 2x, we can use the same trick we used to integrate cosine squared of x. Cosine squared of 2x is going to be 1/2 plus 1/2 cosine of 2 times 2x, so that's 4x. And finally, to integrate cosine cubed of 2x, well, cosine cubed is an odd power, so we can use our odd power trick and save aside one copy of cosine and turn the remaining cosine squareds into 1 minus sine squared. So that looks like this. Notice we have 1 minus sine squared of 2x because we're replacing a cosine squared of 2x. I'll copy the first part down, and now I'll integrate 1/2 to get 1/2 x, and I'll integrate 1/2 cosine of 4x to get 1/2 times 1/4 sine of 4x. We need the 1/4 to counteract the 4 that we get by taking the derivative of sine of 4x and using the chain rule. We can finish off the integration by using a u substitution here, where u is sine of 2x, and so du is 2 cosine of 2x. So we can replace this integral here with minus the integral of 1 minus u squared times 1/2 du. I'll copy the first part down again and integrate that last part. I'll pull out the negative 1/2, and I get u minus 1/3 u cubed. I need a plus c now. I'll plug back in for u and simplify a little bit, and I get a final answer of 5/16 x minus 1/4 sine of 2x plus 3/64 sine of 4x plus 1/48 sine cubed of 2x. Oh, and we need a plus c here. That's a complicated answer, and it was a complicated computation. But it was all based on the same sort of tricks as before, using identities like this one to handle even powers of sine and cosine, and using the Pythagorean identity to handle odd powers. In this video, we used these last two identities to rewrite even powers of cosine and sine in terms of lower powers of cosine. This trick can be used to compute the integrals of complicated even powers of sine and cosine, provided that you have a lot of time and patience on hand. This video is about some special trig integrals, namely the integral of tangent squared of x and the integral of secant of x. These integrals are special only in the sense that there's some special tricks required to integrate them. When I come across the integral of tangent squared x, I find myself wishing that I could integrate secant squared x instead, because integrating secant squared x is easy. It's just tangent x plus c, since the derivative of tangent is secant squared. But happily, I know how to rewrite tangent squared in terms of secant, because tangent squared is secant squared minus 1. So I'll just rewrite this integral as the integral of secant squared minus 1, and that integrates easily to tangent of x minus x plus c. The same sort of trick works to integrate cotangent squared of x, since there's a similar identity relating cotangent and cosecant. Every now and then, you have to integrate secant of x. There's several possible tricks that can be used to do this. One of them is to multiply secant x by secant x plus tangent x in the numerator and denominator. Now distributing, we get secant squared x plus secant x tangent x in the numerator and secant x plus tangent x in the denominator. Since secant squared is the derivative of tangent and secant tangent is the derivative of secant, we can set u equal to secant x plus tangent x and have du sitting right where we want it in the integrand. So now we just have to integrate 1 over u du, which is the ln of u plus c, and now plugging back in for u, we get that our original integral of secant x evaluates to the natural log of secant x plus tangent x plus a constant. A similar trick can be used to evaluate the integral of cosecant x. And that's all for the integral of tangent squared and the integral of secant. This video introduces the technique of trig substitution to evaluate integrals involving square root signs, like this one. There are a few trig identities that are especially useful for this technique. The first one's the Pythagorean identity, and the second is the related identity that involves tangent and secant. There's also a third related identity that involves cotangent and cosecant. This one could also be used in the method of trig substitution, although it doesn't come up as often as the first two. As our first example, let's look at the integral of x squared over the square root of 49 minus x squared. According to Wolfram Alpha, this integral evaluates to this expression involving a square root expression, kind of as expected, and a sine inverse, which just sort of seems to come out of the blue here. Let's see where this answer comes from using a trig substitution. The inverse sine function in the answer gives us a hint that we may want to substitute in something related to sine. I'm going to substitute in x equals 7 sine theta. If x is 7 sine theta, then dx is going to be 7 cosine theta d theta. Now I'll substitute in for x and dx in my integral to get the integral of 7 sine theta squared over the square root of 49 minus 7 sine theta squared times 7 cosine theta d theta. Let me simplify a little. I have a 7 cubed in the numerator times sine squared theta cosine theta. And the denominator I have 49 minus 49 sine squared theta. I'll factor out the 49 here. And since the square root of 49 is 7, I can pull a 7 out of the square root sign. Now here is where a little bit of magic occurs. I know that 1 minus sine squared theta is equal to cosine squared theta by the Pythagorean identity. And the square root of cosine squared theta is equal to cosine theta. Well, actually it's equal to the absolute value of cosine theta, which is the same thing as cosine theta if cosine theta is positive, or in other words, if theta is between pi over 2 and negative pi over 2. For example, I would really like to replace my square root of 1 minus sine squared theta by just cosine theta, not the absolute value of cosine theta. So I'm just going to assume that theta is between negative pi over 2 and pi over 2 when I make my substitution. This might seem like cheating, but it's actually legit, because if you think about the unit circle, as theta ranges from negative pi over 2 to pi over 2, well, cosine's always positive like we want it to be, but sine is ranging all the way from -1 to 1, and so we can actually achieve all of the x values between -7 and 7 this way, which are the only x values in the domain of our function anyway. Now if we go back to our integral, we can actually replace the square root of 1 minus sine squared theta with a simple cosine theta. We've successfully gotten rid of this tricky square root sign, which is the whole point behind trig substitution. Now if we simplify, we just have to integrate 7 squared sine squared theta d theta. And this is a familiar problem that we can solve using another trig identity. Now we've got an integral we can compute. So the integral of 1/2 is 1/2 theta, and the integral of cosine of 2 theta is 1/2 sine of 2 theta. So let me add my constant of integration, and I'm almost done. Almost, but not quite. Because this answer is in terms of theta, and my original problem was in terms of x. Now I know that x and theta are related, according to this equation here. So if I solve for theta, I get sine theta is equal to x over 7, so theta is inverse sine or arcsine of x over 7. So I could just plug in for theta here and get 7 squared, that's 49 times 1/2 sine inverse x over 7 minus 1/2 times 1/2 is 1/4 sine of 2 times sine inverse x over 7 plus c. This is a correct answer, but it's very awkward looking. Sine of twice sine inverse x over 7, there's got to be a way to simplify this. Unfortunately, we can't just pull the 2 out and cancel the sine with the sine inverse because, well, sine doesn't work that way. But instead, we can use the double angle formula. So we can rewrite sine of 2 theta as twice sine theta cosine theta. So let me ignore this line for now, and I'll rewrite the above line as 49 times 1/2 theta minus 1/4 times twice sine theta cosine theta plus c. Now there's one more trick we need to use, and that trick is to draw a right triangle. I'm going to label the sides of that triangle using the equation for the substitution we made, or this equivalent form is a little easier to use. So since sine theta is x over 7, if I label one of my angles as theta, then the opposite side needs to have a measure of x, and the hypotenuse should have a measure of 7. You can check that by the Pythagorean theorem, that means that this bottom side needs to have a measure of the square root of 49 minus x squared. Notice that that's exactly the same expression that was in our original integrand. Once we have the triangle labeled, we can use it to find expressions for sine of theta and cosine of theta in terms of x. Sine of theta is opposite over hypotenuse, so that's x over 7. Well, we already knew that. But now cosine of theta is adjacent over hypotenuse, so that's the square root of 49 minus x squared over 7. We can use these two equations to substitute in for sine theta and cosine theta, and to get rid of this naked theta here, we'll still have to use the fact that theta is inverse sine of x over 7. Those substitutions lead us to this answer, and a little bit of simplification leads us to the same answer that Wolfram Alpha gave us. This was a complicated problem, but the key step was to use this trig substitution, and then that allowed us to use a trig identity in order to rewrite our square root and get rid of the square root. After that, it was a fairly routine integration problem until we got to the point where we had to substitute back in for theta. And then drawing the right triangle helped us figure out what to do. In this video, we used trig substitution to evaluate an integral with a square root in it. This video introduces the method of partial fractions as a way to integrate many rational functions. Recall that a rational function is a function of the form a polynomial divided by another polynomial. Let's work out the integral of 3x plus 2 divided by x squared plus 2x minus 3. According to Wolfram Alpha, the integral evaluates to this expression, involving the log of x minus 1 and the log of x plus 3. So what do x minus 1 and x plus 3 have to do with our original rational function? I challenge you to pause the video for a moment and try to figure this out. You might have noticed that the denominator, x squared plus 2x minus 3, factors into x minus 1 times x plus 3. Let's look at what happens if I take two separate fractions, one with denominator x minus 1 and one with denominator x plus 3, and add them up. The common denominator of these two fractions is x minus 1 times x plus 3. So when I add these fractions together using standard algebra, I should get a fraction with common denominator x minus 1 times x plus 3. Well, my original rational function was just such a fraction, so it seems plausible that I might be able to find numbers a and b so that these two partial fractions add up to this original fraction. Let's figure out what numbers a and b might make this work. To solve for a and b, I'm going to clear the denominator by multiplying both sides of my equation by this least common denominator, x minus 1, x plus 3. When I distribute on the left side, I get x plus 3 times a plus x minus 1 times b, and on the right side, my x minus 1 and x plus 3 cancel out to give me 3x plus 2. I'll distribute the left side a little further, and I'm going to group the terms that involve x and the terms that don't involve x. If I want this equation to hold true for all values of x, then I need the coefficients of x to be the same on the left and the right. So I need a plus b to equal 3. Similarly, I need the constant term to be the same on the left and the right. So I need 3a minus b to equal 2. I now have two linear equations in the two unknowns a and b, so I can use standard algebra to solve these equations for a and b. For example, if I add the two equations together, the b and negative b cancel out to give me 4a equals 5, and so a equals 5/4, and then I can substitute in this 5/4 into either one of my equations and solve for b. So I was able to find a value of a and b that let me rewrite the original fraction as two partial fractions. Let me fill those values of a and b in here. Now to calculate the integral of my original expression, I can calculate the integral of my partial fractions instead. I'm going to split up my integrals here. Now the integral of 1 over x minus 1 is natural log of absolute value of x minus 1. You can check this by taking the derivative, or you can do a simple u substitution, where u is x minus 1, to compute this integral. Similarly, the integral of 1 over x plus 3 is natural log of absolute value of x plus 3. This completes the computation of the integral using the method of partial fractions. Recall that after factoring our denominator, the key step in this process was finding numbers a and b that made this equation hold. And you might wonder, well, yeah, it worked this time, but can we always find numbers a and b that'll work like that? What if our numerator had been something different? What if our numerator had been instead something like, say, 7x minus 15? Could we have still found an a and b that worked? Well, yes, because we still would have gotten two linear equations in two unknowns down here, and we would have been able to solve them. We'd get different values of a and b, but we still would have been able to find a solution. Even if our numerator had just been a number, like 6, we still could have used the same method. We could have thought of this as 0x plus 6, and we could have used the same equations down here where a plus b would have to equal 0 and 3a minus b would have to equal 6. So we'd still have two equations and two unknowns to solve for. In fact, if you think about it for a while, you may be able to convince yourself that this method will always work if you have two conditions. First, the denominator factors into distinct linear factors. By a linear factor, I just mean that the factor can be written like a number times x plus another number with no x squareds or anything in it. And by distinct, I just mean that these two factors are different from each other. The second condition is that the degree of the numerator is lower than the degree of the denominator. This second condition guarantees that we'll have the same number of unknowns, here a and b, as we do coefficients, here 3 and 2, so that we'll have equations that we'll be able to solve for our unknowns. As a technical note, the distinctness of the linear factors guarantees that we won't have contradictory equations. If we have these two conditions, then we can proceed to integrate like we did in this example. In fact, this method even works if we have more than two linear factors in our denominator. We could have 3 or 4 or any number of distinct linear factors. It'll just get a little bit more complicated because we'll have more constants and more equations to solve for those constants. There are also several related methods that allow us to integrate rational functions, even if the denominator factors into linear factors that aren't necessarily distinct, or even if we can't get all the way down to linear factors and some of our factors have squares in them, or even if the degree of the numerator is too big. But I won't get into the details of those related methods in this video. You'll have to read about them in the book, or wait for class, or wait for a future video to find out more. In this video, we integrated a rational function by splitting up the fraction into two partial fractions. This video is about improper integrals, especially the first type, which I'll define in a moment. Two examples of improper integrals are the integral from 1 to infinity of 1 over x squared dx, and the integral from 0 to pi over 2 of tan x dx. What makes these integrals improper? Well, in the first example, it's this infinity in the bound of integration. And in the second example, it's the fact that the function tan of x itself goes to infinity on the interval from 0 to pi over 2 where we're integrating. So an integral is called improper if either of these two situations occur. It's called a type 1 improper integral if we're integrating over an infinite interval. In other words, there's an infinity or a negative infinity somewhere in the bounds of integration. So the first example is a type 1 improper integral. A type 2 improper integral occurs when the function that we're integrating itself has an infinite discontinuity on the interval. By an infinite discontinuity, I mean the function is going to infinity or negative infinity. This is also called a vertical asymptote. This vertical asymptote could occur in the interior of the interval we're integrating over, or, as in this example, it could occur on the endpoint of that interval of integration. Now, it's possible that both of these situations could occur for the same integral, and that's also an improper integral. This video will focus on type 1 improper integrals. A type 1 improper integral asks us to integrate over an infinite interval. To do this, we take the integral over larger and larger finite intervals and take the limit. So for example, to find the integral from 1 to infinity of 1 over x squared dx, we'll evaluate the integral from 1 to some finite number t, and then take the limit as t goes off to infinity. In symbols, we can write the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. Since 1 over x squared is the same thing as x to the minus 2, we can integrate it to get negative x to the minus 1 evaluated between 1 and t, and then take that limit. I'll rewrite this as negative 1 over x and evaluate on the bounds of integration. As t goes to infinity, 1 over t goes to 0. So the limit just comes from this expression, which evaluates to 1. If we think of the integral as representing area, this is a little surprising. Even though we're taking the area of an infinitely long region, the area still evaluates to a finite number of 1. In this situation, we say that the improper integral converges. So in general, the improper integral from some finite number a to infinity of f of x dx is defined as the limit as t goes to infinity of the integral from a to t of f of x dx. We say that the integral converges if this limit exists as a finite number, and we say that the integral diverges if the limit is infinity or negative infinity, or if it doesn't exist. Similarly, we evaluate the integral from negative infinity to some finite number by taking bigger and bigger intervals that extend off to negative infinity. That is, this integral is defined as the limit as the left endpoint t goes to negative infinity of the integral from t to b of f of x dx. We say that this integral converges if the limit exists as a finite number and diverges otherwise. So to evaluate the integral from negative infinity to negative 1 of 1 over x dx, we take the limit as t goes to negative infinity of the integral from t to negative 1 of 1 over x dx. Now the integral of 1 over x is ln of the absolute value of x, which we'll need to integrate between t and negative 1 and take a limit. If we evaluate here, we know that ln of the absolute value of negative 1, that's ln of 1, which is 0. A graph of ln is helpful for evaluating the rest of this expression. As t goes to negative infinity, the absolute value of t is going to infinity, and so ln is also going to infinity. Therefore, our limit is actually negative infinity, and so the integral diverges. In this video, we evaluated improper integrals in which the interval that we're integrating over is infinite by looking at the integrals over larger and larger finite intervals and taking a limit. This video is about type 2 improper integrals. These are integrals for which the interval that we're integrating over is finite, but the function that we're integrating goes to infinity on that interval. To integrate a type 2 improper integral, like this one or this one, we integrate our function over larger and larger subintervals on which the function is finite. And then we take a limit. So in this first picture, where the function approaches infinity as x goes to b from the left, we can call that moving endpoint t and evaluate the integral as the limit as that right endpoint t approaches b from the left of the integral from a to t of f of x dx. The same definition works if f of x is going to negative infinity instead of infinity. In the second picture here, we again want to take a limit of integrals over subintervals on which the function is finite. So in symbols, that says that if f goes to infinity or negative infinity as x goes to a from the positive side, then the integral from a to b of f of x dx is going to be the limit as t goes to a from the right of the integral from t to b of f of x dx. As an example, let's find the area under the curve y equals x over the square root of x squared minus 1 between the lines of x equals 1 and x equals 2. That area can be described as the integral from 1 to 2 of our function, but this is an improper integral because the function is going to infinity as x goes to 1 from the right. So we'll evaluate it by taking the limit as t goes to 1 from the right of the integral from t to 2 of the function. I'll compute this integral using u substitution, where u is x squared minus 1 and du is 2x dx. Since I see an x dx in my integrand here, I'll solve for x dx, and I get x dx is equal to 1/2 du. I'm also going to change my bounds of integration. When x is equal to t, that means u is equal to t squared minus 1, and when x is equal to 2, u is 2 squared minus 1, that's 3. So I'll rewrite my integral. X dx is the same thing as 1/2 du, and my square root of x squared minus 1 becomes a square root of u in the denominator. I'll rewrite again by pulling the 1/2 out of the integral and rewriting the square root of u in the denominator as u to the negative 1/2. Now I can integrate. I get 2 times u to the 1/2 evaluated between 3 and t squared minus 1. My 1/2 and 2 cancel, and I'll plug in my bounds of integration here. Now as t goes to 1 from the right, t squared is also going to 1, so t squared minus 1 is going to 0. Therefore, my limit is just 3 to the 1/2, or square root of 3, and that's the area underneath my curve. This video was about type 2 improper integrals and how to compute them as the limit of integrals over larger and larger subintervals on which the function is finite. Sometimes we don't really care what the value of an improper integral is. We just want to know whether it's finite or infinite, whether it converges or diverges. In this situation, the comparison theorem can be very handy. The comparison theorem can allow us to determine if an integral converges or diverges without actually having to evaluate the integral. Instead, by comparing it to the integral of a function that we know converges or diverges. So suppose that g of x and f of x are both positive valued functions. They're both greater than 0 for all x's on the interval ab. And let's suppose also that g of x is less than f of x on that interval ab. Here, a or b could be infinity or negative infinity. So in the picture, we'll call this blue function g of x and the orange function f of x. And let's consider the interval from 1 to infinity, where g of x is less than f of x, and both of them are bigger than 0. Now, if we already know that the integral of f of x on this interval converges to a finite number, then g of x, which is less than f of x, also has to converge to a finite number. So if the integral of f of x converges, then g of x converges. If we turn this around, we can say that if g of x diverges, so it doesn't converge to a finite number, then f of x has to diverge also. So in the situation where the integral of the bigger function converges, or the integral of the smaller function diverges, then we can make some conclusions about the integral of the other function. But you have to be a little careful about this, because if instead the integral of the bigger function diverges, then we really can't make any conclusions at all about the integral of the smaller function. It could also diverge, or it could be small enough to converge as an integral. Similarly, if the integral of the smaller function converges, then we really just don't know anything about the integral of the bigger function. It could converge or it could diverge. Let's look at an example. Suppose we want to find out if the integral from 2 to infinity of 2 plus sine x over square root of x dx converges or diverges. Instead of trying to evaluate it, which could get tricky because of the sine x and the square root of x in here, I'm going to just try to compare it to something that I know converges or diverges. The first thing that I notice is that sine of x is bounded. It's always between 1 and negative 1. And that means that the numerator, 2 plus sine x, is always going to be in between 3 and 1. Therefore, the function 2 plus sine x over square root of x is going to be between 3 over square root of x and 1 over square root of x. Here's the general idea of the picture. Now the comparison theorem tells us that if our function is less than a function whose integral converges, then the integral of our function will converge. And if our function is greater than a function whose integral diverges, then the integral of our function will diverge. So which one of these two inequalities we want to use depends on what happens to the integral of these functions on the ends. Now we know that the integral of 1 over the square root of x dx from 2 to infinity has to diverge. That's because this is a p function, where p is equal to 1/2, which is less than 1. The integral from 2 to infinity of 3 over the square root of x dx also diverges, since it's just 3 times the other integral. So if we want to compare our function to a function whose integral diverges, it had better be bigger than that divergent integral in order to get any useful information out of it. Being less than a function whose integral diverges doesn't tell us anything. So we need to focus on this inequality. And now we can say that since the integral from 2 to infinity of 1 over the square root of x dx diverges by the p-test, the integral of our function also diverges by the comparison test. In this video, we saw that if we have two positive functions and one function is always less than or equal to the other function on an interval, then if the smaller function's integral diverges, the bigger function's integral also has to diverge. And if the bigger function's integral converges, the smaller function's integral also has to converge. That's the comparison theorem. In this video, I'll give some definitions and notation for sequences. A sequence is a list of numbers in a particular order. The sequence 3, 1, 4, 1, 5, 9, and so on is a sequence that gives the digits of pi. A sequence is sometimes described abstractly with letters in place of numbers, a sub 1, a sub 2, a sub 3, and so on, or more concisely by writing a sub n with these curly brackets. Here we're told that the index n ranges from 1 all the way up towards infinity. Sometimes the sequence is written just a sub n with curly brackets. Here it's implied that n ranges through all positive integers. For these sequences, given by formulas, let's write out the first few terms. We start with n equals 1, and we get a sub 1 is 3 times 1 plus 1 over 1 plus 2 factorial. That is, 4 over 3 factorial. Recall that 3 factorial means that we start with 3 and then multiply with consecutive numbers all the way down to 1. This simplifies to 4/6 or 2/3. To find the next term, a sub 2, we plug in 2 for n. That's 7 over 4 factorial, which is 7/24. Similarly, a sub 3 is 10 over 5 factorial, which is 10 over 120, or 1/12. So the first 3 terms of the sequence are 2/3, 7/24, and 1/12. For the second example, we're asked to start with k equals 2. So I'll call the first term a sub 2 and just plug in 2 for k, which is 5/9, since -1 squared is positive 1. Plugging in k equals 3, we get -6/27, or -2/9. For a sub 4, we again get a positive number, since -1 to the 4th is positive, and in fact, as we keep writing down terms, they're going to alternate between negative numbers and positive numbers because of the -1 to the k in the definition. Sometimes, the nth term of a sequence is defined indirectly in terms of previous terms. This is called a recursive formula. To write out the first few terms of this recursive sequence, we're told that a sub 1 equals 2. To find a sub 2, we just use the recursive formula, 4 minus 1 over a sub 1. Since a sub 1 is 2, that's 4 minus a half, or 7/2. To find a sub 3, we just apply the recursive formula again, 4 minus 1 over 7/2 simplifies to 26/7. Sometimes it's possible to describe a sequence with either a recursive formula or a closed form non-recursive formula. For example, if I look at the sequence 2, 4, 6, 8, 10, I can describe that recursively by saying a sub 1 is 2, and each a sub n is equal to a sub n minus 1 plus 2. Or I can describe it as a closed form expression by saying this sequence is of the form 2 times n, where n starts at 1. Now let's practice writing out a formula for the general term a sub n of a sequence. For this first sequence, notice that each term is 3 more than the previous term. So this is like a linear function with slope 3. Each time that n goes up by 1, our a sub n's go up by 3. And so I can write a sub n is 3 times n plus b, where b functions like my y-intercept in a linear equation. To find b, I can plug in 7 for a sub 1. That corresponds to an n value of 1, and I get that b has to equal 4. So my general formula is 3 times n plus 4, where n starts at 1. I can check this by plugging in a few values of n, like we did in the previous example, just to make sure it works. Notice that it would also be possible to write this as 3 times n plus 7 if we're willing to start with n equals 0 instead of 1. If we let n start with 0, then our first term functions like our y-intercept. This is an example of an arithmetic sequence, a sequence for which consecutive terms have the same common difference. And in general, if a is the first term and d is the common difference, then an arithmetic sequence has the form d times k plus a if our index is k and starts at 0, like it did over here, or if we'd rather start with an index of 1, we can rewrite that as d times n minus 1 plus a. Notice these two expressions are exactly the same if we just set k equal to n minus 1. In particular, the starting value of n equals 1 here, if I plug in 1 for n, I get the equivalent starting value of k to be 0. Let's write some more formulas for sequences. In this first sequence, notice that consecutive terms always have the same ratio of 1/10. In other words, each time n increases by 1, a sub n gets multiplied by 1/10. This is the same property that exponential functions have, and in fact, we can write a sub n in the form of an exponential function with base 1/10, but we need to multiply by the right initial value so that when n is 1, we'll get a first term of 3. That correct initial value is 30. As usual, we can check our answer by plugging in a few values of n equals 1, 2, 3, and making sure we get back the terms in our sequence. If we prefer to start with our index at 0, we can rewrite this as 3 times 1/10 to the nth power. Since a value of 0 for n in this formula gives us 3, just like a value of 1 for n in this formula gives us 3. In this second example, we again have a common ratio. If I divide the second term by the first term, I get a ratio of 5/2, and that's the same ratio as I get when I divide the third term by the second term. So if I use an index starting with 0, I can write this series as 15/2, which is the first term, times 5/2 to the n power. If I prefer to start with my index at 1, one way to do this is to let k equal n plus 1. And making a variable substitution, when n is 0, k will be 1. And since k is n plus 1, n is k minus 1, so I can replace n with k minus 1. This gives the following representation of the sequence. The third example has a common ratio of -2/3. So we can write it as the initial term of 3 times that ratio, -2/3, raised to the nth power, where n starts at 0. Or, as above, we can write it as 3 times -2/3 to the k minus 1, where k starts at 1. Sometimes people like to write the -1 separately. The -1 to the power makes the series alternate between negatives and positive terms. These three sequences are all examples of geometric sequences, which are sequences where consecutive terms have the same common ratio. And in general, if a is the first term and r is the common ratio, then a geometric sequence can be written in the form of a times r to the n, where n starts at 0, or as a times r to the n minus 1, where n starts at 1. These next two sequences are neither arithmetic sequences nor geometric sequences, since their terms neither have common differences nor common ratios. But I can still figure out a formula for the nth term just by looking for the pattern. In this example, since the terms are alternating, if I start at n equals 1, I know that I need a -1 to the nth power to make it start with a negative and then alternate positive, negative again. The numerator looks like it's just twice n, and the denominator looks like it's always a perfect square, starting with the square of 3, so I'll write that as n plus 2 squared. The next sequence doesn't have a simple closed-form formula, but I can describe it recursively by saying that a1 is -6, a2 is 5, and in general, an is equal to the sum of the two previous terms, a sub n minus 1 plus a sub n minus 2. This sequence is closely related to the standard Fibonacci sequence, which has the same recursive formula, but different initial values. This video gave an introduction to sequences, including arithmetic sequences, geometric sequences, and recursively defined sequences. This video introduces the idea of a series and how to find its sum. For any sequence, a sub n, for n equals 1 to infinity, the sum of its terms, a sub 1 plus a sub 2 plus a sub 3 and so on, is called a series. Often this series is written in sigma notation as the sum from n equals 1 to infinity of a sub n. Let's look at the sequence 1 over 2 to the n for n equals 1 to infinity. If we add together all the terms, we get the series, the sum from n equals 1 to infinity of 1 over 2 to the n. That is, the sum of 1 over 2 to the 1, that's 1/2, plus 1 over 2 squared, that's 1/4, plus 1 over 2 cubed, 1/8, plus 1/16, plus 1/32, and so on. But what does it really mean to add up infinitely many numbers? How can we figure out what this infinite sum equals? Well, to start out, we could add up finitely many at a time. Let me write down the first half dozen or so terms, that is the a sub n's, and I'll keep adding more and more of them together, one more at a time. If I just add the first term, well, that's just 1/2. Now I'll add the next term on. That gives me a sum of 3/4. If I add 1/8 to that, my sum goes up to 7/8. And then I'll add the next one. I get 15/16, and so on, just adding one more term each time. This process of repeated addition gives me a new sequence down at the bottom that's called the sequence of partial sums. And it's usually denoted by s sub n. So the first term in the sequence of partial sums is s sub 1, just adding together the first term. Here's the second partial sum, s sub 2, adding together the first two terms. S sub 3 means add together the first three terms, and so on. Let me contrast the sequence of partial sums with the sequence of terms that we started out with. Those are denoted a sub n, so here's a sub 1, the first term, a sub 2, the second term, and so on. Although I can't physically add up infinitely many numbers, I can observe that as I add up more and more numbers, my partial sums are approaching the number 1. That is, the limit, as the number of terms I add up, n goes to infinity, of the nth partial sum is equal to 1. So it makes sense that if I could add up all infinitely many numbers, I should get an exact sum of 1. The sum of this infinite series is 1. In fact, for this particular series, there's a nice way to see that the sum is 1 using geometry. If I draw a square with side length 1 and fill in half of the square, that gives me an area of 1/2. Now if I draw a line here, that gives me an additional area of 1/4. Here's an area of 1/8, 1/16, and if I keep spiraling in here, I keep adding areas that exactly match the terms of this series. In the limit, I'll have filled in the entire square, which has an area of 1. In this example, we found the sum of the series by evaluating the limit of the partial sums. And in general, this is how we find the sum of any series. For any series, the partial sums of the series are defined as the sequence s sub n, where s sub 1 is equal to just the first term a sub 1, s sub 2 is equal to the sum of the first two terms, a sub 1 plus a sub 2, s sub 3 is the sum of the first three terms, and in general, s sub n is the sum of the first n terms. I can also write this in sigma notation as the sum of, say, k equals 1 to n of a sub k. I'm using a different letter k here as the index just because I'm already using n to represent the number of terms that I'm adding up. The sum of a sub n is said to converge if this sequence of partial sums converges as a sequence. That is, if the limit as n goes to infinity of the s sub n's exists as a finite number. Otherwise, if the limit does not exist, or the limit is infinity or negative infinity, then the series is said to diverge. I want to emphasize that we're talking about the limit of the partial sums here, not the limit of the original terms a sub n. And it's important to keep in mind when you're working with series that for any series there are actually two sequences of interest. There's the sequence of terms, the a sub n's, and then there's the sequence of partial sums, the s sub n's. It's the sequence of partial sums that's telling us what the sum of our series is. So if the sequence of partial sums converges to a number L, then we say the series converges to L, or in other words, the sum of the series is L. Let's look at the series, the sum of 1 over n squared plus n. Please pause the video and take a moment to write out the first four terms and the first four partial sums. The first four terms are a sub 1, a sub 2, a sub 3, and a sub 4. So plugging in 1 for n, 1 over 1 squared plus 1, so that's 1/2. A sub 2 is 1 over 2 squared plus 2, so that's 1/6. A sub 3 ends up being 1/12, and a sub 4 is 1/20. Now, s sub 1 is the sum of the first one terms. That's the same as a sub 1. It's just 1/2. S sub 2 is what I get when I add 1/2 plus 1/6. That's 4/6 or 2/3. To get s sub 3, I need to add on the next term. 2/3 plus 1/12 is 9/12 or 3/4. And finally, s sub 4, I need to add on the next term, which gives me 4/5. There's a nice pattern going on with the s sub n's here. For the nth partial sum, the numerator is just n, and the denominator is just n plus 1. So the limit as n goes to infinity of the partial sums is the limit as n goes to infinity of n over n plus 1, which is just 1. That means that the sum of the infinite series is equal to 1. By coincidence, the same sum as in the previous example. In this video, we saw that to find the sum of an infinite series, we have to calculate the partial sums. If we add together more and more finitely many terms, our partial sum will get close to our infinite sum. And in fact, the sum of our infinite sum is defined as the limit as n goes to infinity of the partial sum. This video gives some more definitions about sequences, including the definition of bounded and the definition of monotonic. A sequence is bounded above if all of its terms are less than or equal to some number. In other words, there's a number, capital M, such that the term a sub n is less than or equal to capital M for all values of the index n. A sequence is bounded below if all of its terms are greater than or equal to some number. In other words, there's a number, lowercase m, such that a sub n is greater than or equal to lowercase m for all n. We say that a sequence is bounded if it's bounded both above and below. In other words, all of its terms are trapped between two numbers. Please pause the video and decide which of these three sequences are bounded. This first sequence is bounded above by 3, since all of its terms are less than or equal to 3. Of course, we could have also used 4 as an upper bound or 100 as an upper bound, but 3 is the tightest upper bound that we can use. It's also bounded below by 0, since all of the terms are positive. So we say that this sequence is bounded. The second sequence is bounded below by 1, but it's not bounded above, since its terms will eventually grow past any potential bound. The third sequence is bounded below and above. In fact, if we graph n on the x-axis and a sub n on the y-axis, then our terms bounce around between positive and negative values. But since we're always multiplying by negative 2/3 to get from one term to the next, the oscillations are dying down in magnitude, and in fact, the terms can never get above 3 or below negative 2. We say that a sequence is increasing if each term is less than the next term. That is, a sub n is less than a sub n plus 1 for all n. A sequence is called non-decreasing if each term is less than or equal to the next term. So a sub n is less than or equal to a sub n plus 1 for all n. Non-decreasing is like increasing, it's just we allow equality between two consecutive terms. A sequence is decreasing if each term is greater than the next one. So a sub n is greater than a sub n plus 1 for all n. And a sequence is not increasing if a sub n is greater than or equal to a sub n plus 1 for all n. Again, non-increasing is like decreasing, but we allow for equality between consecutive terms. If we were to graph n on the x-axis and a sub n on the y-axis, then increasing looks like this, just like an increasing function, whereas decreasing would go down, non-decreasing would go up, possibly with some flat patches, and non-increasing would go down, possibly with some flat patches. Notice that increasing is a stronger condition than non-decreasing, since being strictly less than something is stronger than just being less than or equal to it. For that reason, if a sequence is increasing, it is also non-decreasing. And similarly, if a sequence is decreasing, it is also non-increasing. A sequence is called monotonic if it is either non-decreasing or non-increasing. Please pause the video and try to decide which of the following sequences are monotonic. The first two sequences are monotonic. The first one is monotonically non-increasing, since we never increase when we go from one term to the next. In fact, we could also say that it's monotonically decreasing, since we always go strictly down as we go from one term to the next. We never have equality between terms. The second sequence is monotonically non-decreasing. Since we never go down as we go from one term to the next, we either go up or stay at the same level. In this case, however, we could not say that this sequence is monotonically increasing because of the equality between some pairs of consecutive terms. The third sequence is not monotonic. The numbers bounce around between positive and negative numbers, and therefore sometimes we are decreasing while other times we're increasing. And the fourth sequence is not monotonic because of the first few terms. However, from the fifth term on, the terms are monotonically non-decreasing, and we could also say monotonically increasing. In this video, we gave definitions for bounded and monotonic sequences. We'll see later that these definitions can be important for determining when a sequence converges. In class, we talked briefly about this sequence, n minus 5 over n squared, where n goes from 1 to infinity. We wanted to know if this sequence is monotonic and if it's bounded. If we compute the first few terms, the sequence appears to be steadily increasing. But in this case, appearances are deceiving. And a better way to decide whether it's monotonic is to use calculus to decide if the associated function, f of x equals x minus 5 over x squared, is increasing for x values bigger than 1. So let me take the derivative using the quotient rule and simplify. I get that f prime of x is equal to minus x squared plus 10x over x to the fourth. And now I need to decide, is f prime of x greater than 0 for x bigger than 1? If so, my function, and therefore my sequence, will be increasing. To check if f prime of x is greater than 0, I'll first set f prime of x equal to 0. So I'll set my ratio here equal to 0, which means my numerator needs to be equal to 0. And if I factor that, I get that x equals 0 or x equals 10. Now if I draw my number line, since f prime is equal to 0 at 0 and 10, it'll be positive and negative in between these values, and by plugging in values like x equals negative 1, 1, and 11, I can see that f prime is negative for x less than 0, positive for x between 0 and 10, and negative for x bigger than 10. In particular, f increases when x increases from 1 to 10, and then it decreases. And so the same thing is happening to our sequence. Therefore, the sequence is not monotonic. We can also use calculus to check if the sequence is bounded. Our first derivative test shows that our function f of x has a maximum at x equals 10. At least, that's the maximum for x values ranging from 1 to infinity, and that's all that's relevant for our sequence. Therefore, our sequence is bounded above by its value at 10, which is 10 minus 5 over 10 squared, or 1/20th. Now notice that our sequence n minus 5 over n squared is always bigger than 0 for n bigger than 5, since the numerator and denominator are both positive in this situation. And since there are only finitely many terms where n is less than 5, we can just use the minimum of these terms and 0 as a lower bound. The smallest of the first 4 terms is negative 4, which is less than 0, so that negative 4 forms a lower bound. So this sequence is, in fact, bounded. And somewhat surprisingly, the calculus ideas of derivative and maximum and minimum come in handy. In the past, we've encountered limits like the limit as x goes to 2 of x minus 2 over x squared minus 4. We can't evaluate this limit just by plugging in 2 for x, because x minus 2 goes to 0 and x squared minus 4 goes to 0 as x goes to 2. This is known as a 0 over 0 indeterminate form. It's called indeterminate because we can't tell what the limit's going to be just by the fact that the numerator goes to 0 and the denominator goes to 0. It depends on how fast the numerator and the denominator are going to 0 compared to each other. And the final limit of the quotient could be any number at all, or it could be infinity, or it could not even exist. In the past, we've been able to evaluate some limits in 0 over 0 indeterminate form by using algebraic tricks to rewrite the quotients. In this video, we'll introduce L'Hopital's rule, which is a very powerful technique for evaluating limits in indeterminate forms. A limit of the form the limit as x goes to a of f of x over g of x is called a 0 over 0 indeterminate form if the limit as x goes to a of f of x is equal to 0 and the limit as x goes to a of g of x is equal to 0. A limit in this form is called an infinity over infinity indeterminate form if the limit as x goes to a of f of x is equal to infinity or minus infinity, and the limit as x goes to a of g of x is equal to infinity or minus infinity. We saw an example of a 0 over 0 indeterminate form in the introductory slide. One example of an infinity over infinity indeterminate form is the limit as x goes to infinity of 3x squared minus 2x plus 7 divided by negative 2x squared plus 16. Notice that as x goes to infinity, the numerator goes to infinity while the denominator goes to negative infinity. In these definitions of indeterminate form, it's possible for a to be a negative infinity or infinity like it is in this example, but it doesn't have to be. L'Hopital's rule can be applied when f and g are differentiable functions and the derivative of g is non-zero in some open interval around a, except possibly at a. Under these conditions, if the limit as x goes to a of f of x over g of x is a 0 over 0 or infinity over infinity indeterminate form, then the limit as x goes to a of f of x over g of x is the same thing as the limit as x goes to a of f prime of x over g prime of x, provided that this second limit exists, or is plus or minus infinity. Let's look at L'Hopital's rule in action. In this example, as x goes to infinity, the numerator x goes to infinity, and the denominator 3 to the x also goes to infinity. So we have an infinity over infinity indeterminate form. So let's try applying L'Hopital's rule. Our original limit should equal the limit as x goes to infinity of the derivative of the numerator, which is 1, divided by the derivative of the denominator, which is ln of 3 times 3 to the x, provided that this second limit exists or is infinity or negative infinity. In the second limit, the numerator is just fixed at 1, and the denominator goes to infinity as x goes to infinity. Therefore, the second limit is just 0, and so the original limit evaluates to 0 as well. In this example, we have a 0 over 0 indeterminate form, because as x goes to 0, sine of x and x both go to 0 in the numerator, and sine of x cubed goes to 0 in the denominator. So using L'Hopital's rule, I'll try to evaluate instead the limit I get by taking the derivative of the numerator and the derivative of the denominator. The derivative of sine x minus x is cosine of x minus 1, and the derivative of sine x cubed is 3 times sine x squared times cosine x, using the chain rule. Now let me try to evaluate the limit again. As x goes to 0, cosine of x goes to 1, so the numerator here goes to 0. As x goes to 0, sine of x goes to 0, and cosine of x goes to 1, so the denominator also goes to 0. So I still have a 0 over 0 indeterminate form. And I might as well try applying L'Hopital's rule again. But before I do, I want to point out that cosine of x is going to 1. So the cosine of x here really isn't affecting my limit. And in fact, I could rewrite my limit of a product as a product of limits, where the second limit is just 1 and can be ignored from here on out. Now I'll apply L'Hopital's rule on this first limit, which is a little bit easier to take the derivatives in. So the derivative of the top is minus sine x, and the derivative of the bottom is 6 times sine x times cosine x. Now let's try to evaluate again. As x goes to 0, our numerator is going to 0, and our denominator is also going to 0. But hang on, we don't have to apply L'Hopital's rule again because we can actually just simplify our expression. The sine x on the top cancels with the sine x on the bottom, and we can just rewrite our limit as the limit of negative 1 over 6 cosine of x, which evaluates easily to negative 1/6. In this example, I want to emphasize that it's a good idea to simplify after each application of L'Hopital's rule. If you don't simplify, like we did here, then you might be tempted to apply L'Hopital's rule an additional time when you don't need to, which might make the problem more complicated instead of simpler to solve. In this video, we were able to evaluate 0 over 0 and infinity over infinity indeterminate forms by replacing the limit of f of x over g of x with the limit of f prime of x over g prime of x, provided that second limit exists. This trick is known as L'Hopital's rule. We've seen that L'Hopital's rule can be used to evaluate limits of the form 0 over 0 or infinity over infinity. In this video, we'll continue to use L'Hopital's rule to evaluate additional indeterminate forms, like 0 times infinity, infinity to the 0, 0 to the 0, and 1 to the infinity. In this example, we want to evaluate the limit of a product. Notice that as x goes to 0 from the positive side, sine x goes to 0, and ln x goes to negative infinity. Remember the graph of y equals ln x. So this is actually a 0 times infinity indeterminate form. Even though the second factor is going to negative infinity, we still call it a 0 times infinity indeterminate form. You can think of the infinity here as standing for either positive or negative infinity. It's indeterminate because as x goes to 0, the sine x factor is pulling the product towards 0, while the ln x factor is pulling the product towards large negative numbers. And it's hard to predict what the limit of the product will actually be. But the great thing is, I can actually rewrite this product to look like an infinity over infinity indeterminate form, or a 0 over 0 indeterminate form. Instead of sine x times ln x, I can rewrite the limit as ln x divided by 1 over sine x. Now as x goes to 0, my numerator is going to negative infinity, and since sine x is going to 0 through positive numbers, my denominator, 1 over sine x, is going to positive infinity. So I have an infinity over infinity indeterminate form. Now I could instead choose to leave the sine x in the numerator and instead put a 1 over ln x in the denominator. If I do this, then as x goes to 0 through positive numbers, sine x goes to 0, and since ln x goes to negative infinity, 1 over ln x goes to 0. And so I have a 0 over 0 indeterminate form. Sometimes it can be difficult to decide which of these two ways to rewrite a product as a quotient. One rule of thumb is to take the version that makes it easier to take the derivative of the numerator and denominator. Another trick is just to try one of the ways, and if you get stuck, go back and try the other. I'm going to use the first method of rewriting it because I recognize that 1 over sine x can be written as cosecant of x, and I know how to take the derivative of cosecant x. Using L'Hopital's rule on this infinity over infinity indeterminate form, I can rewrite my limit as the limit of what I get when I take the derivative of the numerator, that's 1 over x, divided by the derivative of the denominator, that's negative cosecant x cotangent x. As always, I want to simplify my expression before going any further. I can rewrite my trig functions in the denominator in terms of sine and cosine. Cosecant x is 1 over sine x, and cotangent x is cosine of x over sine of x. Now, flipping and multiplying, I get the limit as x goes to 0 plus of 1 over x times sine squared of x over negative cosine of x. In other words, the limit of negative sine squared x over x cosine x. We know that cosine of x goes to 1 as x goes to 0, so I can rewrite this as the limit of negative sine squared x over x times the limit of something that goes to 1. So I once again have a 0 over 0 indeterminate form, and I can apply L'Hopital's rule yet again. Taking the derivative of the top, I get negative 2 sine x cosine of x, and the derivative of the bottom is just 1. Now I'm in a good position just to evaluate the limit by plugging in 0 for x. In the numerator, I get negative 2 times 0 times 1. The denominator is just 1, so my final limit is 0. In this limit, we have a battle of forces. As x is going to infinity, 1 over x is going to 0. So 1 plus 1 over x is going to 1. But the exponent, x, is going to infinity. It's hard to tell what's going to happen here. If we had 1 to any finite number, that would be 1. But anything slightly bigger than 1, as we raise it to bigger and bigger powers, we would expect to get infinity. So our limit has an indeterminate form. It's hard to tell whether the answer is going to be 1, infinity, or maybe something in between. Whenever I see an expression with a variable in the base and a variable in the exponent, I'm tempted to use logarithms. If we set y equal to 1 plus 1 over x to the x, then if I take the natural log of both sides, I can use my log rules to rewrite that by multiplying by x in the front. Now, if I wanted to take the limit as x goes to infinity of ln y, that would be the limit of this product, x times ln 1 plus 1 over x. As x goes to infinity, the first factor, x, goes to infinity. 1 plus 1 over x goes to just 1, and ln 1 is going to 0. So we have infinity times 0 indeterminate form, which we can try to rewrite as an infinity over infinity or a 0 over 0 indeterminate form. Let's rewrite this as the limit of ln 1 plus 1 over x divided by 1 over x. This is indeed a 0 over 0 indeterminate form, so we can use L'Hopital's rule and take the derivative of the top and the bottom. The derivative of the top is 1 over 1 plus 1 over x times the derivative of the inside, which would be negative 1 over x squared. And the derivative on the bottom, the derivative of 1 over x, is negative 1 over x squared. We can actually cancel out these two factors and rewrite our limit as the limit as x goes to infinity of 1 over 1 plus 1 over x, which is just equal to 1, since 1 over x is going to 0. So we found that the limit of ln y is equal to 1, but we're really interested in finding the limit of y, which we can think of as e to the ln y. Since ln y is going to 1, e to the ln y must be going to e to the 1. In other words, e. So we found that our original limit is equal to e. And in fact, you may recognize that this limit is one of the ways of defining e. In the previous example, we had a 1 to the infinity indeterminate form, and we took logs and used log rules to write that as an infinity times 0 indeterminate form. Well, the same thing can be done if we have an infinity to the 0 indeterminate form or a 0 to the 0 indeterminate form. So 1 to the infinity, infinity to the 0, and 0 to the 0 are all indeterminate forms that can be handled using L'Hopital's rule. In this video, we saw that a 0 times infinity indeterminate form could be converted to a 0 over 0 or infinity over infinity indeterminate form by rewriting f of x times g of x as f of x divided by 1 over g of x, or as g of x divided by 1 over f of x. We also saw how to use L'Hopital's rule on these three sorts of indeterminate forms by taking the ln of y, where y is our f of x to the g of x that we want to take the limit of. This video gives some tricks for deciding whether a sequence converges. We say that a sequence a sub n converges if the limit, as n goes to infinity, of the terms a sub n exists as a finite number. Otherwise, we say the sequence diverges. In other words, a sequence diverges if the limit is infinity or negative infinity or does not exist. More formally, we said the limit as n goes to infinity of a sub n equals L if for any small number epsilon there's a number capital N such that when the index little n is bigger than or equal to capital N, a sub n is within distance epsilon of L. Saying that a sub n is within distance epsilon of L is the same thing as saying that the absolute value of a sub n minus L is less than epsilon. Let me draw this as a picture. If we put n on the x-axis and a sub n on the y-axis, we can plot our terms a sub n like this. Here it looks like our a sub n's are settling at a particular value. I'll draw the value on the y-axis and call it L. We say that the limit of a sub n is equal to L because for any tiny number epsilon, here I've tried to draw a distance epsilon above L and a distance epsilon below L, we can trap our a sub n's within epsilon of L by requiring the index n to be big enough. For the epsilon I've chosen here, our a sub n's are trapped within epsilon of L when little n is bigger than or equal to 3. So there is that big number n, which is here like 2 or 3, such that when little n is bigger than that, the a sub n's are always trapped within epsilon of L. And if I'd chosen a tinier epsilon, I would just have to go a little bit farther out to make sure that my sequence was trapped within epsilon of L. This is the epsilon definition of a limit. Formally, we say that the limit as n goes to infinity of a sub n is infinity if, for any big number, omega, there's a number capital N such that a sub n is bigger than capital N for little n bigger than or equal to capital N. In other words, no matter how big an omega I originally pick, my terms a sub n are eventually trapped above omega. Let me draw a picture for this one too. My terms here again are drawn in red, and now if I pick a certain height omega, eventually all my terms will be above omega. And if I pick a different, bigger value of omega, my terms will still eventually be bigger than omega. I might just need to go further out in my sequence. For this first value of omega, I would just need to pick a capital N of about 1, 2, 3, 4, 5, 6 Once my little n's are all bigger than 6, my a sub n's are bigger than that omega. And for this bigger value of omega, I need to pick a value of capital N of about 9. Once my little n's are bigger than about 9, all my a sub n's would be bigger than this omega. There's a similar definition for the limit as n goes to infinity of a sub n equaling negative infinity. Now we just need to say that for any big negative number, omega, there's a number n such that a sub n is less than omega for little n bigger than or equal to capital N. Please take a moment and try to come up with an example of a sequence that converges, a sequence that diverges to infinity or negative infinity, and a sequence that's bounded but still diverges. One example of a convergent sequence is the sequence 1 over n. This sequence converges to 0 since the limit as n goes to infinity of 1 over n is 0. A divergent sequence is 2 to the n, since the limit as n goes to infinity of 2 to the n is infinity. One example of a sequence that's bounded but still diverges is negative 1 to the n. This sequence alternates between negative 1 and 1, depending on whether n is odd or even. So it's bounded in between negative 1 and 1, but it still diverges because the limit does not exist, since the sequence doesn't settle at a single value. The rest of this video will give some techniques for proving that sequences converge. The first technique is to use standard calculus tricks for finding limits of functions. Even though a sequence is only defined on positive integers, sometimes it's possible to find a function defined on all positive real numbers that agrees with our sequence on the integers. In other words, the terms a sub n are equal to f of n for this function f. When this happens, then if the limit as x goes to infinity of f of x equals L, then the limit as n goes to infinity of a sub n also equals L. The red dots are converging to the same limit as the blue function. So a lot of times we can figure out if a sequence converges by replacing the terms a sub n with f of x for some appropriate function, and then using L'Hopital's rule or other tricks from Calculus 1 to show that the function's limit exists. Let's try that for the following example. When the indices are missing, as in this example, we'll assume that n starts at 1 and goes to infinity. In order to prove that this sequence converges, let's instead look at the function f of x equals ln 1 plus 2e to the x over x, where x is a real number. Now let's look at the limit as x goes to infinity of f of x. That's the limit as x goes to infinity of ln 1 plus 2e to the x over x. And as x goes to infinity, e to the x goes to infinity, so 1 plus 2 times e to the x goes to infinity, which means ln of that goes to infinity. So the numerator is going to infinity as x goes to infinity, and so is the denominator. We have an infinity over an infinity indeterminate form. So we can apply L'Hopital's rule and take the derivative of the numerator over the derivative of the denominator. The derivative of the numerator is 1 over 1 plus 2 times e to the x times 2 times e to the x using the chain rule, and the derivative of the denominator is just 1. We can take derivatives here because we're thinking of x as a real number, not just an integer. Simplifying, we still have an infinity over infinity indeterminate form, so let's take the derivatives again. The derivative of the numerator is now 2 times e to the x, and the derivative of the denominator is also 2 times e to the x, so our limit here is 1. Since our function converges to 1, our sequence also converges to 1. So this original sequence converges to 1. Another technique for proving that sequences converge is to use the squeeze theorem and trap the sequence between two simpler sequences that converge to the same limit. In this example, since sine and cosine are both bounded in between 1 and -1, we know that cosine of n plus sine of n can't be any bigger than 2, certainly, or any smaller than -2. If I divide all sides of this inequality by n to the 2/3, we can see that the original sequence is bounded in between -2 over n to the 2/3 and 2 over n to the 2/3. Notice that n to the 2/3 has to be positive, since as usual we're assuming that n starts as 1 and goes to infinity, and so dividing by n to the 2/3 does not switch the inequality signs. Now it's easy to check that the limit as n goes to infinity of -2 over n to the 2/3 is 0, since as n goes to infinity, n to the 2/3 also goes to infinity. Similarly, the limit as n goes to infinity of 2 over n to the 2/3 is 0. Since these two limits are the same, we know by the squeeze theorem that the limit of our sequence in the middle has to exist and equal 0 also. It's a remarkable fact that I won't prove here that if a sub n is bounded and monotonic, then it has to converge. You might get some intuition for this fact by looking at a graph. If the a sub n's are monotonically increasing, for example, but are bounded, then there's no place for the a sub n's to go. And they can't oscillate up and down because they're monotonically increasing. So it makes intuitive sense that they have to settle on some limit. A fun example of this fact is a sequence that starts 0.1, 0.12, 0.123, 0.1234, and so on, where we just keep stringing together the counting numbers as our decimal. This sequence is certainly monotonically increasing, and it's bounded since every term of the sequence is greater than 0 and less than, say, 0.5. So we have a bounded monotonic sequence, and so this sequence has to converge. Now, what it actually converges to is a little mysterious, since it doesn't converge to some number we're already familiar with, like 0.6 or pi over 3 or something like that. But it does converge to some real number, and that real number is called Champernowne's constant. And it has some interesting properties, and of course it has a decimal expansion that's easy to come up with, since you get it just by stringing together the counting numbers. If you can recognize a sequence to be a geometric sequence, then it's pretty easy to decide whether it converges or diverges. Recall that a geometric sequence is a sequence of the form a times r to the n minus 1, where n runs from 1 to infinity, or sometimes it's written as a times r to the n, where n runs from 0 to infinity. Let's try to figure out for what values of r the sequence r to the n converges. It's not very important here whether n starts at 0 or starts at 1, since when we talk about convergence, we're talking about the behavior of the terms as n goes to infinity. So the first few terms really don't matter. If r is greater than 1, then the sequence r to the n is an increasing sequence. In fact, for the sequence r to the n, if we replace n with x and look at the function f of x equals r to the x, that's an exponential function. And if we're assuming r is greater than 1, the base for our exponential functions is greater than 1. So we know that the limit as x goes to infinity of r to the x is infinity, which means that our sequence r to the n also has to diverge to infinity. If instead r is equal to 1, then r to the n is just 1 to the n, which is just a sequence of 1s, so that converges to 1. If r is between 0 and 1, then r to the n is decreasing. This time, it's like the exponential function f of x equals r to the x with the base between 0 and 1. And so the limit of that exponential function as x goes to infinity is going to be equal 0. Therefore, the sequence also converges to 0. Of course, if r equals exactly 0, then the sequence is just a sequence of zeros, so it also converges to 0. Next, let's look at the case when r is between -1 and 0. Now, the sequence of r to the n's are going to oscillate between positive and negative numbers that get smaller and smaller in magnitude as n goes to infinity. That's because we get from one number to the next by multiplying by r, which is a negative number of magnitude less than 1. So our limit as n goes to infinity of our a to the n's is going to be 0 again. Another way of thinking about this case is by thinking about the squeeze theorem. Since r to the n is always less than or equal to the absolute value of r to the n, and it's always greater than or equal to negative the absolute value of r to the n. Technically, r to the n is always exactly equal to the absolute value of r to the n when n is even, so that r to the n is positive, and it's always exactly equal to the negative of the absolute value of r to the n when n is odd, so that r to the n is negative. But in any case, the inequality still does technically hold, and so therefore, since by the squeeze theorem, the limit of the left terms is 0, and the limit of the right terms is 0, as we noted before, the limit of the middle term also has to be 0. So our sequence converges to 0. Now if r is equal to -1, then our sequence r to the n is just -1 to the n, which alternates between -1 and 1. And so that sequence diverges. Finally, if r is less than -1, then to get from one term to the next, we're multiplying by a negative number that has magnitude bigger than 1, and so our terms are going to oscillate between positive and negative numbers, but they're going to be going up in magnitude. And so the limit as n goes to infinity of a sub n does not exist, and we see that our sequence diverges. If we look through all these cases, we see that the sequence r to the n converges to 0 when r is between -1 and 1. It converges to 1 when r is exactly equal to 1, and it diverges when r is bigger than 1 or less than -1. I'll write that summary below. In fact, almost the same thing is true when we look at the sequence a times r to the n, where a is any real number. The sequence a times r to the n converges to 0 when r is between -1 and 1. It converges to a when r is equal to 1, and it diverges when r is less than -1 or greater than 1. This follows because multiplying all the terms in the sequence by a just multiplies the limit by a. And 0 times a is 0, while 1 times a is a. So anytime you encounter a geometric sequence, that is a sequence that can be written in the form of a times r to the n, you can know that it converges if r is bigger than -1 and less than or equal to 1. This sequence here, although it looks really complicated, it's really a geometric sequence in disguise. One way to see this is by simplifying the form of the terms. This is -1 to the t, e to the t times e to the -1 over 3 to the t times 3 squared. Now this is the same thing as -e over 3 to the t times 1 over 3 squared times e. Now this is looking like the tail end of a geometric sequence where a is 1 over 3 squared times e, and r, the common ratio, is minus e over 3. I say the tail end because we have t starting at 3 instead of at 0. Now since e is less than 3, the magnitude of r is got to be smaller than 1. In other words, r is a negative number that's between -1 and 0, and therefore the tail end of this geometric sequence converges. It's kind of interesting to note that we could also rewrite this geometric sequence if we wanted to, using an index n going from 0 to infinity. And one way to figure out how to do that, the r, the common ratio, stays the same as -e over 3. But since this version starts at t equals 3, the first term here is really minus e over 3 cubed times 1 over 3 squared e. And that becomes our value of a. Notice that when n is 0 here, I get this value, and when t is 3 here, I get the same value for this sequence. So these sequences are equivalent. But in any case, for either sequence, the common ratio r is -e over 3, and the sequence converges, therefore. The final trick that I want to mention for deciding whether sequences converge or diverge is limit laws. The usual limit laws about addition, subtraction, and so on hold for sequences as well as for functions. So, for example, if the limit as n goes to infinity of a sub n is L, and the limit of b sub n is m, then the limit of the sum a sub n plus b sub n is going to be equal to L plus m. And the limit of a sub n times b sub n is L times m, and the limit of c times a sub n, where c is some constant, is going to be c times L. Similar rules hold for subtraction and division. I want to emphasize that these limit holds hold under the condition that the limits of the component sequences exist as finite numbers. I can use these limit laws to decide if this sequence converges, since the limit of the terms is equal to the difference of the limits, provided those limits exist. Now the first limit is 0, since the degree of the numerator is less than the degree of the denominator here. And the second limit is also 0, since this is a geometric sequence with ratio of 4/5, and 4/5 is between 0 and 1. Therefore, the limit of our original sequence must be 0. In this video, we saw several ways to prove that a sequence converges. We saw that we could use calculus techniques like L'Hopital's rule after replacing the sequence with its associated function defined on real numbers. We also saw that we could use the squeeze theorem. We noted that all sequences that are bounded and monotonic must converge. And we saw that geometric sequences always converge if r is bigger than -1 and less than or equal to 1. Finally, we saw that we can use limit laws to handle sums and products and other conglomerations of sequences. This video is about geometric series and when they converge and when they diverge. A geometric sequence is a sequence of the form a times r squared, a times r cubed, and so on for some numbers a and r. This can be written in the wrapped up notation a times r to the k, where k goes from 0 to infinity. For example, if a is 3 and r is 1/2, the sequence would be 3, 3/2, 3/4, 3/8, and so on, which could be written as 3 times 1/2 to the k, where k ranges from 0 to infinity. A geometric series is the series you get by adding all these numbers up. So that would be a plus a times r squared, and so on, which can be written in summation notation as the sum from k equals 0 to infinity of a times r to the k. For our example, our series would be the following, which could be written as the sum from k equals 0 to infinity of 3 times 1/2 to the k. Sometimes you might get a geometric series that's in disguise, like this one. If I write out the first few terms, notice that we're told to start with I equals 2. So plugging in I equals 2 here, I get -1 squared over 3 to the 2 times 2 minus 3. That's 1 over 3. If I plug in I equals 3, I get -1 cubed. That's over 3 to the 2 times 3 minus 3, or -1 over 3 cubed, -1/27. When I equals 4, I get 1 over 243. If I look at the ratio of consecutive terms, -1/27 divided by 1/3 is -1/9. Similarly, the ratio here is also -1/9, suggesting that we might have a geometric series with ratio r of -1/9 and first term coming from here of 1/3. But there's another way to see this that's less arithmetic intensive and makes use of exponent rules. If we look at the basic term and rewrite it using exponent rules, this is 3 to the 2i times 3 to the minus 3. I can rewrite the 3 to the 2i as 3 squared to the I, and the 3 to the minus 3 in the denominator becomes a 3 cubed in the numerator. Now I can group together all the pieces that are raised to the i'th power and write this as -1/9 to the I times 3 cubed, or 27 times -1/9 to the I. Writing like this, I can see that every time I increases by 1, I get another factor of -1/9 multiplied in my expression, and therefore this is a geometric series with ratio -1/9, as I saw before. Now you might think that the first term should be 27, but remember that I doesn't start at 0, it starts at 2. So the first term is going to be what I get when I plug in the first value of I. So that's 27 times -1/9 squared, which works out to 1/3 as before. So we do have a geometric series with first term of 1/3 and common ratio of -1/9. In fact, we could rewrite it in a more standard form as the sum of 1/3 times -1/9 to the k, where k ranges from 0 to infinity. Since k equals 0 in this expression corresponds to I equals 2 in this expression, k is equal to, can be thought of as equal to I minus 2, and this is really a re-indexing and simplification to get from this version to this version. As you may know, a geometric sequence converges to 0 when the common ratio r is between -1 and 1. It converges to a when r is equal to 1, and it diverges otherwise when r is less than or equal to negative 1 or when r is greater than 1. We're assuming here that a is not equal to 0, since otherwise we'd have a very boring, though convergent, sequence of all zeros. I want to restate this convergence criteria in limit form since we'll use it later. What it's saying is that when r is between negative 1 and 1, the limit, as k goes to infinity, of a times r to the k is 0. That's what it means to converge to 0. When r is equal to 1, that limit is equal to a, and when r is less than or equal to negative 1 or greater than 1, that limit does not exist as a finite number. Now I'd like to find similar rules in terms of r for when a geometric series converges or diverges. Again, we'll assume that a is not equal to 0, since otherwise I just have a sum of a bunch of zeros, a boring series that would converge to 0. Our strategy is going to be to find a formula for the nth partial sum of the series and then take the limit of partial sums, since by definition that limit tells us whether the series converges or diverges. Before we carry out that strategy, I want to consider one special case, when r is equal to 1. Then the series is just a plus a plus a, and so that diverges to infinity if a is positive, or to negative infinity if a is negative. Remember, we're assuming that a is not 0. So far as 1, our series diverges, and from now on, we'll assume that r is not equal to 1. Let's look at a few partial sums. The first partial sum, s sub 1, is just the first term a. S sub 2 is a plus a times r, and so on. In general, the nth partial sum, s sub n, is a plus a times r squared. And I continue until, let's see, the last term will be a times r to the n minus 1. The second to last term will be a times r to the n minus 2. Notice that the nth partial sum only goes up to a times r to the n minus 1, since we're starting at a, which is a times r to the 0. I'd like to write the partial sum in a nicer form, so I don't have to write all those dots. And to do that, I'm going to use a trick. I'm going to multiply both sides of this equation by r. So on the left, I get r times s sub n, and on the right, I'm going to multiply each term by r. So the first term becomes a times r, the second term a times r squared, a times r cubed, and so on. This second to last term becomes a times r to the n minus 1, and the last term becomes a times r to the n. Notice that this equation and the equation under it have a lot of terms in common. They match up along the diagonals. So if I subtract the second equation from the first, on the left side, I'm going to get s sub n minus r times s sub n. But on the right side, a lot of my terms will cancel. This term will cancel with the next one. This one cancels with the previous one. And what I'm left with is just a minus a times r to the n. I get a minus sign here because I'm subtracting the whole equation. Now I can solve for s sub n. I can factor it out. I'll factor out the a also just to keep things tidy. And then I get that s sub n is a times 1 minus r to the n over 1 minus r. I don't have to worry about dividing by 1 minus r. That can't be 0 because, remember, I'm assuming that r is not 1. Now that I have a nice tidy formula for s sub n, I can proceed to take the limit as n goes to infinity and see if my sequence of partial sums converges or diverges. So that's the limit of my formula. And notice that the only part of this formula that depends on n is the r to the n. a, 1, 1 minus r are all constants as far as n is concerned, so we can use limit rules to take those out of the limit. I can rewrite the limit as a over 1 minus r times the limit of 1 minus r to the n, or even better, as a over 1 minus r times 1 minus the limit of r to the n. Now this limit I've seen before right on this page. It's the same as the limit I was considering when I was looking at convergence of sequences, where I use the same r and my a is equal to 1. So we know that this limit goes to 0 when r is between -1 and 1 and does not exist as a finite number when r is less than or equal to -1 or r is greater than 1. Therefore, the limit of the partial sums is going to equal a over 1 minus r times 1 minus 0, which is just a over 1 minus r, when r is between -1 and 1, and that limit will not exist as a finite number when r is less than or equal to -1 or r is greater than 1. Since the limit also doesn't exist as a finite number when r is 1, I can add a little equality sign, and now I've got all the cases for r covered. Let me write this down as a conclusion. The geometric series converges to a over 1 minus r for r between -1 and 1. I can also say that's the absolute value of r less than 1. And it diverges for the absolute value of r greater than or equal to 1. Let's use this fact in this example. Remember that we decided that this was a geometric series with common ratio r equal to -1/9, and we found the first term a by plugging in I equals 2 and got that first term of 1/3. Since the absolute value of r, the absolute value of -1/9 is 1/9, which is less than 1, we know that the series converges. And it converges to a over 1 minus r. So that's 1/3 over 1 minus -1/9, which is 1/3 over 1 plus 1/9. That's 1/3 over 10/9, which simplifies to 3/10. In this video, we looked at geometric series with first term a and common ratio r. We saw that a geometric series will converge if the absolute value of r is less than 1, and it'll diverge if the absolute value of r is greater than or equal to 1. In the case that it converges to a over 1 minus r, where a is the first term and r is the common ratio. There's a tricky problem on the 10.3 homework about Koch's snowflake. That's the figure you get by starting with a triangle and then putting little triangles on the sides whose bases are 1/3 as long as the original triangle. So that length there is 1/3 of that length. Then you iterate this. So you put tiny little triangles on each segment of the next triangle, make a figure like this, and you continue. So the problem is asking you to find the perimeter and the area of this figure. And I recommend making a giant table, something like this, where you have the stage or level in the first column. So at stage 0, you just have the regular triangle. At stage 1, you would have the triangle with the little pointy things here. And at stage 2, you have the figure that I drew above. Now, the other information you might want to gather are things like this: the length of the littlest segments at that stage, the number of littlest segments, the total perimeter, that's one of the things you need to find out. Then you might also want the area of the littlest triangles at that stage, the number of littlest triangles, and the total area from the littlest triangles. And then you might want just the total area, which will be sort of from all the stages added up. Okay, so let me do the first few levels for you, and then you can see if you can generalize and finish the pattern. So the length of the littlest segments of, if you have, this is your triangle here, it depends on the triangle side length, and different problems will have different numbers, so I'll just call it S. So the length of the littlest segments here is just S. And the number of littlest segments will just be 3 for the 3 sides of the triangle. So let's see, the total perimeter at that 0 stage will be 3S. At stage 1, the length of the littlest segments is going to be 1/3 of S, because each of these little segments of the little triangle is 1/3 the length of the total side length of the original triangle. So the number of little segments is going to be, well, in this case, it's going to be 12, which is 3 times 4. And so the total perimeter will be 1/3 S times 3 times 4, because it's the number of little segments times the length of the little segments. Okay, at the next stage, I've got teeny tiny little segments, and each one of those segments is 1/3 as big as the previous segment. So it's going to be 1/3 of 1/3 S, or 1/3 squared times S. The number of little segments, well, every time I do this, I'm replacing my side length, one segment, with 1, 2, 3, 4 segments, right? And the next stage, I replace that segment with 1, 2, 3, 4 segments. So I'm multiplying the number of segments by 4 each time. Each segment is proliferating into 4 littler ones. So that means the number of littlest segments should be 4 times the previous one. So that's going to be 3 times 4 times 4, or 3 times 4 squared here. Total perimeter will then be, let's see, 1/3 squared S times 3 times 4 squared. And you can continue with stage 3, stage 4, and stage N, and then you can find the limit of the total perimeter once you find that pattern. Now let's work on to area. So the area of the littlest triangle, well, we've seen in class that the area of an equilateral triangle is square root of 3 over 4 times S squared. Okay, now the next step, that little triangle we've added is going to have a smaller area than the triangle it sits on. And if I draw a picture up here, remember that little triangle, its base is 1/3 as long. So if I actually fill up one of my big triangles with the little triangles, so I can draw it like that, I'm getting a hexagon in the middle here. And that hexagon itself is going to be made up of 6 little triangles. So I'm going to have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 little triangles of this size that would fit in a big triangle, which means the area of the littlest, the little one, is 1/9 the area of the mama one, the big triangle. So in general, so this at this level 1, each little triangle is going to have 1/9 the area of the previous one. And at the next stage, the even littler triangle will be 1/9 as big as the triangle, the previous size triangle. So that's going to be 1/9 squared, square root of 3 over 4 S squared, and so on. Now, to count up the number of littlest triangles, well, there's just 1 in that stage 0 level, and there's going to be 3 at this stage, and there's going to be, well, at the next stage, I'm going to add a little triangle for each segment of my previous stage, right? Each segment is getting a little triangle on top of it. So I just have to count up the number of segments from the previous stage, which was 12, and that'll give me the number of triangles and that I'm adding. And the next stage, it's the number of segments at the previous stage, so 3 times 4 squared will be the number of littlest triangles, and so on. So if I want the total area just from the littlest triangles, I'm going to want to multiply the area of the littlest triangle by the number of littlest triangles, so that's 1 times square root of 3 over 4 times S squared. Here it's going to be 3 times 1/9 square root of 3 over 4 S squared. Here it's 3 times 4 times 1/9 squared, square root of 3 over 4 S squared, and so on. But now when I want the total area, I'm going to have to add up all the stages, right? Because the total area is made up of the big triangle, then its little babies, then their little babies, and so on. So I'm going to have to add these up. So this is basically going to be like sort of S0, right? The sum of the first one. And then this is going to be S1, which is 1 times square root of 3 over 4 S squared plus 3 times 1/9 square root of 3 over 4 S squared. And then this is going to be S2, which is like A0 plus A1 plus A2. Basically, the total area is going to be the sum of this column. It's an infinite sum. So you can, hopefully it's going to be a geometric series and you can add it up, but you have to be a little careful because this term here is different from all of these terms. It doesn't have the right factor of 4 in it, it turns out, if you look carefully. But the rest of these should be a geometric. So you just have to figure out the first term, which is this one. Well, so we're going to add up this separately. So we'll add up just this part. So this is the first term, figure out what r equals, add those all up, and then you can add this piece at the end. So I hope that helps you solve this problem. Tricky problem, but kind of a cool fractal application. This video explains how to determine whether a series converges or diverges using an integral. Let's start with the series, the sum of 1 over n squared. Please pause the video for a moment and think about why this might converge or diverge. The sum from n equals 1 to infinity of 1 over n squared is closely related to the integral from 1 to infinity of 1 over x squared dx. Let me show you what I mean. In this picture, I've graphed the function y equals 1 over x squared in blue. In green, I've drawn a bunch of rectangles. I've divided the x-axis into subintervals of length 1, and so each rectangle has a base of length 1 and a height given by my function's value on the right endpoint of the subinterval. So the first rectangle has a base of 1 and a height of 1, so it has an area of 1. The second rectangle has a base of 1 and a height of 1 over 2 squared, so that's 1/4. So the area here is 1/4. The next rectangle, base of 1 again and a height of 1/9, and so on. The area of each rectangle is just the same as its height, and its height is just given by 1 over n squared for the appropriate value of n. In other words, if I write out the first few terms of this series, it's exactly the same as the areas of my rectangles. And the sum of my series is just going to be the total green area. Now my integral can also be thought of in terms of area. This integral represents the area from 1 to infinity under my blue curve. We know that this area is finite because we know that this integral converges by the p-test, where p is 2. Now if I just look at the rectangles starting with the second rectangle on, all of those rectangles lie below the blue curve and to the right of the line x equals 1. So they'll have a smaller area, and therefore the area of these rectangles from the second one on has to converge to a finite number. That is, the sum from n equals 2 to infinity of 1 over n squared converges. We're interested in the sum from 1 to infinity, but that's just the area of this single rectangle plus the area of all these rectangles. So it's just one more than this sum here. So it also converges to a finite number. To recap, the chain of logic goes like this. First, we saw that the integral represents a finite area because of the p-test. From that, we can conclude that the sum from n equals 2 to infinity of 1 over n squared represents a smaller and also finite area. And from that, we can figure out that the sum from n equals 1 to infinity has to represent a finite area. So our series converges to a finite number. Let's look at another example, the sum from n equals 1 to infinity of 1 over the square root of n. Please pause the video for a moment and think about how you might use an integral to decide if this series converges or diverges. A natural integral to consider is the integral from 1 to infinity of 1 over the square root of x dx. This integral diverges by the p-test, where p is equal to 1/2, which is less than 1. Let's look at a picture to compare areas. The blue curve here is the graph of the function y equals 1 over the square root of x, and here, once again, I've drawn green rectangles using the right endpoints to get the heights of the rectangles. So the areas of my rectangles are the same as the terms in my series. As in the previous problem, if I ignore the first rectangle, then all the rest of the rectangles have an area that's less than the area under my curve from 1 to infinity. But there's a serious problem here. The integral from 1 to infinity of 1 over the square root of x dx diverges to infinity. The area of my rectangles from the second one on might be less than my area under the blue curve, but being less than something that diverges to infinity tells us nothing. This series could converge or it could diverge. But don't give up hope. If we just tweak this picture a little bit, we'll be able to get something that we can use here. In this second picture, I've used left endpoints instead of right endpoints for the heights of my rectangles. Because my function y equals 1 over the square root of x is a decreasing function, using left endpoints makes my rectangles have a larger area than the area under the corresponding section of the curve. Let me label the rectangles with their areas. The areas of these rectangles correspond to the terms in my series. But now we have that the area of the green rectangles, that total area is bigger than the integral from 1 to infinity of 1 over x square root of x dx. Since this integral diverges and this series is larger, it must diverge also. This method of comparing a series to an integral is a very general method for showing convergence. It's known as the integral test. The integral test says that if f is a continuous, positive, and decreasing function on the interval from 1 to infinity, and our terms a sub n are equal to f evaluated at n, then if the integral from 1 to infinity of f of x dx converges, the series from 1 to infinity of a sub n converges. And if the integral from 1 to infinity of f of x dx diverges, then the series diverges. Although I won't give a formal proof of this theorem, the logic behind it is the same logic we used in the previous two examples. If the integral converges, we use the picture here using right endpoints to draw our rectangles. The area of each rectangle is the same as its height, since the rectangle has base 1. And the height of each rectangle is just f sub n. So the area of the first rectangle is just f sub 1, which is a sub 1. The area of the second rectangle is f sub 2, which is a sub 2, and so on. If we focus on the second rectangle onwards, then the combined area of those rectangles is less than the area represented by the integral. So we can say the sum from n equals 2 to infinity of a sub n is less than or equal to the integral. Since the integral converges by assumption, this series here has to converge, and therefore our original series from n equals 1 to infinity must also converge. If instead our integral diverges, then we use the other picture and we use left endpoints for our rectangles. The areas of the rectangles are still given by a sub 1, a sub 2, and so on, but this time the combined area of the green rectangles, that area is now greater than or equal to the integral of our function. Since this integral diverges, the larger area must diverge as well. That's the idea behind the integral test, and to apply it, we just need to be able to integrate the function that corresponds to our terms and check that that function is continuous, positive, and decreasing. Actually, it's enough to check that the function is eventually continuous, positive, and decreasing. By eventually, I mean that it has these properties on some interval from r to infinity for some number r. This is good enough because then I can always draw these same pictures just starting with r instead of 1 in my picture and get that the integral converges if and only if the series starting at r converges by the same arguments we used before. But the series starting at r converges if and only if the series starting at 1 converges. since adding on finitely many extra terms to my series doesn't affect whether it converges or not. And the integral from r to infinity converges if and only if the integral from 1 to infinity converges. Because similarly, adding on a finite little piece of area from 1 to r doesn't change the convergent status of the integral. So by this chain of logic, it's okay if our function starts out increasing for a while, as long as it's eventually positive, continuous, and decreasing. Here's an example of the integral test in action. We want to know if the sum from n equals 1 to infinity of ln n over n converges or diverges. So let's look instead at the integral from 1 to infinity of ln of x over x. This is a continuous function because it's the quotient of two continuous functions, and we're starting at an x value of 1, so we don't have to worry about the denominator being 0. It's also a positive function, since we know that ln of x is greater than 0 for x bigger than 1, and therefore this quotient is greater than 0 also. Finally, let's check if our function is decreasing. One way to do that is to look at the derivative. If f of x is ln x over x, then f prime of x, by the quotient rule, is x times 1 over x minus ln x times 1 over x squared. This simplifies to 1 minus ln x over x squared, which is negative when 1 minus ln x is less than 0, that is, 1 is less than ln x, that is, e is less than x. So the function has a negative derivative and is decreasing whenever x is bigger than e, so it's eventually decreasing. The three conditions are met, so we can apply the integral test. Next, we need to figure out if this integral converges or diverges. This is an improper integral, so by definition, it's the limit, as t goes to infinity, of the integral from 1 to t of ln x over x. We can use u substitution to evaluate it, where u is equal to ln x, du is equal to 1 over x dx, and when x is equal to 1, u is equal to ln of 1, that's 0. When x is equal to t, u is equal to ln of t. Substituting in, we get the integral from 0 to ln t of u du. This integrates to u squared over 2 evaluated between ln t and 0. Substituting in our bounds of integration, we get the limit as t goes to infinity of ln t squared over 2 minus 0. Now as t goes to infinity, ln of t also goes to infinity. So ln t squared over 2 goes to infinity. Therefore, the integral diverges. And so by the integral test, the series also diverges. In this video, we saw that a series converges if and only if the corresponding integral converges, provided that the corresponding function is eventually continuous, positive, and decreasing. In this video, we'll determine whether series converge or diverge by comparing them to more familiar series. Suppose that the sum of a sub n and the sum of b sub n are series. And suppose that the terms of the series are always greater than or equal to 0, and that a sub n is less than or equal to b sub n for all n. In the pictures below, the heights of the blue bars are supposed to represent the a sub n's, and the heights of the green bars are supposed to represent the b sub n's. If we put the pictures together, we see that the heights of the blue bars are less than the heights of the green bars. So we have the inequality 0 is less than or equal to a sub n is less than or equal to b sub n. Since the base of each bar has length 1, the height of each bar is the same number as its area. So when we write the sum from n equals 1 to infinity of a sub n, this represents the area of all the blue rectangles added up, the total blue area. And when we write the sum from n equals 1 to infinity of b sub n, this represents the area of all the green rectangles, the total green area. Because the blue bars have a smaller area than the green bars, we can make some conclusions. First of all, if the total green area is finite, then so is the total blue area. In other words, if the sum of the b sub n converges, then so does the sum of the a sub n. Furthermore, if the total blue area is infinite, then so is the total green area. So we can also say if the sum of the a sub n's diverges, then so does the sum of the b sub n's. These facts are known as the comparison test for series and are very useful in establishing convergence. But we have to be careful not to take the conclusions too far. In particular, if the smaller series of a sub n's converges, then we really can't say anything about the larger series of b sub n's. The sum of the b sub n's could converge or it could diverge. Also, if the larger series of b sub n's diverges, then we can't conclude anything about the smaller series of a sub n's. The sum of the a sub n's could converge or could diverge. When using the comparison test to establish convergence or divergence, it's handy to compare your unfamiliar series to a familiar series that you already know converges or diverges. The following series are especially handy when making these comparisons. First, the geometric series, the sum of a times r to the n, which converges when the absolute value of r is less than 1. And second, the p-series, 1 over n to the p, which converges when p is greater than 1. Let's use the comparison theorem to determine whether the sum of 3 to the n over 5 to the n plus n squared converges or diverges. What matters most as far as whether a series converges or diverges is the behavior of the terms when n gets close to infinity. The behavior of the terms when n is small, the behavior of the first few terms, doesn't make any difference as far as whether that series converges or diverges. So I'm going to focus on what happens to these terms as n gets to infinity. Well, 3 to the n goes to infinity, and 5 to the n goes to infinity, and n squared also goes to infinity. But between 5 to the n and n squared, 5 to the n is going to infinity much faster. So I'm going to say that this 5 to the n term dominates the denominator. It's more important. And for that reason, the behavior of the series we're given should be similar to the behavior of the series 3 to the n over 5 to the n, where I've just left out the n squared term, which is insignificant compared to 5 to the n when n is large. So I'm going to compare our given series to this other series, which is a geometric series. In fact, the second series we know converges because it has a common ratio of 3/5, and the absolute value of 3/5 is less than 1. In order to use the comparison theorem, I'm going to need to compare the terms of this series to the terms of this series, and I want to show that these terms are less than or equal to those terms, because being smaller than a convergent series will guarantee convergence. It's clear that everything's positive, so we don't have to worry about that. And it's also clear that 5 to the n plus n squared is bigger than or equal to 5 to the n. When you divide by a bigger number, you get a smaller ratio, so 3 to the n over 5 to the n plus n squared is therefore less than or equal to 3 to the n over 5 to the n. We've shown that the inequality we need holds, and so by the comparison theorem, since the sum of 3 to the n over 5 to the n converges, so does our original series. We've established convergence using the comparison test. This video was about the comparison test, the fact that if we have 0 less than or equal to an less than or equal to bn, and the sum of the bn's converges, then the sum of the smaller series an's converges. And if the sum of the an's diverges, then the sum of the larger series diverges. The limit comparison test gives an alternative to the regular or ordinary comparison test for series. In the previous video, we looked at the series, the sum from n equals 1 to infinity of 3 to the n over 5 to the n plus n squared. And we used the ordinary comparison test, and we compared to the series the sum of 3 to the n over 5 to the n. This worked out pretty nicely because the terms here are less than the terms here, and this series converges. Being less than a convergent series ensures convergence. But if we change the problem very slightly and look instead at the sum of 3 to the n over 5 to the n minus n squared, look how things start to go wrong. If we now try to compare to the same series, then we get the inequality 5 to the n minus n squared is less than or equal to 5 to the n, and therefore 3 to the n over 5 to the n minus n squared is greater than or equal to 3 to the n over 5 to the n, since dividing by a smaller number gives a larger fraction. But this inequality, unfortunately, is not useful to us. Being greater than a convergent series doesn't guarantee convergence or divergence. So we can't conclude anything based on this inequality. The limit comparison test gives us one way around this. The limit comparison test says the following. Suppose that sum of an and the sum of bn are series with positive terms. If the limit as n goes to infinity of the ratio of an over bn is a number L, where L is a finite number that's bigger than 0, then either both series converge or both diverge. So they have the same convergence status. Let's try the limit comparison test on the problem we were just working on. We still want to compare to the same series, 3 to the n over 5 to the n, but this time we're going to try a limit comparison. So we're going to take the limit as n goes to infinity of the ratio of terms, 3 to the n over 5 to the n divided by 3 to the n over 5 to the n minus n squared. It doesn't actually matter which term goes on the top and which goes on the bottom. We could instead take the ratio the other way. Whatever limit we get when we do the ratio this way will just be the reciprocal of the limit we get when we do the ratio this way. So if this ratio is a finite number that's bigger than 0, this ratio, its reciprocal, will also be a finite number that's bigger than 0. So I'll just stick with the first computation. Let me simplify by flipping and multiplying. I can cancel my 3 to the n's. And now I can actually rewrite this as the limit of 1 minus n squared over 5 to the n. By breaking up my limit, this is the same as 1 minus the limit of n squared over 5 to the n, and this second limit is an infinity over infinity form. So using L'Hopital's rule, carry the 1 over, I'm going to get the limit of what I get when I take the derivative of the numerator and the derivative of the denominator. I've still got an infinity over infinity indeterminate form, so I'll use L'Hopital's rule again. The derivative of 2n is 2, and the derivative of the denominator is ln 5 times ln 5 times 5 to the n. Now the numerator is fixed at 2, while the denominator goes to infinity as n goes to infinity. Therefore, this fraction goes to 0, and my final limit is 1. Since 1 is bigger than 0 and it's finite, it's less than infinity, the limit comparison test tells me that my original series and my comparison series either both converge or both diverge. But my comparison series is a geometric series with ratio 3/5. So it definitely converges. Therefore, by the limit comparison test, our given series also converges. That's the limit comparison theorem in action. The limit comparison test tells us that for two series with positive terms, if the limit of the ratio of the terms is some number which is bigger than 0 and less than infinity, then the two series have the same convergence status. That is, they either both converge or both diverge. The limit comparison test is especially handy when the ordinary comparison test doesn't seem to work. When we know what we want to compare to, but we can't get the inequality to go the right direction. In this video, I'll prove that the limit comparison test works. The limit comparison test says that if the sum of the a sub n's and the sum of the b sub n's are two series with positive terms, and if the limit as n goes to infinity of the ratio a sub n over b sub n is equal to L, where L is a finite number that's bigger than 0, then either both series converge or both series diverge. To prove this theorem, let's start by assuming that all the hypotheses are true. That is, we'll assume all the stuff in brackets here is true. The limit as n goes to infinity of a sub n over b sub n equals L means that if I plot the numbers 1, 2, 3, and so on the x-axis, so those are the values of n, and I plot the ratios a sub n over b sub n on the y-axis, those ratios are going to settle down to a value of L as n goes to infinity. Using more technical mathematical language, it means that for any small number epsilon that's bigger than 0, we can trap the ratios within epsilon of L as long as we go out far enough for our values of n. That is, there exists a number capital N such that an over bn is between L plus epsilon and L minus epsilon for little n bigger than or equal to capital N. In the picture here, a value for capital N of 3 would work, because for all little n's bigger than or equal to 3, my ratios are trapped in between L minus epsilon, which is right here, and L plus epsilon, which is that upper bound here. Let's pick a small enough epsilon so that this interval here doesn't extend all the way down to through 0 on the y-axis. It just extends through positive numbers near L. Recall that L itself is a positive number, so it's possible to trap it in a little interval that's all positive numbers. For example, we could pick epsilon to be equal to L over 2, for example. That way the interval that I'm drawing here would extend down to L minus L over 2, which is equal to L over 2, and it would extend up to L plus L over 2, which is 3L over 2. So we have that L over 2 is less than AN over BN is less than 3L over 2 for little n bigger than or equal to our capital N that works for that value of epsilon. Now I'm going to multiply all three sides of this inequality by b sub n. Recall that b sub n is a positive number. All the series terms are positive, so that doesn't change around the inequalities at all. So we get L over 2 times b sub n is less than a sub n is less than 3L over 2 times b sub n. And remember that everything here is bigger than 0, since all the a sub n's and b sub n's are positive. Let's think about what this inequality tells us. First of all, if the sum of the b sub n's converges, then so does the sum of 3L over 2 times b sub n, because I'm just multiplying that series by a constant. It's still convergent. But now my a sub n terms are less than the terms of a convergent series. So by the ordinary comparison test, we know that the sum of the a sub n's converges also. Furthermore, if the sum of the b sub n's diverges, then we can focus on this part of the inequality. We know that L over 2 times b sub n diverges also. And so here we have the a sub n's are bigger than the terms of a divergent series. So the sum of the a sub n's must diverge, just using the ordinary comparison test. Now you might be worried about the fact that this inequality only holds for little n bigger than or equal to some capital N. So we could rewrite this argument a little bit to say if the sum from n equals 1 to infinity of the b sub n's converges, then so does the sum from n equals capital N to infinity of b sub n, because adding or subtracting finitely many terms off the front never changes the convergence status of a series. After that, we can say, well then, so does the sum from n equals capital N to infinity of 3L over 2 times b sub n. And so then by the ordinary comparison test, since this inequality does hold for all little n bigger than or equal to capital N, we can then conclude that the sum from little n equals capital N to infinity of a sub n converges. And so the sum from n equals 1 to infinity of a sub n converges also, since again, adding or subtracting finitely many terms from the beginning of a series doesn't change anything about convergence. We could similarly rewrite the second part of the argument using precise indices as well. We've shown that the sum of the bn's and the sum of the an's either both converge or both diverge, and that completes the proof of the theorem. In this video, we proved the limit comparison test using the ordinary comparison test. This video defines absolute convergence and how it's related to convergence for a series. A series is called absolutely convergent if the series of absolute values of the terms converges. Please pause the video for a moment and try to decide which of the following series are convergent and which ones are absolutely convergent. The first series is convergent because it's a geometric series with ratio r equal to negative 0.8. It's also absolutely convergent because if I take the series of absolute values, that's the same thing as the geometric series with a ratio of 0.8, which is also convergent. The second series, the sum of 1 over the square root of k, is not convergent. We can see this by the p-test, since p is equal to 1/2, which is less than 1. It's also not absolutely convergent. In this case, the sum of the absolute values of the terms is just the same as the sum of the original terms, which we already said diverges. The third series is the sum of negative 1 to the j times 1 over j. This is a convergent series by the alternating series test. In fact, This is the alternating harmonic series. What about absolute convergence? If we look at the sum of the absolute values of the terms, that's just the same thing as the regular harmonic series, which diverges. So this series is not absolutely convergent. Here's a question for you. Is it possible to have a series that's convergent but not absolutely convergent? Please pause the video for a moment and try to answer this question. The answer is yes. We just saw an example of such a series, the alternating harmonic series. There are many other examples of such series, and in fact, there's a special name for them. They're called conditionally convergent. A series is called conditionally convergent if it is convergent, but not absolutely convergent. In symbols, that is, the sum of the ANs converges, but the sum of the absolute values of the ANs diverges. Next question for you. Is it possible to have a series that's absolutely convergent but not convergent? This is a little trickier, but please pause the video for a moment and think about your answer. The answer to this one is no. It's a fact that every absolutely convergent series is convergent. Let me prove to you why that's true. Let's suppose that we have a series that's absolutely convergent. That is, the sum of the absolute values of the ANs converges. We know that the ANs might be positive or negative, but they do have to lie in between the absolute value of AN and the negative absolute value of AN. Actually, it's true that A sub n is either equal to its absolute value or its negative absolute value, but I'm writing it this way with inequalities to help set the mood for using the comparison test. Now, I can't quite use the comparison test here to prove that the series of A sub n's converges, because even though the A sub n's are less than or equal to the terms of a convergent series, they're not necessarily positive or greater than or equal to 0. And the comparison test only applies to series whose terms are all greater than equal to 0. But there's a nice trick to get around that difficulty. And that trick is to add the absolute value of A sub n to all the sides of the inequality. So then I get 0 is less than or equal to A sub n plus the absolute value of A sub n, which is less than or equal to twice the absolute value of A sub n. Now, since the sum of the absolute value of A sub n's converges, so does the sum of twice the absolute value of A sub n, since it's just a constant multiple. Based on this inequality, which now does involve terms that are greater than or equal to 0, I can conclude that the sum of A sub n plus the absolute value of A sub n converges based on the ordinary comparison test. But now, the series that we want, the sum of the A sub n's, can be written as a difference. And we know that a series formed by subtracting the terms of two convergent series itself converges. So this converges, in fact, to the difference of the sums. We've proved that if our series is absolutely convergent, then it must be convergent. The fact that absolute convergence implies convergence can come in handy when you're trying to prove that a series converges, as in the following example. In this example, we want to prove that this series is convergent or divergent, but the cosine and sine make things a little bit tricky. My intuition here is that this series should converge, since cosine and sine are bounded, and so this essentially should behave something like the sum of 1 over n cubed, which converges because of the p-test. But we can't just compare our series to the sum of 1 over n cubed and use the ordinary comparison test like we've done in similar problems in the past. What's different here is that our terms are not always going to be positive, because sine and cosine can be positive and negative, and so can their sum. To help us out of this pickle, let's think about absolute convergence instead. If we look at the sum of the absolute values, which is the same as the sum of the absolute value of the numerator divided by n cubed. Since cosine of n is between 1 and negative 1, and sine of n is also in between 1 and negative 1, we know that the sum cosine n plus sine of n has to be less than or equal to 2 and bigger than or equal to negative 2. In fact, it can't even get all the way to 2 or all the way down to negative 2. We could find a tighter bound if we tried, but this is good enough for our purposes. This inequality can be rewritten as the absolute value of cosine n plus sine of n is less than or equal to 2. And if I divide both sides here by n cubed, I have an inequality involving positive terms. So, since we know the sum of 1 over n cubed converges by the p-test, that implies that the sum of 2 over n cubed also converges as just a constant multiple, and that implies that the sum of my absolute value of cosine n plus sine n over n cubed converges by the comparison test. Therefore, we know that our series is absolutely convergent. And therefore, it must be convergent, since an absolutely convergent series is always convergent. We've shown that our original series converges. In this video, we saw that if a series is absolutely convergent, then it has to be convergent, but not vice versa. This video is about the ratio test, a test that can be used to prove that a series converges or diverges. The ratio test is all about looking at the ratio of consecutive terms. To figure out how it works, it can be helpful to think about geometric series first. Recall that for a geometric series, the ratio of consecutive terms is given by this number r. And if r has absolute value less than 1, the series converges. While if r has absolute value greater than 1, it diverges. For more general series, the ratio of consecutive terms is not necessarily a constant. But if we look at the limit as n goes to infinity of the absolute value of the ratio of consecutive terms, and if we get a limit of L which is less than 1, then the series converges, just like a geometric series. In fact, the series is absolutely convergent, meaning the sum of the absolute values of the ANs converges, and therefore the sum of the ANs converges also. If instead the limit as n goes to infinity of the absolute value of the ratio of consecutive terms is a number L that's greater than 1, or if that limit is infinity, then just like a geometric series, the series diverges. Finally, if the limit of the absolute value of the ratio of consecutive terms is exactly equal to 1, or if the limit doesn't exist, then the ratio test is inconclusive. That is, the sum of the a sub n's may converge, or it may diverge. And to figure out which, we'll have to use a different test or a different argument. Let's apply the ratio test to this series. We'll need to compute the limit as n goes to infinity of the absolute value of the ratio of consecutive terms. In this case, that's the limit as n goes to infinity of the absolute value of n plus 1 squared times negative 10 to the n plus 1 divided by n plus 1 factorial, all over n squared times negative 10 to the n over n factorial. I've just plugged in n plus 1 for n in this formula to get the a sub n plus 1th term. I can simplify this by flipping and multiplying. And now I'm going to rearrange my factors. This expression is equivalent to the previous one. I've just arranged factors so that similar factors are on top of each other. This will make it easier to cancel things. Now n factorial means n times n minus 1 times n minus 2 and so on. And n plus 1 factorial means n plus 1 times n minus 1 and so on. So if I divide n factorial by n plus 1 factorial, all my factors from the numerator will cancel with factors from the denominator, and I'll just be left with 1 over n plus 1. Also, negative 10 to the n plus 1 over negative 10 to the n cancels out to just negative 10 to the 1 power. So I can rewrite my limit as n plus 1 squared over n squared times negative 10 times 1 over n plus 1. I'm going to divide my limit of a product into a product of limits. Now as n goes to infinity, n plus 1 over n goes to 1. So this expression, which is equivalent to the square of n plus 1 over n, also goes to 1. The limit of the absolute value of negative 10 is just 10, and the limit as n goes to infinity of 1 over n plus 1 is 0. Therefore, our limit is 1 times 10 times 0, which is 0. And since 0 is less than 1, by the ratio test, we know that our series converges absolutely. This video was about the ratio test, which focuses on the limit as n goes to infinity of the absolute value of the ratio of consecutive terms. Depending on whether this limit is less than 1, greater than 1, or equal to 1, we can determine whether the series converges, diverges, or if we need to try another test. In this video, I'll prove the ratio test for convergence and divergence of series. The ratio test says that for a series, if the limit of the absolute value of the ratio of consecutive terms is equal to a number L that's less than 1, then the series is absolutely convergent, and therefore convergent. If, however, the limit of the absolute value of the ratio of consecutive terms is a number L that's bigger than 1, or is equal to infinity, then the series is divergent. Although I didn't write it here, if the limit is equal to 1 exactly, or if the limit doesn't exist, then the ratio test is inconclusive and can't be used to establish convergence or divergence. To prove that the ratio test works, let's first assume that the limit is less than 1. This means that if I graph n on the x-axis, and my absolute value of the ratio of consecutive terms on my y-axis, I get a bunch of dots that settle at a value of L. And this number L is less than 1. Let's pick a tiny number epsilon so that when I add epsilon to L, I'm still less than 1. So I'll pick epsilon greater than 0 such that L plus epsilon is less than 1. By the definition of limit, if I go far enough to the right on the x-axis, all of my red dots are going to be trapped in between this epsilon interval around L. In mathematical symbols, this means there exists a number capital N such that the absolute value of ratios, the thing that's limiting to L, is between L plus epsilon and L minus epsilon for all little n bigger than or equal to capital N. I'm going to multiply all three sides of this inequality by the absolute value of a sub little n. Now I'm going to focus on the right end of the inequality because ultimately I want to prove that my series is absolutely convergent. So it's going to be more useful to show that my terms are smaller than things than to show that my terms are bigger than things. This inequality is true for all values of little n that are bigger than or equal to capital N. So in particular, it's true when little n equals capital N. The inequality is also true when little n is equal to capital N plus 1. Here I've just plugged in capital N plus 1 for little n here, and when I plug it in here, I end up with capital N plus 1, which is capital N plus 2. Now if I string these two inequalities together, essentially I'm substituting in this inequality right here. I get the following inequality, which simplifies to give me the absolute value of a sub capital N plus 2 is less than L plus epsilon squared times the absolute value of a sub capital N. Let's try this one more time. Going back to my original inequality here, I'm going to plug in capital N plus 2 for lowercase n. And stringing these two inequalities together, I get that this is less than L plus epsilon cubed times the absolute value of a sub capital N. And in general, the same reasoning shows that the absolute value of a sub capital N plus I is less than L plus epsilon to the I times the absolute value of a sub capital N for any I. With all these inequalities, I'm gradually building up two series. The first series is the sum of the absolute value of a sub capital N plus I. Let's start that from I equals 1 to infinity. And the second series is the sum of L plus epsilon to the I times the absolute value of a sub capital N. Again, let's start from I equals 1 to infinity. Now this second series is a geometric series where R is equal to L plus epsilon, which is less than 1 because remember we chose epsilon to make sure that it was less than 1. Therefore, this series converges. But that's great news because now looking at this inequality, we can show that series 1 converges just using the ordinary comparison test and recognizing that these terms are bigger than or equal to 0. So series 1 converges by the comparison test, but series 1 is just the tail end of the series, the sum from n equals 1 to infinity, absolute value of a sub little n. So this series converges because it's just finitely many terms added on to a convergent series. And so we've shown that our original series converges absolutely. This proves the first part of the ratio test. Now let's prove the second part, and let's start by assuming that the limit is greater than 1. This time, since L is bigger than 1, we can pick a tiny number epsilon so that when we go down from L by epsilon, we don't go as far as the number 1. So we're going to pick an epsilon greater than 0 such that L minus epsilon is still greater than 1. As before, we can use the definition of limit and a little algebra to get the same inequality as we got before. This time, I'm going to focus on the left side of the inequality though. Since L minus epsilon is greater than 1, this tells me in particular that the absolute value of a sub n plus 1 is always bigger than the absolute value of a sub little n for little n bigger than or equal to capital N. This means that the absolute value of a sub capital N is less than the absolute value of a sub capital N plus 1, which is less than the absolute value of a sub capital N plus 2, and so on. And so my sequence of terms is actually ultimately an increasing sequence of positive numbers. So my sequence of terms cannot converge to 0. limit as little n goes to infinity, absolute value of a sub little n cannot be 0. And so the limit as little n goes to infinity of a sub little n cannot be 0 either. But that means that my original series cannot converge. It has to diverge by the divergence test. We still have one detail to consider: the possibility that the limit of the absolute value of ratios is infinity. In this case, the argument that we just used works almost exactly the same. If we assume that the limit is infinity, then we can skip this part here and here, and just note that there exists some capital N such that the ratios are always bigger than, say, 2 for all little n bigger than or equal to capital N. Since if the ratios are heading towards infinity, they're certainly going to be bigger than 2 eventually. This gives us the same inequality that we need. I'll just write a 2 there. And now, as before, we can conclude that a sub n plus 1's absolute value is strictly greater than a sub n's absolute value. In fact, it's greater than twice of it for all little n bigger than or equal to capital N, and we can make the same conclusion about an increasing sequence of positive terms so that the terms can't go to 0, and the series has to diverge by the divergence test. This concludes the proof of the ratio test. In this video, we proved the convergent part of the ratio test by comparing our series to a convergent geometric series, and we proved the divergent part of the ratio test using the divergence test. This video is a review of all the convergence tests we've talked about in class. I'll list the tests roughly in the order that I would try to apply them. I like to start with the divergence test. Usually it's pretty easy to check if the limit as n goes to infinity of the terms is equal to 0, and if not, you're done because the series diverges. Be careful though, the divergence test can only be used to check for divergence. It cannot be used to prove convergence, because if the limits of the terms is equal to 0, the series may converge, but it may still diverge. The next thing I do is to check if the series is a simple p-series or a geometric series. Remember, a p-series is a series of the form 1 over n to the p. N is our indexing variable. P is some number like 2 or 5.8. And this is easy to test for convergence since it converges if p is greater than 1 and it diverges otherwise. A geometric series, this is the kind of the form a times r to the n, where a is the first term. Let me start at 0 here, so it's really the first term, and r is the common ratio. And this one's easy to check too because it converges if the absolute value of r is less than 1 and diverges otherwise. If the series happens to be alternating, then the alternating test is a good one to apply next. Be careful, this test can only be used to prove convergence. If the series is actually alternating, and what I call the step size, that's the absolute value of the terms, is going to 0 and decreasing, then we can conclude that the series converges. But if some of those conditions are not satisfied, we can't automatically assume that the series diverges. Well, not at least by the alternating test. If the step size doesn't go to 0, then we should have already figured out the series diverges by the divergence test. We're really applying the divergence test there. And if the step size is not decreasing, not even ultimately decreasing, then the alternating test is just inconclusive. It doesn't apply. We don't know yet whether it diverges or converges, and we have to look for another test. Now, if the series is not one of these nice p-series geometric or alternating series, my go-to test is going to be the ratio test. The ratio test is especially good for series with n factorials in them or 2 to the n's in them. Things with sort of geometric pieces that are not strictly geometric are good candidates for the ratio test. But be careful. the ratio test will be inconclusive for what I call p-like series. So series that just have, things like n's in them, and maybe the square roots of n's in them, things that can be easily compared to a p-series are not good candidates for the ratio test. So if you happen to remember that, you can save some time by not trying the ratio test on those. If the ratio test is not a good candidate or ends up being inconclusive, what I might try next is one of the comparison tests. So that would be like what I call the ordinary or the limit comparison test. We generally want to compare to series that we know a lot about, that we know the convergence status of. So we generally want to compare to either p-series or geometric series. The comparison tests are especially good for p-like series that the ratio test is inconclusive for. And to figure out what to compare to, it's a good rule of thumb to consider the dominant or highest power terms. One thing you need to be aware of when applying the comparison test is that it only applies to series with positive terms. Of course, the first few terms never matter for a series convergence, so it's okay to apply it if you have eventually positive terms. But if the terms never become always positive and they're not strictly alternating, so the alternating test doesn't apply, we don't have to give up hope. We can use the fact that absolute convergence implies convergence. That's what I try as sort of my seventh test to try. So you can just take the absolute values of your terms and then maybe use the comparison test. And if that works to prove convergence, then your original series will converge also. Another method I haven't mentioned before is to use limit laws to split up the series. So if you have the sum of two series, say a p-series and a geometric series, then a natural thing to do is to split this up as the sum of two series and use a different method for each piece. If both pieces converge, like they do in this situation, then the sum also converges. Also, if one piece happens to converge and the other diverges, then the sum will diverge. The only thing to be careful of is that if both pieces diverge, then the sum may still diverge, but it may converge because there might be cancellation. One piece might be diverging to infinity and one piece may be diverging to negative infinity, and that's an indeterminate kind of form. If none of this stuff has worked so far, I might look to try the integral test and compare my series to an integral. This is especially handy, in my experience, for series with logs in them. So something, and also it has to be a series where the integral is easy to compute. So, something like ln n over n, if you instead look at the integral of ln x over x, that's pretty easy to compute using u substitution, and so that would be a good candidate for the integral test. Be aware that the integral test can only be used when the series terms can be thought of as the function's values at integers for a function that is positive, continuous, and decreasing. Last on my list is the method of telescoping series. I put it last only because it's kind of a hassle to work with telescoping series, but it does have some good points. First of all, using the method of telescoping series, you can actually compute the sum rather than just tell if it converges or diverges. The only other tool on this list that'll actually compute the sum of an infinite series is the geometric series test, where we have a formula for the sum provided it converges. Another reason to use the telescoping series is if you happen to notice that your terms are the difference of related expressions. So something like the sum of e to the 1 over n plus 1 minus e to the 1 over n might be a good candidate for telescoping series. Something like the sum of 1 over n squared minus 1 would also be a reasonable candidate because you can rewrite it using the method of partial fractions. And using that method and the telescoping series stuff will help you find an actual sum. But if you just want to know convergence, it'll be a lot easier just to use comparison to a p-series 1 over n squared for this one. So that's pretty much everything I know about convergence tests for series. If you want to keep watching, I'll take a look at some examples on the next page. Before you keep watching, please take a moment to look at these 6 examples and decide which convergence or divergence test you might try. Please be aware that for many of these series, there are lots of tests that'll work. So just because you pick a different one than I do doesn't mean that yours is wrong. I think this first example can be conquered using the divergence test. My hunch is if we took that limit and used L'Hopital's rule, we'd get a limit of infinity, not 0. An alternative, though, would be to use the ratio test, because this is a term that has a geometric piece as well as some other stuff. This second example is an alternating series, so my first try is going to be the alternating series test. And my recollection is it does work to prove convergence in this case. For this third one, this is the kind that I call a p-like series, because if I just look at the dominant terms, the highest power terms, I could compare to the p series, which is 1 over n squared cube rooted, or in other words, 1 over n to the 2/3 power. Since this one diverges, I'm going to expect my original one will also diverge. I'll probably need to use the limit comparison test because I don't think the inequalities will go the right direction for the ordinary comparison test. This next one's a perfect candidate for splitting up into 2 pieces. This one, the second piece, I can use the geometric series test to show convergence. And this first one, since it has an n factorial, that's a great candidate for the ratio test. This next one's kind of tricky for me. At first glance, I almost thought it would be a candidate for the integral test. If this had just been an n instead of an n squared, I might be able to integrate using u substitution. But because it's an n squared, the integral test would be more tricky to do. I might have to do integration by parts or something, so I'm going to stay away from that. And I'm going to start by trying the ratio test, because this does have a geometric kind of like piece to it. And this last example, I'm going to use the integral test here, because I know I can integrate 1 over x ln x dx using the u substitution, u equals ln x. Applying convergence and divergence tests is something that takes practice. The more you do it, the better you'll be at recognizing which tests might apply. But a lot of times there's no substitute for just trying the test, and if it doesn't work or it's inconclusive, just try something else. Good luck, and see you in class. This video introduces some of the ideas and key formulas of Taylor series. One of the main ideas behind Taylor series is the idea of approximating functions with polynomials. So suppose we have some function f of x. We want to approximate this function with a polynomial, and we'd like the approximation to be good near x equals 0. And we're going to assume that f prime of 0 exists, and f double prime of 0 exists, and f's third derivative exists at 0. All of its derivatives, we're going to assume, exist at x equals 0. Now, if we just want to get f's value right at 0, we could approximate f with the constant function, y equals f of 0. We can think of this constant function as being a degree 0 polynomial approximation, but it's a pretty lousy approximation. We can do much better than this. In fact, we can do a lot better even if we just use a degree 1 polynomial. That's a linear function. As you know, the tangent line at x equals 0 is a linear function that provides a pretty good approximation for the actual function when x is near 0. At least it's the best approximation you can hope for out of a linear function. The equation for the tangent line is given by y equals f of 0 plus f prime of 0 times x. This comes straight from the point-slope form for a line, where m is the slope of the tangent line, that's the derivative at 0, and the point, x1, y1, is just the point 0, f of 0. So we get y minus f of 0 is f prime of 0 times x minus 0, which simplifies to that equation for the tangent line right there. Notice that the tangent line has the same value as f of x at x equals 0, and it has the same slope as f of x at x equals 0. But I'd like to do a little better than this. I'd like to approximate my function f of x with a polynomial that has the same value, the same slope, or first derivative, and the same second derivative as f of x at x equals 0. It turns out I can do this with a degree 2 polynomial, and I'll show you how. In general, a degree 2 polynomial, also called a quadratic, is a polynomial of the form p of x equals c sub 0 plus c sub 1 times x plus c sub 2 times x squared. And now I just have to figure out what values of the constants, c sub 0, c sub 1, c sub 2, will make my polynomial agree with my function in its value, first derivative, and second derivative. Well, if I want p of 0 to equal f of 0, then that means I want c sub 0 plus c sub 1 times 0 plus c sub 2 times 0 squared to equal s value at 0. In other words, c sub 0 had better be equal to f of 0. But now I also want p prime of 0 to equal f prime of 0. P prime of x is equal to c sub 1 plus 2 times c sub 2x. I'm just using my derivative rules on the equation for p, remembering that my c's are constants. Therefore, to evaluate p prime of 0, I just plug in 0 for x, and I get c sub 1. But this needs to equal f prime of 0, and therefore c sub 1 is equal to f prime of 0. Finally, I want p double prime of 0 to equal f double prime at 0. I can find p double prime of x by taking the derivative of my derivative. So that gives me 2 times c2, but that needs to equal f double prime of 0, means that c2 had better equal f double prime of 0 divided by 2. So now let's look what happened. Requiring that p has the same value at 0 as f forces c sub 0 to have the value of f of 0. Requiring that the polynomial and f have the same first derivative at 0 forces the value of c sub 1 to equal f prime of 0. And requiring that the polynomial and the function have the same second derivative at 0 forces the value of c2 to be f double prime of 0 divided by 2. So we've shown that there is a second degree polynomial that has the same value, first derivative and second derivative as f at x equals 0, and there's a unique such polynomial, and it's given by p of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x squared. Visually, that second degree polynomial is going to look like a parabola. It might look something like this. Let's play this game again. But this time, I want to find a degree 3 polynomial, p of x, such that p of 0 is the same as f of 0, p prime of 0 is the same thing as f prime of 0, p double prime of 0 is equal to f double prime of 0, and p's third derivative at 0 is the same as f's third derivative at 0. Graphically, that's going to be a cubic polynomial that approximates my function, and it's going to be a pretty close approximation. We know that a degree 3 polynomial in general has the form c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed, and we need to find the values of all the constant c's. Please pause the video and see if you can figure out the values of those constants, especially the value of c sub 3 in terms of the value of f and its derivatives at 0. If we write down the derivatives of p, we get the following expressions. And if we evaluate these expressions at x equals 0, all the terms with x's in them vanish, so we get these expressions. Now, because we want our polynomial's value and its derivatives to match the value and derivatives of our function, we get these equations from which we can solve for our constants. C sub 0 is f of 0, C sub 1 is f prime of 0, C sub 2 is f double prime of 0 over 2, and C sub 3 is the third derivative of f at 0 divided by 6. Notice that that number 6 came from multiplying 3 times 2, and that 3 and that 2 came from bringing down my successive exponents when I took derivatives. We can keep track of this process by rewriting C sub 3 as the third derivative of f at 0 divided by 3 times 2, or 3 factorial. So the third degree polynomial that approximates our function is p of x, which is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x squared plus f's third derivative at 0 over 3 factorial times x cubed. I'll write this as p sub 3 to remember it's the third degree polynomial. We can repeat this process to get a fourth degree polynomial whose value at 0 is the same as f of 0, and whose first 4 derivatives at 0 are the same as f's first 4 derivatives at 0. Please pause the video and either work out expressions for the coefficients of p sub 4, or else make an educated guess what those coefficients should be based on the patterns you see. You should get that the fourth degree polynomial has the same first terms as the third degree polynomial and has a final term of f's fourth derivative at 0 over 4 factorial times x to the fourth. If we continue this process forever, finding polynomials of higher and higher degree that match more and more derivatives of f, then in the limit we'll have infinitely many terms that look like this. This is an infinite series, and it can be written in summation notation as the sum from n equals 0 to infinity of the nth derivative of f at 0 divided by n factorial times x to the nth power. This works as long as we use the conventions that the 0th derivative means just the function, that 0 factorial is equal to 1, and that x to the 0 is just equal to 1 even if x is 0. This infinite series is called the Maclaurin series for f of x, and it's also called the Taylor series for f of x centered at x equals 0. Now, so far we've been focusing on the value of f and its derivatives at x equals 0. What if we wanted to approximate f of x near x equals a? Please pause the video and write down what you think the Taylor series centered at x equals a should look like. This is a series, I'll call it t of x, that we want to match f's value at a, and we want all of its derivatives to match f's derivatives at a. It makes sense that this series should have a formula similar to the formula we just found, but it should involve derivatives at a instead of derivatives at 0. In addition, the formula needs to involve powers of x minus a instead of powers of x. I'll leave you to think about the details and to verify that this series really does have the derivatives that we want it to have. In this video, we tried to approximate a function by polynomials that had the same value and derivatives at x equals 0, and we ended up with a formula for a Taylor series at x equals 0, which we generalized to a Taylor series centered at x equals a. This video defines power series. Informally, a power series is a series with a variable in it, often the letter x, and it looks like a polynomial with infinitely many terms. For example, if we look at the series, the sum from n equals 0 to infinity of 2n plus 1 times x to the n over 3 to the n minus 1, that's a power series with variable x. If we expand that out by plugging in values of n, we get when n equals 0, 1 times x to the 0 over 3 to the minus 1. X to the 0 is 1, and 3 to the minus 1 on the denominator is the same as 3 on the numerator, so we can rewrite this term as just 3. The next term, when n equals 1, is 3 times x to the 1 over 3 to the 0. We can rewrite this as 3x, since 3 to the 0 is 1. The next term is 5x squared over 3, and we can continue like this. I want to point out that when working with power series, x to the 0 is always taken to be 1, even though there's a possibility that x could end up being 0, and 0 to the 0 is considered undefined in other contexts. When working with power series, x to the 0 for any value of x is 1. The next series expands out to 1 plus 5 times x minus 6, and so on. This is an example of a power series centered at 6 because of all the factors of x minus 6. In general, a power series centered at a is a series of the form the sum from n equals 0 to infinity of c sub n times x minus a to the n. Where x is the variable, the c sub n's are real numbers, they're constants, called the coefficients, and a is also a real number, a constant, that's called the center. If I expand out the power series and write out the first few terms, it looks like this, where c sub 0 is the constant term. Notice that x minus a to the 0 is taken to be 1, even when x equals a. If the power series is centered at 0, then we just set a equal to 0. We can write this a little more efficiently in the following form. Sometimes you might see a power series that starts with index of 1 instead of 0. That's perfectly legit, it just means there's no constant term. Or if you prefer, you can think of the constant term as being 0. It's also fine for the index to start at some other positive number. But it's not considered a power series if the index starts at a negative number, resulting in x's in the denominator. That's all for the definition of power series. Recall that a power series is a series with a variable in it. In this example, the c sub n and the a are supposed to be real numbers that are held constant. So the only variable is x. That's the only place where I can plug in different values at different times. This video explores the question of for what values of the variable x does the power series converge, and for what values of x does it diverge. Let's look at a few examples. First, for what values of x does this power series converge? There's one value of x that I know for sure it converges for. Please pause the video for a moment and try to guess which value of x I'm thinking of. The series definitely converges when x equals 3. If I expand out the first few terms of the series, I get this expression. Then plugging in 3 for x, all of my terms vanish to 0 except for my constant term of 1. So at x equals 3, the series converges to its constant term. And in fact, this is true of any power series. All power series converge at their center. But let's see what other values of x it converges for. Although we have many tests for convergence in our toolkit, the ratio test is usually the best test to use to determine where a power series converges. For the ratio test, we need to take the limit, as n goes to infinity, of the absolute value of the ratio of consecutive terms. For our example, this is n plus 1 factorial times x minus 3 to the n plus 1 divided by n factorial times x minus 3 to the n. Let's simplify by canceling things. And we get n plus 1 times x minus 3. Now x minus 3 is some number, and I'll assume it's a non-zero number since I already dealt with the case when x equals 3. So I have a non-zero number that stays fixed as n goes to infinity times a number that's going to infinity. So the absolute value of the product has to go to infinity, no matter what x value we have, other than the x value of 3. The ratio test says that if this limit is infinity, the series diverges. Therefore, the power series diverges for all values of x except for 3. The only place where it converges is at the center of 3. In this next example, the center of the series is -4, so the series definitely converges when x equals -4. Let's use the ratio test to figure out what other values of x make it converge. So we'll take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. This works out to the limit of the absolute value of -2 to the n plus 1 times x plus 4 to the n plus 1 divided by n plus 1 factorial all over -2 to the n x plus 4 to the n over n factorial. Let's simplify by flipping and multiplying and rearranging a little. After canceling, we get the limit of the absolute value of -2 times x plus 4 divided by n plus 1. The numerator of this expression doesn't depend on an n, so it stays fixed as n goes to infinity, but the denominator goes to infinity. Therefore, we're dividing some fixed constant by larger and larger numbers, and so this limit is equal to 0. Once again, the limit doesn't depend on x's value. It's always 0, no matter what x is. So by the ratio test, since 0 is less than 1, the series converges for all values of x. Here's our third and last example. In this example, it's a little trickier to figure out what the center is. One thing we can do is to rewrite the series in a more standard form by factoring out the -5. Then we get -5 times x minus 2/5 all raised to the nth power over n. I can rewrite this again as -5 to the n times x minus 2/5 to the n over n, and in this more standard form, it's easy to recognize that the center is 2/5. Another way to find the center is just to figure out the value of x that makes terms go to 0. So in our case, if we want -5x plus 2 to equal 0, we need x to equal 2/5. And therefore, 2/5 must be the center, like we found before. In any case, our series converges for x equals 2/5 for sure, but it might converge for other values of x. So let's use the ratio test to find other values of x that make the series converge. We start off the same way as usual by taking a limit of a ratio of the n plus 1th and nth terms. And then we simplify by flipping and multiplying. And after canceling, we get the limit of -5x plus 2 times n over n plus 1. As n goes to infinity, n over n plus 1 goes to 1. And -5x plus 2 doesn't depend on n, so this final limit is just the absolute value of -5x plus 2. So by the ratio test, our series converges when this limit is less than 1. And it diverges when the limit is greater than 1. The ratio test is inconclusive when the absolute value of negative 5x plus 2 is exactly equal to 1. So we'll worry about that case later. Let's solve the first absolute value inequality. When the absolute value of something is less than 1, that means that the quantity inside the absolute value sign has to be between 1 and negative 1. So we can rewrite the absolute value inequality as negative 1 is less than negative 5x plus 2, which is less than 1. We can solve this for x by subtracting 2 and dividing by negative 5. Dividing by a negative number reverses the direction of the inequality signs. So we have that our series converges for these values of x. Now let's solve the second absolute value inequality, the one that tells us where the power series diverges. The series diverges when the absolute value of negative 5x plus 2 is greater than 1. When the absolute value of something is greater than 1, that means that whatever's inside the absolute value sign has to either be less than negative 1 or greater than 1. So we can replace our absolute value inequality with two inequalities. Negative 5x plus 2 is less than negative 1, or negative 5x plus 2 is greater than 1. Let's solve these inequalities by subtracting 2 and dividing by negative 5, and similarly on the other side. So our series diverges when x is greater than 3/5 or less than 1/5. That makes sense. It's kind of the opposite of where it converges because we were solving an absolute value inequality with the opposite inequality sign. Putting all this information together, we see that our series converges when x is between 1/5 and 3/5, and diverges on either side of this interval. We still don't know what happens when x is exactly equal to 1/5 or exactly equal to 3/5, since those values correspond to the case when the ratio test is inconclusive. So let's turn our attention to the x values of 1/5 and 3/5 next. Let me write down our original power series. It was the sum from n equals 1 to infinity of negative 5x plus 2 to the n over n. If we want to know if this power series converges at x equals 1/5, let's just plug in x equals 1/5. This simplifies to the sum of 1 to the n over n, which is just the regular harmonic series, which diverges. If we plug in x equals 3/5, we get this series, which simplifies to the alternating harmonic series. So it converges. So now we know that the series converges when x equals 3/5 and diverges when x equals 1/5. And our final answer is that the power series converges on the interval from 1/5 to 3/5, where we use an open bracket to denote that we exclude the endpoint 1/5 because the series diverges there, and the closed bracket, square bracket, means that we include the endpoint of 3/5 where the series does converge. I want to make one more observation before we leave this example. Notice that the midpoint of this interval is the number 2/5. Remember, at the beginning of the problem, we calculated the center of the power series, and it was also 2/5. We'll see in a moment that this is no coincidence. In fact, the interval of convergence is always centered at the center of the power series. And we could, in fact, describe the interior of this interval of convergence as the x values for which x minus that center is less than 1/5. That is, all x values within a distance of 1/5 from the interval center. We've seen 3 examples of power series, and each one converged in a very different way. In general, it turns out that there are only these 3 different types of convergence that we've already seen. It's possible, like we saw in the first example, that a series might converge only at its center. It's also possible that a power series could converge for all values of x. This is what happened in our second example. But if neither of these 2 cases hold, then the only other possibility is that there exists a number r such that our series converges anytime we're within r units from the center A. And the power series diverges for any x values that are more than r units from the center A. In symbols, I can write there exists a number r such that the power series converges when the absolute value of x minus a is less than r, and diverges when the absolute value of x minus a is greater than r, since the absolute value of x minus a represents the distance between x and a. This was the situation we saw in our third example. Now in the first case, we say that the radius of convergence of the power series is 0. In the second example, we say the radius of convergence is infinity. And in the third example, we say the radius of convergence is r, since r represents the distance from the center of the interval, sort of like the radius of a circle represents the circle's distance from the center. Now the interval of convergence is the interval of all x values for which the power series converges. So in our first situation, the interval of convergence is just the number a. It's not really an interval, just a single number, but we call it the interval of convergence anyway. In the second situation, our interval of convergence is the interval from negative infinity to infinity. And then the third situation, the interval of convergence includes this entire interval here that extends from the number a minus r to the number a plus r. So our interval could be the open interval a minus r to a plus r, but it could also include one or more endpoints. So it could be the closed interval, or it could just include the left endpoint, or just the right endpoint. In this video, I worked out some examples using the ratio test to figure out what x values make a power series converge. I also stated the fact that there are only 3 options for convergence of a power series: convergence at the center only, convergence for all real numbers, and convergence on some finite interval centered at the center of the power series. This video gives an example of computing the interval of convergence and the radius of convergence for a power series. To compute the radius of convergence and interval of convergence for this power series, we start by using the ratio test. So we need to find the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, where the a sub n's are the terms. For this power series, we can compute a sub n plus 1 by just plugging in n plus 1 everywhere we see an n in this expression. So that's negative 4 to the n plus 1 times x minus 8 to the 2 times quantity n plus 1 divided by n plus 1. We divide all that by the a sub n term, which is just negative 4 to the n, x minus 8 to the 2n over n, which I've just copied from the formula here. Now I'm going to simplify. I'll flip and multiply. And now I'm going to rearrange terms so that corresponding terms are on top of each other. So I'm going to write negative 4 to the n plus 1 over negative 4 to the n times x minus 8 to the 2 quantity n plus 1, that's the same thing as 2n plus 2 over x minus 8 to the 2n, and then I'll write the n and n plus 1, so that's n over n plus 1. Once I cancel terms, I get the limit of negative 4 times x minus 8 squared times n over n plus 1. Now as n goes to infinity, n over n plus 1 is going to 1. And the absolute value of negative 4 is just 4, and the absolute value of x minus 8 squared is just going to be x minus 8 squared, since this expression is always positive. So we have our limit, and the ratio test says the series will converge where this limit is less than 1. So next, let's set 4 times x minus 8 squared to be less than 1 and solve for x. In other words, x minus 8 squared is less than 1/4. Now we can't solve this quadratic inequality by taking the square root of both sides. That would lead something like x minus 8 is less than plus or minus the square root of 1/4, which doesn't even make any sense, and it's not true. What we can do instead is solve the quadratic equation x minus 8 squared is equal to 1/4, and then use some logic to figure out the inequality. So now that we have an equation sign, we can take the square root of both sides to get x minus 8 is equal to plus or minus the square root of 1/4. In other words, x minus 8 is plus or minus 1/2. So in other words, x is equal to 8 plus 1/2 or 8 minus 1/2. That's either 17/2 or 15/2. Now let's go back to the inequality that we're interested in. Since we know that x minus 8 squared is equal to 1/4 at x values of 15/2 and 17/2, we can test to see whether x minus 8 squared is bigger or smaller than 1/4 by plugging in values in between these numbers. So when x is less than 15/2, just by plugging in a sample value like 0, we can see that x minus 8 squared will be bigger than 1/4. While when x is between 15/2 and 17/2, say at a value of 8, we can plug in 8 and for x and see that 8 minus 8 squared, which is 0, is going to be less than 1/4. And finally, plugging in a value of x over here, maybe something like 10 for x, we're going to get a value of x minus 8 squared that is, again, bigger than 1/4. So putting this together, we can see that x minus 8 squared is less than 1/4 when x is between 15/2 and 17/2. So by the ratio test, our series converges for x between 15/2 and 17/2. The ratio test also tells us that the series diverges when this expression is greater than 1. In other words, x minus 8 squared is greater than 1/4. In other words, for x values less than 15/2 or greater than 17/2. Now the only thing we still need to figure out is what happens at the endpoints of the interval 15/2 to 17/2. Recall that our series was given by this formula. So when x is equal to 15/2, we have negative 4 to the n, 15/2 minus 8 to the 2n over n, which is equal to negative 4 to the n, negative 1/2 to the 2n over n, which I can rewrite as negative 1 to the n times 4 to the n times negative 1 to the 2n over 2 to the 2n divided by n, which is the same thing as negative 1 to the n, 4 to the n, negative 1 to the 2n divided by n times 2 squared to the n. Since 2n is always even, negative 1 to the 2n is always equal to 1. And since 2 squared is 4, this 4 to the n on the denominator cancels with the 4 to the n on the numerator. So I'm left with the alternating harmonic series, which we know converges. So the series converges for x equal to 15 halves. Now when x equals 17 halves, we can go through the same computation, just using 17 halves in place of 15 halves. That changes the negative 1/2 here to a positive 1/2. And now we have a positive 1 to the 2n, which is still always 1. Everything else works the same, and so we still have a convergent series. So going back up to the top, we know that the series actually converges for x greater than or equal to 15 halves and less than or equal to 17 halves. That is our interval of convergence. Closed bracket, 15 halves to 17 halves, closed bracket. Notice that the interval of convergence has length 1, because 17 halves minus 15 halves, the difference of the two endpoints, is 2 halves, which is 1. Also, the interval of convergence has center of 8, because the average of the endpoints, 17 halves plus 15 halves over 2, is equal to 8. This should come as no surprise, because our original series was centered at 8. So if we draw our interval of convergence on the number line, it's centered at 8, and it extends out a total distance of 1 unit. In other words, it extends out by half a unit on either side, and so the radius of convergence is the length of the interval divided by 2, or 1/2. So we found the radius of convergence, and we found the interval of convergence, which was this closed interval here, and so that completes the problem. In this video, I'll prove some of the key facts about convergence of power series. My ultimate goal is to prove that there are only 3 possible options for convergence. A power series could converge only at its center. It could converge for all real numbers. And if these 2 options don't hold, then there must exist a number r such that the power series converges for all x within r units away from the center A, and the power series diverges for all x whose distance from A is greater than r. First, I'll prove some preliminary facts. I'll start with this one. If a power series converges when x is equal to b, for some non-zero number b, then it also converges for any x whose absolute value is less than the absolute value of b. To prove this fact, let's assume that the power series converges when x is equal to b. That is, the sum of c sub n times b to the n converges. If a series converges, then the limit of its terms has to equal 0, since if the limit of the terms is not equal to 0, the series would have to diverge by the divergence test. Therefore, by the definition of limit, for any epsilon, there exists a number capital N such that C sub n times b to the n is between 0 plus epsilon and 0 minus epsilon for little n bigger than or equal to capital N. In particular, if we pick epsilon equal to 1, this says there exists a capital N such that negative 1 is less than C sub n times b to the n is less than 1 for little n bigger than or equal to capital N. I can rewrite this statement as the absolute value of C sub n times b to the n is less than 1 for little n bigger than or equal to capital N. Now, if x is any number with absolute value less than the absolute value of b, we can write the absolute value of C sub n times x to the n as the absolute value of C sub n times b to the n times x over b to the n, just using algebra. I can rewrite this as absolute value of C sub n times b to the n times the absolute value of x over b to the n. For little n bigger than or equal to capital N, we know that the absolute value of C sub n times b to the n is less than 1. So this expression has to be less than the absolute value of x over b to the n. Now, if the absolute value of x is less than the absolute value of b, this means that the absolute value of x over b is less than 1. So the series, the sum of absolute value of x over b to the n, is a geometric series whose ratio has absolute value less than 1, so it's a convergent series. Now the ordinary comparison test tells us that the sum of the absolute value of C sub n x to the n also converges, because we know that the terms of that series are less than the terms of our convergent geometric series. Therefore, our original series, the sum of C sub n x to the n, converges absolutely, and therefore converges. So we've proved the first statement. The second statement says that if the power series diverges when x is equal to d for some non-zero number d, then it also diverges whenever we have an x whose absolute value is greater than the absolute value of d. This statement follows directly from the first statement, because suppose we have the sum of C sub n times d to the n diverges. If the absolute value of x is bigger than the absolute value of d, and the sum of C sub n x to the n converged, then by part 1, the sum of C sub n d to the n would have to converge, since the absolute value of d is less than the absolute value of x. But this contradicts the assumption that the sum of C sub n times d to the n diverges, and therefore we know that the sum of C sub n times x to the n must diverge after all. That's all for the proof of facts about convergence of series. In this video, we'll talk about power series as functions. Consider the function defined by f of x is equal to the sum from n equals 0 to infinity of x to the n. This can also be written as 1 plus x squared, and so on. When we think of this as a function, the variable x becomes our independent variable, or input variable. So to figure out the values of f, we can plug in numbers for x and evaluate. Please pause the video and calculate f of 1/3. F of 1/3 is equal to 1 plus a third squared, and so on. This is a geometric series, so it adds up to the first term, 1, divided by 1 minus the ratio of 1/3. And that simplifies to 3/2. Next question, what's the domain of f of x? We can think of the domain of a function as the values of the input variable x that give us a real number as output. Please pause the video to write down your answer for the domain of f of x. The series, the sum of x to the n, converges when x is between -1 and 1. So for these values of x, we get a finite real number as our answer for f of x. Also, the series diverges for other values of x. So we don't get a real number answer when we plug in values of x less than or equal to -1 or greater than or equal to 1. Therefore, the domain of f of x is the set of x values for which -1 is less than x is less than 1. Or in interval notation, we can write this as the interval from -1 to 1. And in general, the domain of a power series is exactly the set of values where it converges. By a closed form expression for f of x, I mean an expression that doesn't involve a summation sign. I can write the sum of x to the n without the summation sign by using the geometric series formula. The first term is 1 divided by 1 minus the common ratio of x. This holds for all x values between -1 and 1, as usual, where the geometric series converges. Therefore, I can write f of x as 1 over 1 minus x for x values in that interval. Notice that if I just looked at the function g of x equals 1 over 1 minus x out of context, it would have domain spanning from -infinity to 1 together with the interval 1 to infinity, because this function g of x is defined for all x values that are not equal to 1. So f of x and g of x are not exactly the same function. They have different domains, but they are exactly equal on the interval from -1 to 1. And we say that the function g of x is represented by the power series, the sum from n equals 0 to infinity of x to the n. If we want to be more precise, we can say it's represented by this power series for x between -1 and 1. We can think of the partial sums of this series, sum of x to the n, as a way to approximate the function 1 over 1 minus x with polynomials. Please pause the video and write out the first few partial sums. Your answers should have x's in them. S sub 0 is just the 0th term 1. S sub 1 is 1 plus x, and so on. S sub n is 1 plus x plus all the way up through x to the n, an nth degree polynomial. In this figure, I've drawn the function 1 over 1 minus x in blue, and I've drawn the first partial sum, the linear function 1 plus x, in orange. Notice that these two functions are close to each other when x equals 0, but get farther away from each other when x is far from 0. In this graph, I've added the next partial sum, S2, which is a degree 2 polynomial, a quadratic. Here I've got partial sums through S4, and here I've got partial sums through about S12. The original function, 1 over 1 minus x, is here in blue. I'll mark over it. And you can see that these partial sums are becoming very good approximations to that original function on the interval from -1 to 1. Now, outside that interval, for example, for x values below -1, our partial sums deviate wildly from our original function. I want to show one more graph. In this graph, the function 1 over 1 minus x is shown in blue, and the graph of the power series, the sum of x to the n, is shown in orange. The blue function is actually obscured by the orange function because the two functions are identical for values of x between -1 and 1. The only difference between these two functions, as discussed before, is that the function 1 over 1 minus x is defined for all x values except for the x value of 1. And that's why we can see the blue graph even when x values are less than -1. However, the function given by this power series has domain in between -1 and 1, and so it only exists here in between those x values. In this video, I talked about representing the function 1 over 1 minus x with the power series, the sum from n equals 0 to infinity of x to the n. These two expressions are equal for x values between -1 and 1, where the power series converges. I also used a graph to give an idea of what this equation means. The partial sums, drawn in various colors, give excellent approximations to the original function, drawn in blue, on the interval of x values between -1 and 1. Since the partial sums are polynomials, this gives us a way to approximate this rational function with simple polynomial equations. The idea of approximating functions with polynomials is a very important idea that we'll see again and again. This video is about rewriting functions in terms of power series. All the examples that we'll do in this section will be based on the formula for the geometric series, the fact that the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x for x between -1 and 1. We want to express the function 2 over x minus 3 as a power series, and we want to do this by using the geometric sum formula. The trick here is going to be to rewrite 2 over x minus 3 so it looks more like 1 over 1 minus something. Then we can treat whatever that something is as x and plug into the formula to get a power series. So that's the idea. Now I'm starting with 2 over x minus 3. And I don't really like the x minus 3. I'd rather this was 3 minus x, because that reminds me more of 1 minus x. So I could rewrite it like this, but my two expressions now aren't equal. This one's the negative of this one, so I can fix that by just sticking a negative sign out in front. Now my two expressions are equal because I've just multiplied my first expression by -1 over -1 to get this expression. But I still don't really like the 3 minus x. I wish that were 1 minus x. It'd be nice if I could just divide the 3 by 3 to get 1, but in order to leave the expression unchanged, I'm going to need to divide everything by 3, both the top and the bottom. This gives me -2/3 divided by 3 minus x over 3, which I can also write as -2/3 times 1 minus x over 3. Now if I bring the -2/3 out front, I have -2/3 times 1 over 1 minus x over 3. Using my geometric sum formula, this is the same as -2/3 times the sum from n equals 0 to infinity of x over 3 to the n. I'm just plugging in x over 3 for x in this formula. I've now found a power series representation, but I'm going to clean it up a little bit and make it look more standard. I'll bring the -2/3 into the summation sign and distribute my exponent to get x to the n over 3 to the n. And now I can rewrite this as -2 over 3 to the n plus 1 times x to the n. To figure out the interval of convergence for this power series, there are two different approaches that I could take. First, I could do a standard computation using the ratio test. I'll let you work out the details yourself, but you should get that the radius of convergence is 3 and the interval of convergence is from -3 to 3. A second approach to finding the interval of convergence is to look at the history of how we made the power series. Our basic template power series was the sum from n equals 0 to infinity of x to the n, which converges when x is between -1 and 1. We then plugged in x over 3 for x. Well, this should converge when x over 3 is between 1 and -1. In other words, when x is between 3 and negative 3. Finally, we multiplied that series by negative 2/3. This doesn't change the interval of convergence. So the interval of convergence for our final power series is the interval between negative 3 and 3, just like you could have gotten from the ratio test. As a second example, let's find a power series representation of x over 1 plus 5x squared. Again, we want to use the geometric series summation formula. So we want to make this expression look more like 1 over 1 minus something. Well, 1 plus 5x squared is the same thing as 1 minus 5x squared. So if I just wanted a power series for 1 over 1 plus 5x squared, I could do that easily by using the geometric sum formula and getting the sum from n equals 0 to infinity of minus 5x squared to the n. All I'm doing here is plugging in negative 5x squared for x in this formula. Since I want a power series for x over 1 plus 5x squared instead, I can just multiply everything by x. Again, I'd like to clean things up and make this expression look more like a standard power series. So I'll drag the x inside the summation sign. I can do that because the summation is over n, which has nothing to do with x. Now I can use my laws of exponents to rewrite this as negative 1 to the n, 5 to the n times x to the 2n. Now x times x to the 2n is equal to x to the 2n plus 1, and so this gives me a good power series representation for my function. Although the problem didn't explicitly ask for it, it's a good idea to compute the interval of convergence to see for what values of x this equation actually holds. I'll use the history approach. We started with our old familiar power series, which converges when x is between 1 and negative 1. We plugged in negative 5x squared for x, so that converges when negative 1 is less than negative 5x squared is less than 1, which is equivalent to the inequality 1/5 is greater than x squared, which is greater than negative 1/5. Notice that I had to flip around the inequality signs when I divided by negative 5. Looking at a graph of y equals x squared, I can see that x squared is between negative 1/5 and 1/5 for x values corresponding to this section of the graph that I'm drawing here in green, or this interval of x values on the x-axis that I'm drawing in pink. To find the endpoints of this pink interval, I just need to find where x squared is exactly equal to 1/5, which is when x is equal to plus or minus the square root of 1/5. So the x values that satisfy my inequality are the x values in between these two values. I have negative the square root of 1/5 is less than x is less than the square root of 1/5. Now the last step in my history is when I multiplied everything by x. This doesn't change my interval of convergence, which remains this interval here. In this video, I represented several functions with power series using the geometric series summation formula. Although only a limited class of functions can be handled using this formula, some of the techniques that I used in the process, like multiplying my whole power series by x or plugging in an expression for x, some of those techniques can be used in a much broader context to represent many different kinds of functions as power series, as we'll see. Up to now, we've only been able to calculate the sum of a few very specific series, like geometric series and some telescoping series. In this video, we'll see how to use Taylor series to find the sums of other series. Let's start by finding the Taylor series for arctan of x centered at x equals 0. Since arctan of x is equal to the integral of 1 over 1 plus x squared, one easy way to find the Taylor series for arctan of x is to build it up, starting with the formula for a geometric series. 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. Now 1 over 1 plus x squared is equal to 1 over 1 minus negative x squared, so I can plug negative x squared in for x in this power series. And I get the sum from n equals 0 to infinity of negative x squared to the n, which simplifies to the sum from n equals 0 to infinity negative 1 to the n, x to the 2n. Therefore, arctan of x, which is the integral of 1 over 1 plus x squared dx, is going to be equal to the integral of this power series, at least up to a constant. I can integrate this power series term by term to get the sum of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 plus a constant. To figure out the constant c, I can plug 0 in for x on both sides of my equation. Since all of my powers of x involve a positive power of x, even when n equals 0, I've got x to the 1. So there's always at least one copy of x there. So if I plug in x equals 0, all of these terms go to 0, and arctan of 0 is also 0. So plugging in x equals 0 gives me 0 equals the sum of a bunch of zeros plus c. In other words, the constant is 0. Therefore, this expression right here gives me a Taylor series representation of arctan. Let's take a moment to figure out which x values this equation is actually true for. We know that the geometric series formula holds for x values between negative 1 and 1, not including the endpoints. Therefore, when I plug in negative x squared for x, I get an equation that holds for negative x squared between 1 and negative 1, which is equivalent to saying that x is between 1 and negative 1. And when I take the integral of both sides, I still get an equation that holds true for x between negative 1 and 1. So I'm guaranteed that this equation up here holds for x values between negative 1 and 1. But in fact, it's not hard to check that this series actually converges at the endpoints of negative 1 and 1. This follows from the alternating series test, since when we plug in x equals negative 1 or x equals 1, either way we get an alternating series that converges. So this series converges on the closed interval from negative 1 to 1, and it's equal to arctan on that open interval. In fact, it turns out that it's equal to arctan even on the closed interval. In particular, the equation holds for x equal to 1. When x is equal to 1, then I plug into the equation to get that arctan of 1 is equal to the sum from n equals 0 to infinity, negative 1 to the n, times 1 to the 2n plus 1, that's just 1, over 2n plus 1. I can rewrite that. Now, arctan of 1 is the angle whose tangent is 1. So arctan of 1 is going to be pi over 4. In other words, I now have a series that sums to pi over 4. Let's write out the first few terms of this series and see what it looks like. The first term is 1, the next term minus a third, plus a fifth, minus a seventh, plus a ninth, and so on. In other words, multiplying both sides by 4, we get that pi is equal to 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths minus 4 elevenths, and so on. If you've ever wondered how to generate digits for pi, Here's one way. We've found the sum of kind of a natural series to look at, and we've found a beautiful formula for pi. For the next example, let's start by finding the Taylor series for f of x equals ln x centered at x equals 1. We can write out the pattern of the function and its derivatives, and we soon notice that the nth derivative will have negative 1 to the n minus 1 times n minus 1 factorial times x to the n. Since we're centering at x equals 1, we'll plug in 1 and get the nth derivative of f at 1 is equal to negative 1 to the n minus 1 times n minus 1 factorial. Therefore, the Taylor series for ln of x will be the sum from n equals 0 to infinity of f to the n at 1 over n factorial times x minus 1 to the n. Since this pattern for the nth derivative of f really only works starting with the first derivative, not with the 0th derivative, I'm going to split out the first term, which is just going to be ln of 1, which is actually 0, and then all the other terms follow the same pattern, and we have negative 1 to the n minus 1 times n minus 1 factorial divided by the n factorial times x minus 1 to the n. This simplifies to ln of x is equal to the sum from n equals 1 to infinity of negative 1 to the n minus 1 times x minus 1 to the n over n, since the n minus 1 factorial cancels with almost all of the n factorial, leaving just the factor n in the denominator. So I now have a formula for the Taylor series for ln of x. It's easy to check using the ratio test that this power series has a radius of convergence of 1, and so it converges when x minus 1 is between 1 and negative 1. In other words, when x is between 0 and 2. And although I won't prove it here, it turns out that this Taylor series really does converge to its function, ln of x, and in fact, it converges to ln x on the interval for x greater than 0 and less than or equal to 2. Now, if I plug in x equal to 2 into my equation, I get something interesting. I get that ln of 2 is equal to the sum from n equals 1 to infinity of negative 1 to the n minus 1 of 2 minus 1 to the n. Well, that's just 1 to the n, which is just 1. And so I get ln of 2 is equal to the sum of negative 1 to the n minus 1 over n. That should be looking familiar to you, and yes, it's true. This is just the alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4, and so on. So Taylor series has given us the sum of the alternating harmonic series, and it is ln of 2. In this video, we use Taylor series to find the sum of the alternating harmonic series. We also used Taylor series for arctangent to find that the sum of a different series is actually equal to pi. As you get more familiar with Taylor series, you'll be able to calculate the sum of other series by recognizing them as the series that you get by plugging in a certain value of x into the Taylor series of a particular function. For example, if you see the series 1 plus 1 over 2 plus 1 over 3 factorial plus 1 over 4 factorial, and so on, you might recognize that as the number 1 plugged into the formula for the Taylor series of e to the x. In other words, this series is equal to e to the 1, which is e. For any function f of x whose derivatives all exist, we can write down the Taylor series for f of x, centered at x equals a, by using this formula. But just because we can write the Taylor series down doesn't guarantee that the Taylor series actually converges to the function we started with. In this video, we'll address the questions of when can we be sure that the Taylor series converges to its function, and when the Taylor series does converge, how good is the approximation by Taylor polynomials, or partial sums? In other words, how big is the remainder? The answer to the question, does the Taylor series always converge to the function it's made from, is unfortunately no. Sometimes the radius of convergence is 0, and sometimes, even though the radius of convergence is large or even infinite, the Taylor series converges, but it converges to the wrong function. Here's an example of the second situation. If we look at this piecewise defined function, g of x is defined as e to the minus 1 over x squared if x is not 0, and it's defined so that it's continuous at 0 to be 0 when x equals 0. It's possible to work out the value of g prime at 0 using the limit definition of derivative. G prime of 0 is the limit as h goes to 0 of g of 0 plus h minus g of 0 over h, which is the limit as h goes to 0 of e to the minus 1 over h squared minus 0 over h. I'll rewrite this as the limit as h goes to 0 of 1 over h divided by e to the 1 over h squared. As h goes to 0 from the positive side, this is an infinity over infinity indeterminate form. And as h goes to 0 from the negative side, this is a negative infinity over infinity indeterminate form. In either case, we can use L'Hopital's rule to replace this limit with the limit of the derivatives, which simplifies to a 0 over infinity kind of limit, which is equal to 0. In a similar way, it's possible to prove that the second derivative of g at 0 is also 0, and so is the third derivative, and so are all the derivatives of g at 0. Therefore, if we write out the Taylor series, it's just the sum of a bunch of zeros, or the zero function. Certainly, this Taylor series converges for all x, but it converges to the constant zero function. And that's different from the function that we started with. In fact, the function that we started with, g of x, is not 0 for any x except x equals 0. So the Taylor series only matches the function at the single point x equals 0 and nowhere else. We found an example where the Taylor series converges, but not to its function g of x. Fortunately, this behavior doesn't happen for most of the functions that we typically deal with. To understand better which Taylor series are guaranteed to converge to their functions, let's take a look at the idea of remainders. For a function f of x and its Taylor series t of x, the remainder is written r sub n of x equals f of x minus t sub n of x, where t sub n of x is the nth degree Taylor polynomial. This can be expanded out as follows. Previously, when we looked at remainders for series, we wrote that the remainder was the infinite sum, which I'll call S infinity, minus the nth partial sum. The analogous expression for Taylor series might be the entire Taylor series minus the first terms up through the degree n term, but that's not what we define the remainder to be for Taylor series. Instead, the remainder for Taylor series is the difference between the function and the first terms up to the degree n term. The reason it's defined a little bit differently is because for Taylor series, we're super interested in the Taylor series converging to its function, and it's of less interest whether or not the Taylor series happens to converge to its infinite sum. Because we define the remainder as the difference between the function and its nth Taylor polynomial, it follows directly that the Taylor series for f of x converges to f of x in an interval around a, if and only if the limit of the remainders is 0 in this interval. To see this, just note that the limit, as n goes to infinity, of the Taylor series equals f of x, that's what it means to converge to f of x, if and only if f of x minus this limit is equal to 0. We can rewrite this as the limit as n goes to infinity of f of x minus the limit as n goes to infinity of Tn of x equals 0, since the limit as n goes to infinity of f of x is just f of x. There's no n's in this expression. Using limit laws, we can rewrite this again as the limit of the quantity f of x minus Tn of x equals 0, but that's just the same thing as saying that the limit of the remainders is 0, by definition of remainders. So we restated the question about when does a Taylor series converge to its function as a question about when does the limit of the remainders equal 0. Taylor's inequality gives us a bound on these remainders that can help us answer the question of when the remainders limit to 0. This bound can also be a useful way to answer the question of how close is the approximation when we use Taylor polynomials to approximate a function. Here are some details about when this bound holds. Suppose there's a number capital M such that the n plus 1th derivative of x has magnitude less than or equal to capital N for all x's within a distance d of the center A. As a graph, this means that there's a number capital M, and for all x's within a distance d of the center A, the graph of the n plus 1th derivative of f lies between negative m and m. So if such a number m exists, then the remainder r sub n of x of the Taylor series satisfies the inequality that the magnitude of r sub n of x is less than or equal to this bound capital M divided by n1 plus 1 factorial times the absolute value of x minus a to the n plus 1th power for all x's in this interval of length 2d that we're talking about. Now in the statement of Taylor's inequality, the number m can be chosen just to work for a particular derivative. But really nice things can happen if we are able to choose the same number of m to work for all derivatives, for all values of little n. In fact, if all derivatives are bounded by the same value, capital M, then we can guarantee that the Taylor series converges to the function. That gives us a nice practical convergence criterion that I'll show you on the next slide. The practical convergence condition says that if there's a number capital M such that the magnitude of the nth derivative at x is less than capital M for all numbers x in a certain interval around the center and for all numbers n, then the Taylor series for f of x converges to f of x for x's in that interval. I'll represent the convergence condition visually. This time we're agreeing that all the derivatives are within this bound. So the original function lies within this bound, and its derivative lies within this bound, and the second derivative lies within this bound. These are not necessarily accurate representations of the derivatives, but that's the idea. So as long as the bound holds for all the derivatives, then the Taylor series converges to the function. And it's not too hard to prove this practical convergence criteria from Taylor's inequality. Remember that Taylor's inequality says that because of this bound m, the nth remainder is bounded by m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. But it's a fact that the limit as n goes to infinity of m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 is equal to 0. And it's not hard to prove this fact by looking at the series and using the ratio test to show that the series converges. I'll leave that as an exercise for the viewer. Therefore, by the divergence test, we know that the limit of the terms has to be 0, which is what we want. Now, because the limit of this expression is 0, by the squeeze theorem, the limit of the RNs has to be 0 as well, which means that the Taylor series converge to the function. This practical convergence criterion is a very good way to show that Taylor series converge to their function. But even if it doesn't hold, it's still possible that the Taylor series may converge to its function, or in some cases it may not. Let's use this practical convergence condition to prove that the Taylor series for sine x converges to sine x. Recall that the Taylor series for sine x is given by this equation. And recall also that any nth derivative of x for f of x equals sine x will have to be of the form sine x or negative sine x or cosine of x or negative cosine of x. That's simply because when we take repeated derivatives of sine and cosine, the values cycle around in between those 4 possible answers. Now, since the absolute value of sine x is always less than 1 or equal to 1, and same thing for cosine, we know that the nth derivative of our function has to be bounded by 1. So we'll let m be 1, and this bound holds for all x values, all real numbers. Therefore, we know that the Taylor series converges to the function sine of x for all values of x. We've used the practical convergence condition with m equals 1 to prove this. In this video, we defined the nth remainder for a Taylor series as the difference between the function and its nth Taylor polynomial. We also gave a bound on the size of the nth remainder. It's always less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1, where m is a bound on the size of the n plus 1th derivative of x for x within some distance d of a. Because of this formula for the nth remainder, known as Taylor's inequality, we can show that if the nth derivative of x is always bounded by the same m for all x within a certain interval around a and for all values of n, then the Taylor series converge to its function. This video introduces the idea of parametric equations. Instead of describing a curve as y equals f of x, we can describe the x-coordinates and y-coordinates separately in terms of a third variable, t, usually thought of as time. So we can write x as a function of t and y as a separate function of t. This is especially useful as a way to describe curves that don't satisfy the vertical line test and therefore can't be described traditionally as functions of y in terms of x. A Cartesian equation for a curve is an equation in terms of x and y only. Parametric equations for a curve give both x and y as functions of a third variable, usually t. The third variable is called the parameter. As our first example, let's graph the parametric equations given here on an xy coordinate axis. We'll do this by finding x and y coordinates that correspond to the same value of t. For example, when t is -2, you can calculate that x, by plugging in -2 for t, gives you 5, and y, when you plug in -2 for t, gives you 8. Please pause the video for a moment and fill in some additional values of x and y for some additional values of t. Your chart should look like this. And when we plot the xy pairs and connect the dots, we get something like this. Notice that this point over here corresponds to a t-value of -2, and this point over here corresponds to the t-value of 2. So if we think of t as time, we're traversing the curve in this direction. To find a Cartesian equation for this curve, we need to eliminate the variable t from these equations. One way to do this is to solve for t in one equation, say the first equation. So 2t is equal to 1 minus x, which means that t is 1/2 minus x over 2. Then we can plug that expression for t into the second equation and get y equals 1/2 minus x over 2 squared plus 4, which simplifies to the quadratic equation y equals 1/4 x squared minus 1/2 x plus 17/4. Let's try some more examples. A table of values for the first example helps us draw the familiar graph of a circle of radius 1. This should come as no surprise, since the equations x equals cosine t and y equals sine t are familiar from trig as a way of describing the x and y coordinates of a point on the unit circle. Notice that when t equals 0, our curve lies on the positive x-axis, and as t increases from 0 to 2 pi, we traverse the curve once in the counterclockwise direction. A Cartesian equation for this unit circle is given by the equation x squared plus y squared equals 1. This follows from the trig identity cosine squared t plus sine squared t equals 1 by substituting in x for cosine t and y for sine t. Please pause the video for a moment to graph the second curve and rewrite it as a Cartesian equation. A table of values should help you see that the graph is again a unit circle, but this time, as t increases from 0 to 2 pi, we actually traverse the circle twice in the clockwise direction. I'll draw this with a double arrow moving clockwise. The Cartesian equation for this graph is still x squared plus y squared equals 1. And so we found two different parameterizations for the same graph on the xy axis. Let's take a look at the third equation. There's no interval of values specified for t here, so let's just assume that t can be any real number. Now, as t ranges from -infinity to infinity, our y values, which are given by cosine t, oscillate between 1 and -1. Our x values are always the square of our y values. So the graph of this curve has to lie on the graph of x equals y squared, which is a sideways parabola. But our parametrically defined curve doesn't cover this whole parabola. Remember that y is given by cosine of t, so y can only range between -1 and 1. And so we're only getting the portion of the parabola that I shade in here. As t varies from, say, 0 to pi, I traverse this parabola one time. And then as t goes from pi to 2 pi, I go back again in the other direction. And as t continues to increase, I traverse this parabola infinitely many times. The Cartesian equation for this curve is the equation x equals y squared, with the restriction that y is between -1 and 1. We've seen several examples where we went from parametric equations to Cartesian equations. Now let's start with a Cartesian equation and rewrite it as a parametric equation. In this example, y is already given as a function of x. So an easy way to parameterize this curve is to just let x equal t, and then y is equal to the square root of t squared minus t, substituting in t for x. The domain restriction in terms of x just translates into a restriction in terms of t. I call this the copycat parameterization, since we've successfully introduced the new variable t, but t just copies whatever x does. In the second example, we could try setting x equal to t. Then we get 25t squared plus 36y squared is equal to 900. And solving for y, we'd have y squared equals 900 minus 25t squared over 36. So y is plus or minus the square root of this quantity. This is a very awkward looking expression. In fact, y is not even a function of t here because of the plus and minus signs. So let's look for a better way to parameterize this curve. Because of the x squared and the y squared, this equation is a good candidate for parameterizing using sine and cosine. In fact, if we divide both sides of the equation by 900, we get 25x squared over 900 plus 36y squared over 900 is equal to 1, which simplifies to x squared over 36 plus y squared over 25 is equal to 1. If I rewrite this as x over 6 squared plus y over 5 squared equals 1, then I can set x over 6 equal to cosine of t and y over 5 equal to sine of t, and I can see that for any value of t, x over 6 and y over 5 will satisfy this equation simply because cosine squared plus sine squared equals 1. This gives me the parameterization x equals 6 cosine of t, y equals 5 sine of t, which is a handy way to describe an ellipse. As a final example, let's describe a general circle of radius r and center hk. For any point x, y on the circle, we know that the distance from that point x, y to the center of the circle is equal to r. So using the distance formula, we know that the square root of x minus h squared plus y minus k squared has to equal r. Squaring both sides, this gives us the equation for the circle in Cartesian coordinates. So for example, if our circle has radius 5 and has center at the point -3, 17, then its equation would be x minus -3, that's x plus 3 squared, plus y minus 17 squared is equal to 25. One way to find the equation of a general circle in parametric equations is to start with the unit circle and work our way up. We know that the unit circle, with radius 1, centered at the origin, is given by the equation x equals cosine t and y equals sine t. If we want a circle of radius r centered around the origin instead, then we need to expand everything by a factor of r. So we multiply our x and y coordinates by r. If we now want the center to be at hk instead of at the origin, then we need to add h to all our x coordinates and add k to all our y coordinates. This gives us the general equation for a circle in parametric equations to match the Cartesian equation above. We can write our same example circle in parametric equations as x equals 5 cosine t minus 3, y equals 5 sine t plus 17. In this video, we translated back and forth in between Cartesian equations and parametric equations, with a special emphasis on the equations for circles. This video is about finding the slopes of tangent lines for curves defined parametrically. To find the slope of the tangent line for a curve y equals p of x, given in ordinary Cartesian coordinates, we just take dy dx. Or, equivalently, we calculate p prime of x. If the curve is defined parametrically by the equations x equals f of t, y equals g of t, to find the slope of the tangent line, we still want to find dy dx. But since our curve is given parametrically, we don't have ready access to dy dx. Instead, we'll need to calculate it from dy dt and dx dt, which are easy to get from our parametric equations. To relate dy dx to dy dt and dx dt, we just need to use the chain rule. Recall that the chain rule says that dy dt is equal to dy dx times dx dt. So, rearranging, we know that dy dx is equal to dy dt divided by dx dt. And that's how we'll calculate the slope of our tangent line. We can write this formula equivalently as dy dx is equal to g prime of t over f prime of t. Now let's use these formulas in an example. For the Lissajous figure given by these equations and drawn below, let's find the slopes of the tangent lines at the center point with x and y coordinates of 0, and let's find the way the tangent line is horizontal. The slope of the tangent line is given by dy dx, which is dy dt divided by dx dt. Now dy dt is going to be cosine of 2t times 2, and dx dt is going to be negative sine of t. Taking the ratio, we see that dy dx is twice cosine of 2t over negative sine of t. Now we want to calculate this slope not when t is 0, but when x and y are 0. X is 0 when cosine of t is 0, which is when t is pi over 2 and 3 pi over 2. Those are the only t values that work in the interval of t values that we're interested in. And it's easy to check that when t has these values, then y, which is sine of 2t, is also going to be 0. So we want to calculate dy dt at t equals pi over 2 and at t equals 3 pi over 2. Plugging into our formula for dy dx, we get twice cosine of pi divided by negative sine of pi over 2, which simplifies to positive 2. And when t is 3 pi over 2, we get twice cosine of 3 pi over negative sine 3 pi over 2, which simplifies to negative 2. So our tangent lines at the origin have slopes positive 2 and negative 2. Next, let's find where the tangent line is horizontal. From the figure, there should be 4 places. If we set dy dx equals 0, we get that 2 cosine of 2t over negative sine of t needs to be 0, which means that we need cosine of 2t to equal 0, or 2t to equal pi over 2 plus some multiple of pi. Solving for t, we get that t has to equal pi over 4 plus some multiple of pi over 2. There are indeed 4 such values of t in the interval from 0 to 2 pi, and those are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We can find the x and y coordinates of these points simply by plugging in these values of t into our original equations. Here are the xy coordinates of those 4 points. In this video, we saw that for a curve given by parametric equations, the slope of the tangent line is given by dy dx, which is dy dt divided by dx dt. In this video, we'll find the area under a curve defined parametrically. Recall that the area under a curve y equals p of x defined in usual Cartesian coordinates is just the integral from x equals a to x equals b of y dx, or, in other words, the integral from a to b of p of x dx. If instead the curve is given by the parametric equations x equals f of t and y equals g of t, the area is still going to be the integral of y dx, but now y can be written as g of t, and dx is going to be f prime of t dt, using differential notation. Therefore, the area is going to be the integral of g of t f prime of t dt. And since we're integrating with respect to t now, our bounds of integration have to also be t values. I'll still call them a and b, but I want them to represent t values here. It's important to note that this is still the area under a curve. In other words, in between the curve and the x-axis. Let's use this formula to find the area enclosed by this Lissajous figure given by these equations. By symmetry, it's enough to compute the area under one segment of the Lissajous curve and then multiply that area, which I'll call a, by 4. Now a is equal to the integral of y dx, and using our parametric equations, we know that y is sine of 2t and dx is the derivative of cosine, so that's negative sine of t dt. The rightmost point of the section of curve that we're interested in, right here, happens when x is 1 and y equals 0. It's easy to check that that occurs when t equals 0. The leftmost point of the section of curve occurs when x and y are both 0. Setting both our equations equal to 0 and solving for t, we see this happens when t is pi over 2 plus any multiple of pi. So the first time we reach this point after the t value of 0 is when t is simply pi over 2. So we'll set our bounds of integration as from t equals 0 to t equals pi over 2. Plugging this information into our equation, we get that the area is the integral from 0 to pi over 2 of sine of 2t times negative sine of t dt. Let's pull the negative sign out and use the double angle formula to rewrite sine of 2t as 2 sine t cosine t, multiply that by the sine t dt. We can pull the 2 out and rewrite this as sine squared of t cosine t dt, and then a u substitution will allow us to compute the integral. We get negative 2 times the integral from u equals 0 to 1 of u squared du, which integrates to negative 2 u cubed over 3 evaluated between 1 and 0, which is negative 2/3. Notice I get a negative answer here, and that's because I accidentally integrated from right endpoint to the left endpoint instead of from the left to the right. I accidentally followed the t values in increasing order when I should have integrated in the other order in order to make the x values in increasing order. In any case, I can correct this by switching my bounds of integration, or more quickly just by sticking a negative sign in front and changing my sign. Now I can figure out the total area inside the Lissajous figure just by multiplying by 4. In this video, we saw that the area underneath a curve given in parametric equations is given by the integral of y dx, which if x is f of t and y is g of t, this is just the integral of g of t times f prime of t dt. Our bounds of integration need to be t values. In this video, we'll calculate the length of curves given by parametric equations. As a warm-up, let's calculate the length of this curve graph below. Since it's piecewise linear, we can just calculate the length of each linear piece using the distance formula. For example, the length of the first segment is given by the square root of y2 minus y1 squared, that's 3 minus 2 squared, plus x2 minus x1 squared, that's 2 minus 1 squared, which gives us the square root of 2. Similarly, the second piece has length given by the square root of 5 minus 3 squared plus 3 minus 2 squared, which is the square root of 5. We can make similar calculations for the length of the third segment and the fourth segment. Adding these together, we get a total length of twice the square root of 5 plus the square root of 2 plus 2. We can use the same process to approximate the length of any curve by dividing it up into n small pieces, approximating each piece with a straight line, and using the distance formula to find the length of the line segments. If the curve is given by the parametric equations x equals f of t and y equals g of t, then we can write each of these points along the line in terms of f and g. For example, p of I minus 1 we can write as the x-coordinate f of t I minus 1 and the y-coordinate g of t I minus 1. And similarly, pi is going to be x-coordinate f of ti, y-coordinate g of ti. If we think of t as time, then this is just saying that t sub I is the time at which we get to point p sub I. Now the distance formula tells us that the length of the line segment from p sub I minus 1 to p sub I is going to be given by the square root of x2 minus x1 squared, that's f of t sub I minus f of t sub I minus 1 squared, plus y2 minus y1, that's g of t sub I minus g of t sub I minus 1 squared. Now the total length of the curve, which is called the arc length, is going to be approximately equal to the sum of the lengths of these segments. This is starting to look a bit like a Riemann sum, but it's missing the delta t, so I'll fix that by multiplying the numerator and the denominator by delta t. If I suck the delta t from the denominator inside the square root sign, it needs to become a delta t squared, and I get the following expression. If I break up my fractions, I can rewrite this. Now there's something kind of exciting going on. This quotient here looks a lot like a slope. In fact, it's exactly the expression for the slope of the secant line for the function f that we get if we were calculating the derivative of f with respect to t. And similarly, this expression in here is exactly the expression for the slope of the secant line we'd get if we were calculating the derivative of g with respect to t. Because these quotients here are approximately equal to f prime and g prime, or more rigorously because of the mean value theorem, I can replace my expression with f prime of ti star squared and g prime of ti star squared, where ti star is some time in the ith time interval. Now exact arc length is going to be the limit of this expression as the number of intervals goes to infinity. As usual, I can replace the limit of this Riemann sum with an integral, where the bounds of integration are the t values that get me from the start of the curve to the end of the curve. This arc length formula has an alternative form, which is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. And these are my two versions of this very useful formula for arc length. Now let's use this formula to set up an integral to express the arc length of this Lissajous figure. Since dx dt is given by negative sine of t, and dy dt is given by 2 cosine of 2t, our arc length is given by the integral of the square root of sine of t squared plus 2 cosine of 2t squared dt. We do still need to figure out the bounds of integration in terms of t that'll make us wrap around this curve exactly one time. It's easy to check that when t equals 0, x is equal to 1 and y is equal to 0, so we're at this point right here. The next time that we get to this point with an x-coordinate of 1, we need x equal cosine t to equal 1, so the next time will be when t equals 2 pi. Therefore, our bounds of integration are going to be from 0 to 2 pi. It's easy to set up this integral, but it would be very difficult to actually integrate it, and that's often the case with arc lengths. But we could use a calculator or computer to get a numerical approximation of about 9.4. In this video, we derived an equation for arc length. This video introduces the idea of polar coordinates. Polar coordinates give an alternative way of describing the location of points on the plane. Instead of describing a point in terms of its x and y coordinates, those are the Cartesian coordinates of the point, when using polar coordinates, we instead describe the point in terms of a radius r and an angle theta. R is the distance of the point from the origin, and theta is the angle that radius line makes with the positive x-axis. Let's plot these points given in polar coordinates. So the 8 here is the value of the radius, and the negative 2/3 pi is the value of the angle, theta. The negative angle means that I need to go clockwise from the positive x-axis, instead of counterclockwise like I normally would for a positive angle. So here, a negative 2/3 pi means that I need to go to this line right here, and the 8 for the radius means I need to go 8 lines out from the origin, so my point should be around right here. The next point has a radius of 5 and an angle of 3 pi. The angle of positive 3 pi means that I go counterclockwise starting at the positive x-axis. Here I've gone around by 2 pi, and here I've got an extra pi to make 3 pi. Now the radius of 5 means I need to go 5 units out from the origin, so that puts me about right here. Notice that I could have also labeled this point with the polar coordinates of 5 pi. There's more than one way to assign polar coordinates to a point. The next point has an angle of pi over 4 and a radius of negative 12. The negative radius means that I need to jump to the other side of the circle before I plot the point. In other words, instead of plotting the point at an angle of pi over 4 and a radius of 12, which would be about right here, I go to the opposite side of the circle and plot it at the same distance from the origin, but 180 degrees or pi radians around the circle over here. Now I could have also labeled this point using a positive radius of 12 and using an angle of pi over 4 plus pi, or 5 pi over 4. And in general, a point with polar coordinates of negative r theta means the same point as the point with polar coordinates r theta plus pi. Adding pi just makes us jump around to the opposite side of the circle. To convert between polar and Cartesian coordinates, it's handy to use the following equations. First, x is equal to r cosine theta, y is equal to r sine theta, r squared is equal to x squared plus y squared, which means that r is plus or minus the square root of x squared plus y squared, and tangent theta is equal to y divided by x. Let's see where these equations come from. If we draw a point with coordinates x, y, and draw lines to make a right triangle, the height of that triangle is y, the length of the base is x, and the hypotenuse has length r. Theta is the measure of this interior angle. From trig, we know that cosine theta is equal to adjacent over hypotenuse. So that's x over r, which means that x is equal to r cosine theta. Similarly, sine theta is opposite over hypotenuse. That's y over r, which means that y is equal to r sine theta. That gives us the first two equations. The Pythagorean theorem tells us that x squared plus y squared is equal to r squared, and that gives us the third equation. Finally, tangent theta is opposite over adjacent, so that's y over x, which is the fourth equation. To convert 5 negative pi over 6 from polar to Cartesian coordinates, we just use the fact that x equals r cosine theta and y equals r sine theta. So in this case, x is equal to 5 times cosine of negative pi over 6. That's 5 times square root of 3 over 2. And y is equal to 5 sine negative pi over 6. So that's equal to negative 5 halves. To convert negative 1 from Cartesian to polar coordinates, we know that negative 1 and negative 1 are our x and y values. So we need to use the fact that r squared is x squared plus y squared, that is, r squared is negative 1 squared plus negative 1 squared, or 2. Also, tangent theta is y over x, so that's negative 1 over negative 1, or 1. Now there's several values of r and theta that satisfy these equations. R could be square root of 2 or negative the square root of 2, and theta could be pi over 4 or 5 pi over 4, or we could add multiples of 2 pi to either of these answers. But not all combinations of r and theta get us to the right point. The point with Cartesian coordinates negative 1 lies in the third quadrant. But if we use a theta value of, say, pi over 4 and an r value of square root of 2, that would get us to the first quadrant. So instead, we need to use the polar coordinates of square root of 2 and 5 pi over 4, or, if we prefer, negative square root of 2 and pi over 4. We could also add any multiple of 2 pi to either of these values of theta and get yet another way of representing the point in polar coordinates. This video talked about polar coordinates and converting in between Cartesian coordinates and polar coordinates using some familiar equations from trig.